Bom dia a todos. Yeah? Eu acho que sim. So, what is it? So, good morning, everybody. Welcome to SPLASH 2023 in Cascais. My name is Vasco Vasconcelos. And I'm going to tell you all some data about the whole event, SPLASH. But first, I would like to tell you that the keynote for Onward will start at 9:30. Yeah, so that Onward attendees can be here for the announcements and then attend the keynote for Onwards. Yeah? So I'm going to tell you some data about SPLASH, and then I'll hand the microphone to Mira Mezzini, the Review Committee Chair, to tell you a little bit about UPSLA. Okay? So this is one of the largest SPLASH in the last few years. I was looking at data, and in the last 12 years, this is the second largest conference in terms of participants, non-COVID conferences, so to speak. Okay, so there's quite a lot of students here, and well, that's good. That's very good. That's very good for programming language. That's very good for software verification because there will be a tomorrow. But it also says that I know you're worried about where the fees that you pay go. How do you use them? And a large proportion of that is to support students. Okay, we support students with student research competition, programming language mentoring workshop, doctoral symposium, and the reduced fees for students. Okay, so I'm very happy that we have almost 40% of students within us. So this is the second SPLASH after COVID, and we decided it will be mainly in person. We believe that we have to meet at coffee breaks in front of a glass and of a drink, and but nevertheless we still allow remote participation. Okay, but you will see that remote participation is quite small compared. It's less than 50 compared to the whole number. And as for the workshops and conferences, we decided that the PC chairs will decide what they want to do. Some conferences do not allow remote presentations, others would. Also, so this is a conference in Europe. It's no surprise that the majority of the participants will come from Europe, almost 60%, followed by North America, that is US and Canada, and Asia. Okay, and on the 3% you'll find the Brazil and Chile, Algeria, Nigeria, Australia, and New Zealand. So this is a very large conference. It's probably one of the largest in MF. In a large event, it's probably one of the largest in number of conferences. We have 8, including UPSLA, we have 8 conferences. So we have 7 co-located conferences. We had PPDP and Lobster for the first time with SPLASH. We had an MPLR that is with SPLASH again after a few years. And then the others that are usually with SPLASH. We also have 10 workshops, and we have these tracks that I've mentioned before, like the Onward, the papers, and the essays, and the programming language mentoring workshop, the student research competition, and all that that are usually with SPLASH. So this is a very large event. So 720 days have passed since Mira first asked me whether I would like to do SPLASH in Lisbon. And I said, why not? But big mistake. It's a huge endeavor, but in the end, I think it will. Everything is going okay, I think, and I'm happy that you all here, and we will have enjoy this conference. So this is a number of messages in my mailbox a few days ago, and also in the last week or so, we started using Discord among the members of the working the organizing committee, and I lost the count of messages in Discord. They are produced quicker than I can read them. But the good thing is that we count with an amazing organizing committee. I mean, an event of this size cannot be organized without really the help of this professional organizing committee. I'm not going to name all of them because we'll see them in the page. So if you go to the main page, organizing committee, you will see there's 30 plus members. And so this 2K message in my mailbox, the number is that low only because all these people, they work by themselves. They are pretty much autonomous, and they don't have to report everything to me. Otherwise, I wouldn't, I think it would fill my quota at the university. So, and in general, for each of these roles, we have two chairs. So that knowledge, and usually these chairs stay for 2 years, and we have one junior and one senior, and then so that the knowledge is passed. And so these are great members, and all these people work for free. They donated a large time of a large part of their time to organize this conference. So they really deserve an applause here. And on top of that, we still had 50 student volunteers for which I don't have the photographs. So to complete my introduction, we also I would like to thank all our sponsors at different levels for supporting the conference, including SPLASH'23, which is the umbrella for a series of conferences that you may know of: PLDI, ICFP, SPLASH', and POPL. And that's it. So enjoy the conference. I'll be around if you want to, and if you need anything. And I'll now let Mira introduce UPSLA. You want to use this to change? And this goes there. This is only if you need to change your slide.
Continue.
Cancel. Can you cancel it?
Okay, good morning, everyone. Great to have you here. My name is Mira Mezzini. As Vasco already said, I'm still the chair of the review committee for UPSLA. And Vasco, I hope you still will talk to me. We'll still be friends despite me being the reason for you to suffer, but be ensured I suffered as much as you. It started even earlier because even compiling the review committee started much, much earlier than 2022, already in 2021. And the same as you, when I was asked, I have to say I didn't think too long. I mean, this is my home, this is my community, this is where I grew up as a scholar and eventually will retire. So it was a great honor for me to take over this role, but also a huge responsibility. And as you see, I present myself as associate editor of PACMPL, which I am. This is the proceedings of the ACM on programming languages, and that's the journal where the UPSLA papers appear. And the journal has, unlike other journals, this specific feature that it has calls for papers. Namely, currently we have 2 calls, and 2003 had a call in October 22 and one in April 23, the second call. Some numbers in the first call, we got 93 submissions, and out of those, including 9 resubmissions from the previous round, which is basically the second round of UPSLA 2022. And out of those, we accepted 31 articles, which are published in the first issue, UPSLA issue of PACM-PL 2023. In the second round, we got 211 submissions, and including 14 that we passed from the first round to the second round, papers that were decided to revise and resubmit, and we accepted 79 of those, which have appeared already in the second issue of UPSLA PACM-PL. How does the reviewing process go once the papers are in? And one number I heard that this year the submission numbers are in the first round even higher, which is a good sign for the community. Now the process itself, so we used an AI-based initial assignment of the papers to reviewers, and then we asked the reviewers to do a very quick review in the sense of looking at the paper abstract introduction and just judge whether they feel comfortable enough, whether they are experts in reviewing this paper, and the goal was also to identify cases where we need more additional expertise. Phase 2 is the normal phase, standard phase, what you know. Reviewers had to put a lot of effort in reviewing papers. There were 3 reviewers per paper. And at the end of this phase, we formulated explicit questions also in addition to the comments in the reviews for the authors, and received their responses, which were discussed together with each other reviews by the reviewers in a very intensive way. I think this worked perfectly. I'm very happy about the process, the outcome, how seriously the author responses were taken by the reviewers, by us as the committee as a whole. And to give you some numbers, I looked at the comments, the amount of comments, and altogether, including reviews, responses, comments, we had 5,500 roughly pages altogether, a huge book, and there were roughly 5,000 reviewer comments in the discussion among each other, while also discussing the author responses. Sometimes this amount of comments and discussions amounts to a bigger paper than the paper itself, which is a very good sign, I think, for authors. I believe at the end, we were able to put together a very nice, diverse program, and we put a lot of effort in taking very seriously the author comments. Some of the papers, kind of roughly 10%, got a Distinguished Paper Award. Here, basically, the process was also very simple. We got the papers that had straight A's, plus a few that had mostly A's, but let's say a B, but were nominated explicitly by reviewers, only 2 of them. The papers, in no particular order, are accelerating fuzzing through prefix-guided execution, grounded copilot, how programmers interact with code generation models, languages with decidable learning, a meta-theorem, live pattern matching with type holes, algebra geometric algorithms for template-based synthesis of polynomial programs, then randomized testing of Byzantine fault-tolerant algorithms, a mechanized concurrent separation logic for weak persistent memory, initializing global objects, time and order, formal abstractions for packet scheduling, bring your own data structures to data log and solving string constraints with lengths by stabilization. All the papers you can find in the program have had this sign of having won an award. For now, I just would like to ask the authors of those papers that are in the room to just get up and get our applause for their award. So at the end, altogether, I think we have a very nice program, and I would like at this point to say thank you to authors for sending their work to UPSLA, to submitting their papers to UPSLA. I would like to say thank you very much to all the review committee members. There are too many for me to show the pictures on the slides. We will have to spend a lot of time going through those slides. But again, if those of you that are in the room, please stand up and let us give you a huge applause, because this is a huge amount of work that goes into reviews. Let me also thank the keynote speakers. We have 3 keynote speakers, a great mixture of keynote speakers, keynote talks, I think. Dimitrios Vitinotius, Joe Hellerstein will be here with us tomorrow, and Amal Ahmed. Again, thank you very much for accepting my invitation and being here with us. And last, but certainly not least, I'm very thankful, very grateful to the associate editors, Derek, Sophia is here, Shriram and Patrick Oyster. They also didn't quite know what they were jumping in when they asked them to join the team as associate chairs. And in turn, I also didn't know quite exactly what ended up being for me. It was a great experience with these great colleagues. They helped a lot in ensuring the quality of our reviewing process. And we had so many discussions. At some point, I think Shriram said to me, you thought we would be, or Sophia, I think it was Shriram, said to me, you thought you'd have less work by having us on board. I think it's more work that you got. But it was worth every minute of it, discussing with them and disputing with them, and they disputing among each other. And now, I would like to thank Ragnar. At the end of the room, Sophia called him our hero today. He supported us in all the process, managing this complex structure like hot CRP and in all matters and issues. So we couldn't do our job without him the way we did it. So that's it for that part. Let me just say, you are a great community, and let us, all of us now, enjoy the conference and cash. Thank you. And with this, it's my very great pleasure and honor to introduce our first keynote speaker, Dimitrios. I hope I was not too bad with your last name, Vitiniotis, I repeat, to make it hopefully better. Dimitrios started his academic career with his studies at the National Technical University of Athens, and then he moved on for his PhD at the Pennsylvania University, and after that he spent some time with Microsoft Research in Cambridge, I believe with the Haskell team, and now he is with DeepMind. Dimitrios has done work in all different aspects of programming language design and implementation, and also applying the PL techniques to other areas, in particular in the last years, to making sure that machine learning algorithms scale up. And this is the topic of his keynote today, and I'm very excited to hear what Dimitris has to tell us. So please welcome him together with me on stage with an applause. And Dimitris, the stage is yours now.
Give me a few minutes, a couple of minutes to set up. Yep, so I think this works. Time, I can see the time. Okay, great, so let's get started. Thanks very much for having me here. It's a great honor. It's really actually my first big conference talk after many, many years, like before COVID, really. So I'm honored and terrified. So this is the work that we've been doing in DeepMind for the past several years, and it's about scaling machine learning models, really. And we're going to start by talking a little bit about what is a machine learning program. And a machine learning program is really the numerical. We're going to refer for this talk to the numerical computations that are used for training or serving machine learning models. These are n-dimensional array programs. They consist of linear algebra ops. Typically, the types are statically known rank, dimension sizes. And these programs are generated through Python tracing, for example, from high-level frameworks like JAX or PyTorch or TensorFlow that you may have heard. And because they are traced out, you don't see algebraic data types, you do not see dynamic control flow, or very little of it. And they're typically purely functional. So, you know, down there you can see an example of a training step where in Python, where basically a training step takes the parameters of the neural network, the optimizer state, and some samples, a mini batch, for example, computes the gradients of the parameters with respect to the gradients of a loss function with respect to these parameters, and then applies the optimizer to update the parameters for the next step. So training a neural network is really just a big process of training steps. These programs are generally easy, right? I told you, purely functional, no interesting data types, no control flow. However, they are computationally very, very intensive. So we have reached the point where we need more than 10 billion petaflops to actually train some of the state-of-the-art neural networks. And just to kind of put this in a bit of perspective, if you had 4,000 NVIDIA A100 GPUs, which is not the top of the line, but it's kind of a pretty beefy accelerator, you need to keep them training continuously for about 3 months. And that is assuming that they reach peak performance, the nominal peak performance, which is very difficult to do, ignoring any communication synchronization cost, and also ignoring system failures and restarts, which are actually quite typical in a data center deployment scenario. So, so these kind of programs run in big clusters, and this is a figure from a recent Google Cloud offering for some accelerator setup. For the purposes of this talk, I think it would suffice to think of these systems as devices and topologies. So there are the accelerator devices like a cloud TPU v4 up there, which is basically a device that has some local memory. It has some units to accelerate specific operations like matrix multiplication. And then these devices are getting connected into interesting interconnects. So this is a figure again from public Google Cloud. This is not for TPU v4, it's for TPU v5e, a slightly different variant. But the way the TPU chips are organized in this setup, for example, is that they're organized in TPU pods, and a pod is a collection of this kind of TPUs connected by a fast local network. It's called Inter-Chip Interconnect Network, ICI network. But you can also go across pods through the data center host network. So you have this kind of hierarchies of communication hierarchies in these offerings. And a lot of that stuff is actually known externally. So there are papers about the TPU architecture and interconnect, if people are interested. Now, Of course, you need parallelism, right, to train this kind of model. So the simplest, more traditional form of parallelism is what people have been calling batch parallelism, where here you have like two devices, and they share the same parameters. So, for example, the parameters would be loaded in each of the devices. They could be shared. And then you have one batch or one shard of the batch if you want going into one of these devices, another one going to the other device. And there's some computation that computes the gradients with respect to the parameters. This is if you've heard of the term backpropagation. So this, there's some forward execution, some backwards execution of the gradients. And finally, you get to produce the gradients for the parameters. But what you need to do mathematically for this to be correct, you actually need to reduce. You need to sum the gradients from the multiple devices together and make sure that every device gets that sum. And then every device can proceed to independently update the parameters. So the parameters are kept, if you want, shared by virtue of the update function happening in all of the devices. This is a specific setup. You know, there's various variations of data parallelism. But the important thing here is to notice is that you do need this communication in between. You do need this synchronization in between. From around 2020 onwards, it was pretty clear that, that certain parallelization strategies emerged. So if you want to parallelize a program, it wasn't a completely unstructured way of doing it. And some of these strategies were motivated by the need to scale for these large language models that everyone is hearing about these days. So, okay, data parallelism pre-existed, but certain forms of parameter sharding appeared, like Megatron-style parameter sharding, optimizer gradient sharding. I'm just throwing some terms here and some papers on the right. And the key thing for this conference is that these were all strategies that were, it was a small number of them, they were easy to describe at a high level, and they composed. For example, there's this kind of nice paper here down left, which was actually a study, an experimental study of what are the effects of composing these strategies for large language models on GPU clusters. And some people attempted to even do search over some kind of higher level strategies. Like this FlexFlow paper from in the middle. Okay, right. So just to give you a small flavor of these strategies, I've told you about batch parallelism. I'll tell you about a little variation of data parallelism, where basically on the right, you see there that the parameters are not actually shared on the two devices, they're also sharded. But in order to compute the gradients for the parameters, or in order to compute forward the network, you do need the full parameters. So what do? Right before you need the parameters, you issue an all-gather communication primitive. You get all the parameters on the device, you do your computation, but then, you know, that big tensor that you just collected from all of the devices is very short-lived. So actually it doesn't matter too much. You can just throw it away and you know, use effectively that memory space for activations as you proceed executing your network. So whereas previously the full parameters were live on the devices for a very long time, now the full parameters come on the devices for very short amounts of time. And also, you don't need to compute to keep the full parameter gradients on both devices all the time. Instead of having an all reduce on the gradients, you have a slightly cheaper operation that's called all reduce scatter, which basically reduces and scatters the gradients. So every device gets a shard of the gradients. And then the update is actually an update on the local shard of the parameters. So it's kind of an interesting variation that reduces a little bit the communication time. The all reduce becomes reduce scatter, reduces the optimizer time from the computation. But in exchange, it adds more communication and also improves the memory on the device. So it's a really complex trade-off of things that are happening at the same time. How do you figure out what is the right thing to do? And there are forms of model parallelism. I'm not going to go into a lot of detail, like pipelining and forms of model parallelism where you shard the parameters, but then you need to synchronize the activations of the network at various points. Let's not go through a lot of detail in this slide here. So parallelization is hard. As I said, you know, even for these structured forms of parallelization, there is a lot of trade-offs that you have to take into account. And, you know, you're given a model, you're given a TPU system, for example, or a GPU system, and you have all these kind of strategies that you need to pick the specifics of these strategies and how to compose them. And also, the other thing is that happens if you are a machine learning engineer, but that also happens if you are a systems designer. So you're a systems designer, and you know you are given the new architecture for the new GPUs or TPUs or accelerators. And you have some representative models that you think they're going to be used in the future. And you want to figure out, OK, how much memory should I actually have on every device? What should be my interconnect type? Should I be using a hierarchical system, a switched system, a mesh? What is my ICI domain size? How many devices should I have on the fast network? And how many devices should I let them communicate through a slower host network, for example? What should be my host connectivity? How much bandwidth should I put? How many NICs should I put per host? And the key thing to note here is that you should not really penalize a system design just because you picked a completely unsuitable parallelization strategy for that system. So it's kind of parallelization and system design kind of go hand in hand. And that was kind of our first intuition. Before I jump a little bit to what we did, I just want to tell you that there is a very, very nice software abstraction for these kind of systems, which is viewing them as n-dimensional arrays. So here on the left, you have a 2x4 hierarchy of 2 servers, and every server has like 4 devices. They're connected in a ring, in this case. I don't know why. And you can view them as a 2-dimensional array, where devices D0, D1, D2, D3 are kind of local to one server, and D4 to D7 are local to the other server. And these kind of n-dimensional system views are convenient, and we like them when we talk about parallelization, because it's very easy. It's easier to reason about communication. So you know that if you want D0 to D3 to talk to each other, you can go through the local network on per server. But if you want D0 to talk to D4, D1 talk to D5, D2 talk to D6, and D3 talk to D7, you have to go through the host network, and that could be more expensive, and the links could be oversubscribed. So I just want to say that it's a convenient abstraction that we're going to be using in the rest of the talk. OK, so composing strategies with meshes. So meshes and composing strategies is a really good match. So here we see 6 stages of pipelining. Pipeline is composed of 6 stages, and within each stage you do 64-way data parallelism and 16-way parameter sharding. So you can think of a cluster of 6 by 64 by 16 devices. And the very first thing that we did here is that we decided to, since we want to talk about composition of the strategies, we decided to come up with a little modeling DSL where actually programmers, systems designers could actually sketch some of these strategies. So we had a little IR that composed of computable blocks that described abstractly the input shapes, the output shapes, the parameters, the flops, and the memory requirements for a block of code, if you want, communication primitives, and some constructs to nest parallelization strategies. So here's how it would look. You would say in this example here, you would say this is a pipelining consisting of 6 stages, and we're going to name the mesh axis we're going to be using. And then within each stage, you're going to do 64-way data parallelism. And then within that group of devices, you're going to do 16 ways model parallelism. And the actual computation you will be doing is a sequence of transformer layers, for example. And a transformer layer is self-attention, which is one of these computable blocks, followed by some communication on the model axis, more computation, and then more communication. So some human had to take one of these models and actually script these strategies. But the benefit was that we did have a very concise description of these strategies. Now, if you take this kind of little DSL and you in addition, you write on the other hand, you expose a target system interface, basically an interface that tells you how many flops you have per device, how much memory you have per device, what's the memory bandwidth you have per device, number of devices, and also a way to map some kind of, to map the software, the parallelism axis into the physical topology axis and an analytically computed cost. Then you could actually simulate these programs, these strategies very easily by just writing an interpreter. So you could say, I'm going to the simulate function has a signature, takes a computation and a target system and gives me back some metrics. So that's kind of what we did. And we had some internal validations, but we also did the brave thing of taking an external paper that had one of these big studies on a cluster that we did not have access to. And we tried to see, given what is publicly known about this cluster and what is publicly known about this paper, can we simulate it? Can we get the same results? And we sort of did. If you see that figure up there, The thick lines is what our simulator predicted, and the dashed ones is what the actual experiments found for several configurations. So the trends are the same. The absolute numbers differ a little bit because, well, again, we didn't have access to really tweak our roofline models or network models. But what was even more exciting is that once you have this little DSL, you can track everything. You can track cost centers, and you can actually enumerate programs in this little DSL by code which is as simple as writing this kind of silly comprehensions that you see down to the right. And that gave you the ability to do systems co-design. So for example, here we have an 18 billion transformer model, a medium, small for these days transformer model on a cluster of 256 GPUs. I'm not going to tell you much about the topology, but what we did there is we wanted to investigate if every device has 80 gigabytes of memory versus if we start shrinking the memory that's available per device to all the way to 6 gigabytes, what's going to happen to our throughput? And the important thing to notice here is like the two arrows, is that if you go from 80 to 15, there is an impact. There's a moderate impact or small impact to throughput. The interesting thing to notice here is that this first column has a different parallelism, optimal parallelism strategy than this column here. So you change a little bit your parallelization strategy, and then you mitigate the effects of cutting the cost from a system. And then the other interesting thing here to notice is that if you really push the limits to the extreme, you say every device has 10 gigabytes or 6 gigabytes of memory, it's actually still possible to parallelize, but you have to introduce more interesting parallelization like pipelining. And you see this because of these green things that measure the pipeline bubble, which is some inefficiency introduced by pipelining. So despite the inefficiency, it was actually better than just picking a different parallelization strategy. Right. And I just want to kind of mention in tangent this kind of work that we did here, which it stemmed out of the previous work, which was, I talked to you about this kind of software parallelism and about viewing the hardware as an n-dimensional array of devices. And it was the obligation of the target system implementer to really express that mapping. But what we wanted to explore here in this paper, we wanted to say, well, actually, you could systematically explore the possible mappings. So that's kind of what we did. So why not? We have basically a tensor of required software parallelism and the actual n-dimensional array of devices. And there is a systematic way to enumerate the mappings, possible mappings. And then once we had that, we wanted to say, okay, now that we have this mapping, can we actually decompose collectives like all reduce to smaller primitives, smaller collectives like reductions, broadcast, reduce scatter, and all gather to make the reductions run faster. And that's what we did in this paper with Ning Ning. So it's a pretty interesting, nice extension of this work. Okay, well, okay, after that work, was it time to pack and go on vacation? And not really. There was still a lot of problems in this kind of work. And the problems are the following. First of all, it was a modeling DSL. It was not a solution for actually partitioning programs. Second thing is that as new papers emerged and new techniques evolved, we often had to extend the DSL with little extensions that we didn't really think about in the beginning. And it was getting a bit too messy and too low level, and we didn't like that very much. Then the other thing is that a human has to write the abstractions of these models, which is error-prone. They may forget some collectives. And then finally, really, when you execute a neural network, the image is not so simple. So for example, you have a backwards pass. The reductions, where the reductions are actually going to happen, they don't happen all at the end. Once you finish with the backwards pass, reductions could happen, depending on how the backend compiler schedules things, could happen in the middle of the computation. And we just didn't have good ways of describing this kind of scheduling improvements and possible overlapping of communication with computation. So we really wanted to kind of go after the IR that was actually going to execute, not a modeling IR. But we wanted to still maintain the same high level of abstraction when people describe the schedules, these strategies. So this is the birth of the PartIR project that has been our main focus for the last couple of years. It had like 3 goals. One goal was we wanted to enable teams that didn't have ML system experts to easily and automatically scale their models. So this is a large number of researcher teams with, let's say, medium or small compute footprint. They need a few TPUs, a few GPUs, a few devices. But then we also wanted to enable the teams that specialize in large models, the ones that have the machine learning, the systems expertise in them, to easily express, debug, and combine custom strategies. You know, these teams, they knew exactly what they were building, what they wanted to build, so they wanted to kind of instruct the compiler stack to just do the right thing. And this was a small number of specialist teams, but with a huge compute footprint. So the product in both cases was quite big. And finally, you know, we wanted to still enable the use cases that we had before, like co-design, or also use cheaper and less contented hardware, older generation hardware in our data centers. So I'm just going to have one slide that tells you all the good stuff you get, or that you would want to get, and then I'm going to tell you a little bit about how we got to some of these things. So the machine learning researcher writes their training step. They just write the math of the model, no model modifications, nothing to do with systems there. They just pretend they have a giant supercomputer that can run the model. Then they organize their devices in a mesh. And that requires a little bit of expertise sometimes. So I would say maybe that's the least kind of nice part of it. So we haven't automated that part, although, you know, we had all this previous work that could possibly do it. Then they write a schedule. So a schedule is a little bit like the high-level descriptions that I described before, but in a more traditional schedule, if you want, for this kind of community, halide schedule style, where you actually, one by one, you tell the compiler what to really do. So in this case, the schedule says, partition my samples on the 0 dimension and axis batch. And then it says, once you're done with that, find automatically the best model parallelism using the model axis. And once you're done with that, shard the optimizer state along 0 dimension. And also, we ask the users to provide some hints to help, especially with the automation part. If you have, for example, repeated layers, you don't want the search agent to really repeat exactly the same decisions for all layers you have. You just want to kind of, you really want to repeat the same decisions for every layer. You don't want it to search and rediscover. And then what you get back is you get back a partitioned device local function and some metadata. And the metadata says, how was the function actually partitioned? What do you need to do? How do you need to invoke that function? How do you need to shard the inputs and outputs of the function to actually invoke it? And also some per tactic metrics. For example, after every tactic, what happened with the communication primitives? What is the estimated runtime? What's the memory? What are the flops? What else? Yeah, I think these things. Now, that's really nice, right? You know, the machine learning researchers can just take the math and run it with these little scripts. Literally, the actual code is that long in most of the deployments we see. So let's see how we actually did that. I'm going to start like from the beginning. How do we actually get these kind of array programs from JAX that I told you about? So here on the left, you have a function, and the function multiplies the input x with 2 weights. So W is a tuple here in Python. And so you take W0 and W1, you just multiply x back to back with it. And JAX offers this kind of JIT transformation, which is effectively, it says, take the Python code, trace it out. While you trace it out, construct an array program in a lower level IR. This is the stable HLO MLIR dialect, which is an array IR that effectively wraps the XLA array language, which is what the XLA Google compiler ingests to compile for GPUs or TPUs or CPUs, and then runs these things. So that's what happens. And I mean, you will notice here that, you know, W in Python, that would be a tuple really, but in MLIR, it has been teased out into 2 arguments. So this is what I said before, this is the impedance mismatch between the Python program and the actual low-level program. The low-level program doesn't even have tuples in most cases. It has just arrays. Now, JAX also offers some transformations. So JAX.grad is the automatic differentiation transformation that's offered. So here, if you take the grad of the same function with respect to its first input, the parameters, what you expect to see some code. You don't need to read the code, but what you need to read is that it returns 2 values, and they correspond to the 2 gradients for the 2 W's, the W0 and W1 that I mentioned before. So that's how we get from JAX to these kind of array programs. And a full training step, well, it's really a JITted step that includes the gradients and the optimizer state, and you get like this kind of really verbose programs that include matrix multiplications, but also a lot of random number generation for some layers, or also vector ops for optimizers and whatnot. So, right, how does our system work? So the system works at a high level. We take this part IR JIT. So we start from this kind of JIT entry point as well. We have a variant of it, part IR JIT, and that accepts also these schedules. We trace out, like JAX, to stable HLO, and then we go into our compiler stack. And our compiler stack rewrites the programs according to the schedules, or also according to some of these tactics involve automation. So for that, we have a search algorithm that is using a simulated cost model. This is the simulator at the level of the IR that I described before. And the simulator, again, like before, takes a target system specification and a low-level IR and gives you back some metrics about it. And then finally, the program comes out and gets compiled by the XLA backend compiler. But now that code also involves communication primitives as well. So, OK, so here's the key idea of part IR, one of the key ideas of part IR. The theory behind it is based on linear algebra homomorphisms. What do I mean by that? Is if you have a dot operator, like a matrix multiplication, it takes two tensors, 16 by 32 and 32 by 64. You get out a tensor of a matrix of size 16 by 64. You can actually view it as producing the output along the 0 dimension in chunks, where every chunk could be produced by a smaller matrix multiplication of a slice of the first operand with the full y second operand. And this tile 0 says that you should stack all the chunks together on the 0 dimension again. So, of course, there's more ways that you can see a matrix multiplication homomorphism. You can say there's the contracting dimension as well, the dimension of size 32 here in the middle. So you can say, if I slice my first operand on dimension 1, and if I slice my second operand on dimension 0, then if I do a matrix multiplication, every time I get a chunk of 16 by 64, the full matrix size. So what do I need to actually get the right result? I need to sum all of these pieces together, and this is expressed with this reduce business here. So you have these tiling loops where effectively the monoid about what you should do with the local computation, should you stack it or should you reduce it, appears here as a little attribute in the IR. And some notes is that the loops themselves bind to specific mesh axes. And that is actually convenient for the parallelism story that I'm going to describe later on. So you can think of, you can think that this restricts the way you can nest the loops. So you can never nest these loops in ways that are not allowed by the mesh you have available. So you can never double nest the same axis in a loop nest. That is going to let you lower these programs in a SPMD fashion in these meshes very easily. But the second thing to notice is that the semantics of this is not really tied to these axes, so you could view these axes as just annotations, and you could ignore them, and you could lower these loops sequentially as loops that actually concatenate in the end or reduce in the end. And in fact, that's what we do for our reference interpreter. So that was kind of idea number one. Idea number two is that, OK, we have a generic way of expressing these homomorphisms, which we call the tile mapping registry. And basically, it says here, if you want to produce the output in chunks in dimension 0, you should be slicing the first input on dimension 0 and leave the second one untouched, the second operand untouched. There's another one for the output dimension. But also it says, if you want to produce the whole output, you could actually do a reduction where you slice the first operand on dimension 1 and the second operand on dimension 0. So it's really like a coding. Think of it as a sort of a refinement type for this kind of linear algebra operators. It's a succinct coding of these homomorphisms. And there are other ways you could express this with affine maps, for example. And I just want to stand on the engineering benefits of having a registry. So first of all, it allows you to bring your own array dialect. So if you want to partition a new array dialect, other than the XLA dialects that we've been thinking with, it's very easy. You just bring a new module that describes the registration of this dialect with these homomorphisms. The rewriting code is actually shared across many ops. And there is, it's very easy to kind of concentrate the behavior of the system in one place, in this tile mapping registry, and also to incrementally add more mappings. As you discover, for example, that some operator is very tricky, you don't really understand its full homomorphism behavior, it's very easy to just add another one at the point when you discover, a new behavior. For example, for scatter op, XLA scatter ops are a really complicated operator, and initially, maybe we supported, I think, just batch parallelism. But then over the time, we discovered some more interesting behaviors, and we started adding more and more and more mapping. So that was easy to do. And it is a fact that we have not seen semantic bugs over 2 or 3 years of development, I think mainly because of this separation. So we never had like rewrite code, pair op rewrite code. We just had this kind of centralized rewrite code we just ran once. So the trusted code base was small. Okay, right. So once we had that, we could actually define compiler action spaces. So the compiler APIs now can expose some of these tiling actions. So this is a tile action here. If you see a value, which is a tensor, you can say every value can be tiled, can be expressed as a loop that on every iteration just slices a piece of that value and gives it back to you. So we called it initially, because it's very dumb, we called it dumb tiling. It's how you bootstrap. It's how you start creating the loops in your program. And then the second API, compiler API that we exposed was propagation. So if you have a dot operator, here a matrix multiplication, and you see that the first operand is actually produced by a loop, you could actually convert the dot itself to become a loop guided by the tile mapping registry. And then later on, if you're going to compile for temporal, you could fuse the loops. If you're going to compile for SPMD, you didn't really need to, but you could do it. But the thing is, you create more loops out of existing loops based on this kind of homomorphisms that you have. And we had propagation going from operands to ops, as I described here, propagation going from op uses to ops, and also sideways propagation going from one operand to other operands. Right, now we have the action space. That's very nice, because now it can be targeted by either manual partition tactics or automatic partition tactics. So, for example, an ML systems expert would say manual partition my inputs on dimension 0, and samples was a full Python tree with like 3 array values in the leaves. What you could get, actually, you could get these 3 actions that said tile argument 55, 56, and 57 on dimension 0 along the axis badge, and then propagate the consequences. And the agent could also be picking arbitrary things and say, oh, tile argument 4, or tile argument 16, or tile argument 24. So our agent was exploring a tree of actions, really. And the right loops will be inserted by propagation thanks to all of these linear algebra homomorphisms. Right, I just have one slide about automation. Automation was really important because it accelerated research and model iteration, and it minimizes really the manual labor, especially for teams that do not have experts. And it has been used, and it's been used particularly for models where people have unknown or not universally agreed upon sharding strategies, like graph nets are an example of this. We used Monte Carlo tree search because we exposed these imperative actions, so exploring one action at a time and trees of actions seemed like a very good fit for it. And why does it work well? The reason it works well is because we thought very hard about how would a human partition a model. So humans would actually try to shard some of their parameters, and they would expect that the matrix multiplications inside the models would be sharded along the data. So we exposed a little work list to the agent that only included the function arguments, and the agent was actually able to pick from these. And as we tiled some arguments through propagation, other arguments became obsolete. So the search space started shrinking very drastically as soon as you started taking some right decisions. And also, humans know that they have repeated layers, so we don't need to independently search for them. So we asked users to tell us, If you're using repeated layers, tell us some grouping, that we should not repeat the same choices. And yeah. So how do we lower these loops? As I said, these loops could be lowered temporarily. In fact, they are lowered temporarily in the reference implementation, but they're lowered mainly to SPMD parallelism, single program multiple data parallelism. So we introduced a separate dialect for that, separate language for that, IR, slightly lower level, where you take one of these nested loops, loop over axis X and loop over axis Y, and you flatten the nested parallelism out into flat parallelism over both axes, and inside the region of code tells you what to do on a per device. And that IR also included types to express distribution, replication, and explicit collectives and distributions. And it came with a proof of correctness, which will be released when we release the paper at some point. Here, the paper on the right is a paper that is actually open. Does not describe the lowering, but gives you a good introduction to part IR distributed types, and also how to optimally compile a redistribution operation to lower level collectives. Okay, so how do these types look like? If you have an axis, if you have a mesh X and Y, and you have some data that's replicated on all of these axes, basically, you can think that types have a global denotation, which is what is the value that they actually capture, and that they also, can get the local type per device. So part IR redistribute commands never change the global denotation, but they change the actual physical distribution of the data. So you have a distributed tensor here where all the data is replicated on all devices. You can issue an old slice on the y-axis. So then the top devices get only the top data, and the low devices get only the low data. And then you can all slice on the x-axis, and then all devices get the left data, and the right devices get the right data. And then you can also all gather all of them back, and you get back to the original type. So you can go through collectives and implement this kind of redistributions. And as we know, part IR SPMD had a global view of the computation, had this kind of distributed types, but we wanted to compile to device local code. So for that, we introduced an intermediate level of abstraction, which we called part IR MHLO, which effectively was like part IR SPMD, but had the local view of these collectives. Instead of having these complicated types, I talked about the global denotation, it had this kind of local types here. And there were optimizations that were easier to express if you knew the global denotation, and there are optimizations that were more convenient to just express if you just had the local types here. And this is a higher level variant of the XLA collectives that actually talk about device groups. So we introduced kind of this higher level of abstraction at that point. And I just want to kind of stand to this point for a little bit. One lesson we learned is it's very useful when you try to build the right level of abstractions for the transformations you want to make, because that helps you reason, be correct, test them. So for example, here's a transformation from a paper that appeared in SPLASH'23, which says if you see a matrix multiplication followed by a reduction and a scatter, then you can actually rewrite it to hide the communication cost of this scatter in a loop. Without going into a lot of details, that loop allows you to overlap a permutation with the actual dot general. So it's a little bit like it has a systolic array flavor to it. And the key idea here is that we introduced some abstractions that were not in the array language we were working with, XLA or MHLO, that made this code very easy to debug, view, reason about. So, MHLO XLA does not have a structured for that tells you the static number of iteration count. Okay, it doesn't have a collective rotate. So this is rotating the data, sending the data to your neighbor along a specific axis. So all the devices of a specific group send to their data to their neighbor. And also we introduce this kind of collective with a slice and a shift. That also doesn't exist. So expressing this very succinctly was very nice because we would implement this in a little pass, whereas the actual implementation, at least the original one in this paper, was baked in with code generation effectively in the partitioner. I want to talk a little bit about MLIR. So MLIR is a framework for defining dialects and has been very useful for us because it allows us to share languages and constructs and operations from other languages. So we didn't write any array operators, and we didn't write any compiler infrastructure ourselves to manipulate and write passes for these array operators. They all existed in the MHLO dialect, which someone else had developed. When we import to part.ir, we pattern match on some of them and we introduce some of our custom ops. So we have a soup of, let's say, MHLO array operators and our own operators. And that's happening at the part.ir level as well. We introduce these loops on top of the existing IR. And then when we lower, we remove the loops of part.ir and we introduce temporal loops, for example, here. And then when we lower even more, we remove these loops and we introduce part.ir MHLO collectives or for loops. And then finally, we export to MHLO. So MLIR is a great framework for adding constructs, removing constructs, expressing the invariance at every level of your stack. So as I said, it's a framework to define dialects and passes. It standardizes the compiler data structures across different projects. And that really means that diverse engineers from different teams actually speak the same language now. And it has a lot of things that we value and love from building compilers in functional languages, so which is my background. So for example, it makes it relatively easy to define rewrite rules and patterns in declarative ways. And also, the compiler implementation itself pervasively uses value semantics for things. So it feels natural, easy to learn, and combined with good C++ practices, it's actually a pleasant experience. And it is easy to reuse other dialect attributes, types of operation, or operations, which means that it really fosters collaboration. So there are teams working on various compilers across Google and the rest of the world, and MLIR really gives them a kind of a common point to talk about and develop things and share things from each other, and also adds a sense of shared infrastructure ownership. Everyone owns this infrastructure, it's for everyone. And really, we, in our team, we do have some compiler PhDs, but we do get mostly very good engineers. And they're not compiler experts. They come from a Java background or whatever. And they very quickly turn into proficient compiler engineers. And I think largely because of this framework and guidance from our team. Okay, so a good idea that we had in this project was to actually separate the partitioner from the backend compiler. Some people keep asking, why is a partitioner part of the compiler? Is it not a part of the compiler? What is it? In this project, it has been very beneficial to separate the partitioner from the compiler because it enabled innovation around the partitioner. So if you think about a core compiler team, like for example the XLA team, or then whatever team each company may have, they have to tend to everyone's needs, and everyone's needs are not the same. The compiler team has to actually prioritize things and design things right for everyone. Whereas if you actually think about it, there are different teams with different needs, and going from a monolithic compiler to an adaptable compiler stack, it's really important. So just to give you some examples, by ingesting stable HLO on top, we were able to introduce some custom operators for specific needs. So for example, to express better vectorizing transformations from the source level, or to express some extensions for MPMD computations that I'm going to talk about in a bit. And then also after we exit the compiler stack, other teams, because this was not inside the compiler, other teams were able to take the program that we emitted and actually do more interesting rewrites to it. Like, for example, rewrite the communication collectives in ways they found would be better or optimal for the specific runtimes that they were planning to run these things on. So the only wish I had in that point is that if only the backend compilers expressed some more APIs and hooks for the upstream compiler components to drive them and help them steer to not undo things that the upstream compilers wanted to happen. So I want to kind of mention one good thing, which is incrementality. Incrementality, I talked to you about these kind of actions. You do tiling and propagation that keeps rewriting the module. So that's actually very, very good for this kind of conflict resolution problem that we call. So here, the colors are not very visible, right? So here you can say you want to shard the 0 dimension of the batch, but you also want to shard dimension 1 of the parameters. Because this is the diagram that I showed you before. You shard the batch and you shard the parameters. So the problem is that this dot, this matrix multiplication, potentially could be sharded on the 0 output dimension or on the dimension 1. Which one should we have picked? And the answer is that if you do these choices sequentially, you are in better luck than actually throwing these constraints to the compiler and let the compiler figure it out. So here you say tile batch on dimension 0, and you will get a loop. And then you say tile the parameter now on dimension 1, and you will try to get a loop, but you cannot double nest, right? So you cannot further partition the dot. It's already partitioned on the model batch. So what happens? Well, you just have the dumb tiling of the parameters. And if you lower this program, you will get the old gather that you expect on the parameters. So doing things incrementally really helps with this conflict resolution business. So there's the other approach, which is you add all your sharding constraints at once, and you let the compiler figure out what to do. Or if the compiler doesn't do what you do, you ask the user somehow, or maybe the user finds out what to do. And here I have some plots that actually show that, yes, it is really important to, if you try to do blind, just throw all the constraints and let the compiler do its thing, even this kind of compiler, it's not going to perform as well as if you had resolved the conflicts, either with internal constraints yourself or with this kind of sequentialization that I described. Right, and I really only have 2 more slides. Okay, so that's what we've done. I think you have a good overview of the whole system. So what comes next? First thing that comes next, things that we are thinking about or we will be thinking about in the future, beyond SPMD. SPMD is good, but it's very uniform to have these meshes. In reality, you want to have like heterogeneous systems, clusters of GPUs and TPUs, or different sized clusters. So you want to move really from SPMD to data flows of SPMD or MPMD. On the automatic partitioning side, I told you that sequentialization is good for conflict resolution, but there are still cases, especially in some exotic models, where you do need some internal guidance, even in part IR, because taking one choice for the input may still require to do some interesting thing in the middle of a model. So we have some work to automatically discover exactly the right places where you need to make a choice. And the challenge there is you don't want to expose too many intermediate points because you're going to really make your search space blow up. You want to just figure out the right intermediate points. Then we would like to revisit the rewrite-based propagation. So the algebra homomorphisms, great idea. Using loops themselves, maybe. It is good in terms of semantics, but actually we rewrite the module. And rewriting these kind of huge modules of like 500,000 ops continuously while we do search is expensive, and it's expected to be expensive. So could we somehow combine the good ideas of these kind of algebra homomorphisms and some ideas from layout propagation or sharding propagation from GSPMD to make things faster? And the other thing is, when we go to extreme scale, you don't expect that you have a program to run, I don't know, 4,000 TPUs I mentioned before, or more actually, to run without failures. Things are going to fail. So how do you recover from these failures? And do you perhaps push the problem to the runtime and you say, hey, please, runtime, give me a view of the system that, where there's no failures, a virtual system, or do you virtualize everything, or do you actually try to make the IR itself more aware and the API more aware of the failures, and you provide recovery mechanisms? And I have a hunch that this could be related to kind of declaring effects and effect handlers in the program to tell you what to do in this case. And the challenge here is, again, how to do this without changing the model code. Like we never want to change the math of the program. Okay, right. And I just want to conclude. How will the future AI compilers look like? So this is some predictions, or maybe just kind of my wish list. I kind of like these ideas, but I don't know if they will ever become true. So I think we should be going to compiler components, not monolithic compilers anymore. We should be defining, there's the backend compiler and the partitioner is kind of one example. Custom teams have custom needs, and the compiler pipelines should be adaptable, basically. But that also means that you need to make sure that some of the actions, some of the requirements for some of these compiler components should kind of be exposed by the downstream compiler components. I expect that we will see progressively more use of search and AI, especially for problems that are not like time critical. You don't need to compile within like a very small budget. So I expect to see more and more hierarchical and learned cost models and techniques like Monte Carlo tree search. And I think really the other thing that intrigues me in this space is that compilers compile, especially in big organizations, compile hundreds or thousands of programs every day. And that's a lot of data and a lot of optimizations that are happening. And that data is not collected very well to really kind of inform us about what is the actual compiler choices that have been done here, and how could we use all the data across users, across compilations to really learn something and improve our compilers. So if you think about a compiler passive or a compiler component as a service, that could be a service for everyone. Every user of XLA could be using it. What can we do in that space? Right, and with that, I'd like to thank you. This is a bunch of the team and collaborators, and I will take questions in the rest of the time. Thank you.
How do we handle questions? Please walk around. So questions, please. Someone will bring you a microphone when you...
Hello, thanks. Very interesting talk. A lot of these optimizations and tweaks that you let the programmer do, just from my own experience, they can be quite unpredictable. So the programmer themselves they have to go through a cycle of trial and error until they actually optimize the code. So it looks like really long-term, the only solution is to allow these, AI programs to write themselves, right?
Yes, so we try to make the debugging experience easier because we have these imperative schedules. At least they can get early feedback. So, they say, I want to do batch parallelism, and they get metrics back, and the metrics say, you've inserted, all gathers. Oh, dear, I didn't expect an all gather in a batch parallel program. Something has gone wrong here. They require a little bit of expertise, but it's actually better than writing all the constraints, let the compiler do something, go run the program, trace it, figure out it's slow, figure out which collective is slow, and then going back. So we try to make this through simulation to make that process less painful. But yeah, automation. Some users don't want to bother with this, and they just go for automation. But I would say yes, there are search aficionados who really, really love the search and just put it in their models, and it's kind of just stuck with that forever. No one has turned back from search. Someone was telling me yesterday. But, not everyone trusts search yet. Yeah?
So, thank you. And I'm probably going to use the wrong terminology for what I'm saying, but I think that my question will be clear despite me using the wrong terminology. Okay. So perhaps you said it, but I was wondering, this language that you are proposing that allows to talk about how to architect the system, does it have a component where it observes the throughput or other runtime properties and then changes the architecture at runtime?
No, you're talking about the first part of the talk, like that little DSL, right?
Yeah, yeah.
No.
Why
it was
not?
just purely simulation.
I would have thought that this is a good thing to, to try.
It's done mostly in simulation. So in simulation, you would get a cost, but we never tried kind of taking the schedule and mutating it or rewriting it based on what we observed from simulation to get to. So we didn't try to kind of explore, mainly because it was so simple that we could typically we just enumerate the whole space and we just get points for the whole space. But I see your point, with more and more complex strategies, which that DSL didn't really capture. It captured it's a small set. You would need to explore a little bit.
Hi.
Oh, hi.
Hey, Dimitris. Thank you for a very nice talk. I just want to piggyback on your answer to the previous question that people don't, many people don't usually trust into the search. So in order to build this trust, do you envision that any of the research we do in verification and formal methods would be useful? And if the answer to this question is yes, then what kind of verification would be the most viable in this setting?
Oh, it's not a matter of trusting in terms of correctness. They say, I think it's a matter of it feels like too opaque for them. I mean, correctness, as I said, we really never had a correctness bug. Correctness, occasionally we get bug reports for correctness, and that has to do with verification because the numerics change subtly because we introduce all reduce, right? And all reduce moves a reduction, which was inside the metric multiplication unit, outside to go through the network implemented somewhere else. I don't really know. So we do get occasional issues like that. The training is not as stable as it used to be. Maybe verification could help with that, but then I don't know how to mitigate it anyway. It's like, you do want to parallelize. It's very difficult to mitigate. And yeah, the other relation where verification could be interesting here is that we have this tile mapping registry, and it's about homomorphisms. But people in the team have sat down and said, oh yeah, this is a parallel dimension. Let me add 1 and 0 and null here. Oh, this is a contracting dimension. We add 1 and 1. Some. No one has actually verified that stuff. We've tested the most tricky ops with exhaustive testing. Exhaustive testing. But it's unverified. So, yeah, I don't know.
Maybe I have a question myself. So, thank you very much first for the talk and amazing amount of work. And I hope the ML algorithm people appreciate what you do to make ML pipelines scale. Now, you mentioned the MLIR as a very good platform that has enabled a lot for your team. And I fully understand the pragmatics. My question is, do you see any need for research there? So as far as I am informed, this is basically an SSR-based intermediate representation. Do you see need for other intermediate representations that might be better suited for ML?
It's a good question. Like occasionally, so MLIR is for everyone. Is a semantics-less framework sort of. It's really a data structure, but it's really engineered to allow you to talk about SSA dialects or this kind of blocks with arguments, which is the modern way of doing control flow. But I think there are some interesting language design questions, IR design questions there, which is say you want to support forms of dependent types. The current MLIR framework doesn't really allow you to do that very nicely. So, how do you extend there? So, language design, IR design questions exist. Changing dramatically the IR to something different, I don't know. It has been useful so far to us until now, but I didn't know that before. So before I also thought that we would need abstract syntax trees and Haskell-like, functional programming-like data types. But it, as I say, seemed fine. We all know they're isomorphic, right, to some extent. So I don't know. There's interesting language design questions, interesting type system questions. How do you encode things? Often, if you try to do research in that area, you will be bogged down by the practicalities, which means that, the memory of an attribute is owned by the MLIR context. So therefore, if you want to add a value, if you want to store a value there, that value, someone else owns that memory. So you have to really think hard about the engineering problems. Yeah.
Do you have any data on if you have an expert do the manual partitioning and then you just replace it with an automatic partitioning?
Yeah.
How much worse is this?
So obviously it varies a ton, right?
Wildly.
A ton. So for the simplest, so we actually we do have some open papers that describe some of these experiments. So we are able to discover expert strategies for known models, like transformers, for example. And then for models where people just didn't know, just didn't get good manual shardings, we got better. That ICLR paper that I described, the graphness paper, the highlight paper, was produced by just using the automatic partitioning. They didn't actually write manual partitioning at all. So there is evidence that we can find better partitions. But it depends a little bit on the model as well. There are crazy models where we are not going to do so well, especially models that require internal partitioning. So if you start to do, if you think about, just going to give you a very simple example. in a transformer, there's one specific operation, it's called the attention matrix, computing the attention matrix, which is an attention matrix who has a size which is sequence length, how many tokens you had in your initial context, times sequence length. So it's a rectangular matrix, right? So that sequence length dimension comes from one input, comes from the original input. So it's almost like you've taken some kind of outer product at some point, right? More or less. So, okay, the input comes sharded on that dimension. How should you shard the transformer, that internal matrix? Should you shard it on the rows or on the columns? It's the same dimension. You know, you have to insert an all gather in one of the arguments, but which one? That's an internal choice, and you actually have no option to expose it through, sequentialize it through arguments. You only had one argument, the input. So there are models that are like that need internal choices, and they're not even exposed in our search space. We're not going to capture this specific sharding. But the work that we're doing now, follow-up work we're doing now, is going to uncover these interesting points as well.
Do we have more questions? Yeah.
Thanks for the wonderful talk. I think Ilya asked the correctness, but I want to ask the exact opposite. Have you considered, I mean, machine learning itself is imperfect, so why not bother introduce some approximation into the optimization process? So have you considered approximate computing, maybe even analog computing, so that we can get huge speed up by sacrificing some accuracy or perfection?
So you mentioned approximate computing.
Right.
So approximating so instead of sharding, approximating the models, or are you talking about, yes, can you clarify a little bit more?
Yeah, I mean, instead of guaranteeing the absolute correctness, why not,
I see.
Yeah, why not intentionally introduce some imperfection into
no, it's a very interesting work. It's a very interesting idea. We haven't done that so far, but it could be relevant, especially for the very large-scale experiments. I have nothing to add to this yet, but it is one of the things that we would like to learn more about. Happy to connect offline if you have pointers.
Okay, thanks.
Maybe one last question. If you had this continual learning in your very last slide, very last item, what do you exactly mean?
Yeah,
I mean, more support for continual learning, or using continual learning to make the compilers?
Yeah, make the compilers better. So you always compile programs. As you compile programs, you kind of learn from what you did. Maybe you compile several variants, and you use that as a feedback continuously to improve your instruction scheduling, for example, or your sharding.
Okay. Thank you very much.
Thank you.
And I guess we are now up for coffee, right? We are now up for coffee.
What do you want? That's interesting. Okay, hang on. So, see, I don't know why I was about to write the code. I was about to write the code and I knew what I wanted to write, but now I'm sitting here seeing if this somehow had come up with something better than the person who's been writing Haskell for 5 years. I don't, why am I doing that? Why am I giving it the time of day? No, this is not what I want. Okay.
Maybe one way to say it, right, is I have a picture in mind, and that picture ranges from syntactic or textual features, like a literal shape in words, to semantic, about like the kind of methods that are being invoked, the order in which they should be invoked, and so on. And when I see a suggestion, the closer that suggestion is to the mental image I have in my head, Maybe one way to say it, right, is I have a picture in mind, and that picture ranges from syntactic or textual features. Maybe one way to say it, right, is I have a picture in mind, and that picture to semantic about like the kind of methods syntactic or textual features, like a literal. And when I see a suggestion, the closer that suggestion is to the mental image about like the kind of methods that are being invoked, the more likely I am to be invoked, and so on. And when I see a suggestion, the closer that suggestion is to the mental image I hold in my head, the more likely I am to trust it. Maybe one way to say it, right, is I have a picture in mind, and that picture ranges from syntactic or textual features. Maybe one way to say like it, right, is I have a picture in mind, and that picture to semantic about like the kind of methods syntactic or textual features, like a literal. And when I see a suggestion, the closer that suggestion is to the mental image about like the kind of methods that are being invoked, the order which they should be invoked, and so on. And when I see a suggestion, the closer that suggestion is to the mental image I hold in my head, the more
this is for questions.
I will pick it up.
All right. Does it, yes. All right, so welcome everybody. This is the first session of Uppsala. We have a very exciting program. We start with an award winning paper. So the first talk is by Michael James. He is talking about grounded copilot, how programmers use code generating models. Stage is yours.
Thank you. Hi everyone, I'm Michael. I'm excited to tell you about some work that my co-author Shraddha and I have done. So we are entering a new era of programming with tools like GitHub Copilot, Meta's Llama, and AWS Code Whisperer going to change the way that people program. If you're unfamiliar with these tools, something like Copilot offers quick completion of a program given just a prompt, any kind of prompt, be that a comment, a function definition, and it can complete the function or end of line for you. But as these tools are gaining popularity, there are important questions that we should ask about these tools to make them better. How do programmers use them? How do programmers tend to express intent? And what do programmers use them for? To answer these questions, in our paper, we studied and interviewed 20 programmers as they used Copilot. We identified patterns in the behaviors that they had as they used this tool, and we created a theory of those patterns. In short, our theory is essentially of programming fast and slow. Programmers are either in a mode that we call acceleration, which is kind of like a supercharged autocomplete, or they're in a mode called exploration, which is like a Stack Overflow ++. In this talk, I'm going to tell you about the method that we use to arrive at this theory. I'm going to give you more detail about our two modes, acceleration and exploration. We'll compare and contrast them. And I'm going to offer recommendations for future tools and other research questions to answer as a result of this work. So over the course of our study, our participants completed up to four tasks, ranging from working in an existing code base to working from fresh code. We had a range of different challenges, from implementing business logic in a chat API to a networking task that few of our participants knew how to use, including using a custom crypto API that we knew Copilot would have no clue how to use. We had participants work across 2 different languages in one task, and another was a programming competition task that was easy to test. Among our 20 participants, we had about 15 from academia, 5 in industry, ranging in their language proficiency for their languages of choice, occasional, regular, professional users, and about half of them had used Copilot before. Now, how do you generate a theory from watching programmers use Copilot? To do this, we started with a broad question and 2 tasks. We had our participants perform these programming tasks. We interviewed them about their experience, and we recorded these videos. We recorded their sessions. We annotated those videos with tags that we created about what they did, how they got a suggestion from Copilot, what they got from Copilot, and then what they did with that suggestion from Copilot. We identified common things to find patterns, and we began to find a work-in-progress theory. we continued this cycle of developing new tasks to challenge untested parts of our theory, continued to annotate videos, and rework our theory as new data came in. We kept doing this cycle until we reached, in the grounded theory parlance, what's called theoretical saturation. That is, at the end of our 20th participant, no new data surprised us. And at this point, we could say that we had found a theory of acceleration and exploration. Acceleration, in brief, essentially is the programmer driving. It's kind of an autocomplete ++. The programmer has a plan, and Copilot helps them execute faster. Really, the programmer feels in the zone. I've got a little video that is emblematic of acceleration.
Oh no, this is values. Username equals text. Oh no, this is values. Send. Oh, there you go. Username already taken. Username equals text. Then, oh, there you go. Username already taken.
Okay, so this participant had a clear idea of what they wanted to write, and Copilot just completed the line and put the return for them. There was no thought about whether it was right or wrong. It was exactly what this participant meant to write. So they just accepted it and were able to continue on. On the other hand, exploration is more about Copilot driving the coding session. Participants tended to treat it like a Stack Overflow ++. Commonly, when the programmer is lost, Copilot could suggest solutions to help them get started. I've got another video here, another emblematic video.
Where I say,
this participant had no clue how to start this task, and they just they knew where to start, but not how to get going. And they left it up to Copilot.
Wow, actually, look at that. Try, sure. Wow. I wonder if this is from
not handshake, I like
the
that.
solution or something.
Okay, this seems potentially wrong, but I'll keep. Okay, not handshake, I like that. Sure. Okay. Great. This seems potentially wrong, but I'll keep. Wow, I'm such a good coder. Sure. Great. Wow, I'm such a good coder.
For this participant, Copilot helped them get started on the task and provided jumping off points to complete the rest of this chat server task. All right, so that was the two modes on a high level, but now I want to compare and contrast 4 different features of them. There are more in the paper, and I encourage you to check it out. So we're going to talk about the conditions that lead to participants entering each of these modes, how they prompt the model in these 2 different modes, what their edit tolerance is like for suggestions from the model, and how they validate that the suggestion meets their intent. In acceleration, if the programmer is able to break down the task, then we saw that they were much more likely to be in acceleration. They had a better idea of what they wanted for each subcomponent, and Copilot could offer a completion. Meanwhile, in exploration, particularly when faced with unfamiliar APIs or unexpected behavior, the programmer wasn't sure how to proceed, and Copilot offered a great place to get started. So acceleration is great for small tasks, exploration when programmers are faced with uncertainty. For their prompting behavior, in acceleration, the prompting was largely unintentional. They had simply paused while they were typing, committing thought to code. Copilot saw that as an opportunity to present an end-of-line completion, and the participant could quickly see whether that matched what they intended to write, accept it, and move on. This was not the case with exploration. We saw programmers spend much more time writing comments, and they were willing to rewrite comments in exploration to elicit better responses from Copilot. Copilot would then often suggest multiple lines for these participants. So in acceleration, the prompting is often unintentional, whereas in exploration, they're comment-driven. Now, when Copilot gives many responses or multiple lines, we often saw participants in exploration mode cherry pick parts of those snippets. They were willing to work with incomplete or incorrect suggestions because it still offered a good place to get started. Whereas in acceleration, participants really wanted a small edit distance from their expected piece of code. All right, so they were unwilling to edit in acceleration, and they wanted to cherry pick in exploration. Now, how did they check whether things actually match their expectation? In acceleration, we had this one participant put it really well for the specific things that they were looking for when deciding to consider a suggestion.
Maybe one way to say it, right, is I have a picture in mind, and that picture ranges from syntactic or textual features. Maybe one way to say it, right, is I have a picture in mind, and that picture ranges semantic about like the kind of methods syntactic that are being invoked, the order which they should be invoked, and so on. Like a literal and when I see a suggestion, the closer that suggestion is semantic about like the kind of methods that are being invoked, the more likely I am invoked, and so on. And when I see a suggestion, the closer that suggestion is to the mental image I hold in my head, the more likely I am to trust it.
So in acceleration, participants used a sort of mental pattern matching on the suggestions that they got from Copilot to decide whether to accept it and move on. That pattern matching was often on the shape of the code, the literal shape of the code, the set of method calls that were used, or what they perceived to be their own edit distance from a correct solution. Meanwhile, in exploration, we saw participants review the code carefully. When they got multiple suggestions from Copilot, they would use the frequency of how often, say, plt.hist appears to determine whether that was a valid suggestion or just a hallucination of the LLM. They would use frequency to gauge confidence of the model. They would run the code, and they would also check external documentation to double check the model's suggestions. All right, so we've compared and contrasted acceleration and exploration. We also ran a little bit of a small quantitative analysis of our results. We took the annotations and we analyzed them. And there are two interesting findings that I want to share with you. There are more in the paper. So we noticed that experts explored the least. They already had a good idea of the APIs that they needed to use or how to get started on a task, so they could spend much more time accelerating through their task. We also noticed that those who were new to using Copilot tended to explore a lot more. Those who had used Copilot before mentioned that they had reduced their trust in the model and they weren't willing to explore as much. Now, I have some recommendations for future tools and future research questions that we as a community could look into. In acceleration, we noticed participants often had this tension between reading a suggestion, the end-of-line completion, or just ignoring it and writing their own code. Oftentimes, participants were pretty good at maintaining a good balance, but sometimes it would go terribly wrong. Participants reported feeling sucked into reading a suggestion. They felt like, well, Copilot offered me this code. I should check that it was right. So I have a participant. I'm going to show you a video of a participant who was working on a programming competition task in Haskell, importantly.
What do you want? What do you want? That's interesting. Okay, hang on. So, see, I don't know why I was about to write the code. I was about to write the code and I knew what I wanted to write, but now I'm sitting here seeing. See, I don't know why I was about to write the code. Come up with something better than the person who's been writing Haskell what I wanted to write. I don't. But now I'm sitting here seeing if this somehow had come up with something better than the person who's been writing Haskell for 5 years. I don't. Why am I doing that? No, this is not what I want. Okay. Giving it the time of day. No, this is not what I want. Okay.
That Haskell code that Copilot suggested was so dense for this participant, but since it was just a one-line completion, he felt sucked into reading it and considering it. So we noticed that unexpected and complex suggestions tended to break our participants' sense of flow. So if a model could be more aware of the mode that a programmer is in, that is, if they're experiencing the effects of acceleration, then a model should be significantly more confident in the suggestion it provides, whereas if they're going slower, a participant might be more willing to look at longer pieces of code. There's also useful work to do in helping programmers validate suggestions. Like, could that Haskell code have been right? Maybe some small part of it could have been. By presenting intermediate values or intermediate types, we might help our users better and more quickly evaluate whether a suggestion fits their intent. We noticed that our subjects had trouble distinguishing suggestions. They would get multiple suggestions from Copilot, and then they would be left wondering, well, I know these are all textually distinct, but how are they really different? And participants would spend extra time considering the difference, playing spot the difference between many different suggestions. So there are some interesting research questions to help distinguish suggestions. In this space, particularly with novices who are trying to explore for the right approach to a problem, might be asking kinds of questions that the model could definitely help with. Like, what are different ways to solve this task? What are common API calls? And what are the edge cases to consider when implementing an algorithm? All right, so I've told you about how we arrived at our theory. I've told you about our theory of acceleration and exploration. And I've presented some recommendations for future tools and future research questions. I want to thank my co-authors, Shraddha Bark and Nadi Polerkapova. I want to thank my participants and you for coming to my talk. Thanks.
So we have time for one or two quick questions. Any question from the audience?
Really great talk, really great stuff. On your slide where you've got the two graphs where you correlated like professional versus not and versus previously using Copilot or not, was there a correlation between if professionals had used Copilot more than non-professionals? I was just wondering if there were...
We did not run that analysis, so I don't have anything to say on that.
Okay, thanks.
Any other questions?
Thanks for the talk. I'm using Copilot with Rust, and something that have been bugging me is that it's hallucinating in non-obvious way. Sometimes, you write something, and in acceleration mode, it looks like it's right because it has the right shape, but it uses a method that doesn't exist. And it's frustrating because if I were to write this code, I wouldn't do that because I use the LSP and I have autocomplete. And I wonder if you saw that as well, and if you have ideas about, I don't know, like making the agent talk with the LSP incrementally before showing the results, or some other external feedback loop before presenting it to the program.
What a wonderful suggestion. That sounds like a great opportunity to help, like one way to help validate the code that Copilot provides, to highlight, to say, well, I have an idea you could write it this way, but red squiggle, like this phantom text won't compile as is. Future work.
All right, so we need to move on to the next talk. Misha will be around to answer other questions after the talk, and thanks him again. So the next talk is by Alex. He's at MIT, and he's talking about complexity-guided data sampling for training neural surrogates of programs.
All right, everyone hear me? Okay, make sure my clicker does not seem to be working. All right, whatever. So, hi everyone, I'm Alex. I'm going to be talking about our paper, Churiko, Complexity-Guided Data Sampling for Training Neural Surrogates of Programs. This is co-authored with Yi Ding and my advisor, Mike Carbon. Let me start by defining a surrogate of a program. So a surrogate is a model of the behavior of a given program. And this is typically something like a neural network, which you train such that for any given program input, it predicts what the program would produce as output for that input. People like surrogates because surrogates can help to improve the speed and the accuracy of programs. And I can ground this in some examples from the literature. So in some prior work, Ismail-Zadeh and co-authors trained surrogates of numerical programs to speed up these programs at the cost of a little bit of approximation error. And by training these surrogates to mimic the program and deploying them in their place, they were able to find surrogates that were about 2 to 3 times faster than the original programs. Kutzkowski and co-authors trained surrogates of physics simulations and then fine-tuned these neural network-based surrogates on some data from the expected actual behavior of the process that the simulation was modeling to increase the accuracy of the surrogate relative to the simulation. And by doing this, they were able to find surrogates that were about 2 to 3 times more accurate than the original simulation. And in some of our prior work, we trained surrogates of CPU simulators and then exploited the fact that these neural network-based surrogates are themselves differentiable to optimize simulation parameters of the original simulation against the surrogate, ultimately finding simulation parameters that actually increase the accuracy of the original simulation relative to expert set parameters or values for those parameters. So as you can see, there's a wide range of applications of surrogates of programs, and each with potentially substantial benefits. And the first step of each of these different design patterns involves actually training a surrogate, a neural network-based surrogate, to mimic the behavior of a given program. And this raises the natural question, what is the methodology for doing this to get the best accuracy surrogate if you know the source code of the original program? And in this work, we focus on one particular aspect of this question, which is what data distribution should you use to train a neural network-based surrogate of some given program? So I will make this more concrete with a case study from our paper. And so specifically, this case study is going to be of a 3D renderer program, such as from a video game engine, that will generate this scene here. And we're going to be looking at creating a surrogate of one particular tiny sub-program of this overall renderer, which is going to be this luminance shader here. So this is a shader program that, a shader that is essentially executed for each different point in the input scene, thousands of times to generate each frame of the render that I was just showing. And so it takes 2 inputs. It takes the sun position, which is the Y position of the sun in the sky, ranging from -1 at night to +1 during the day, and the emission properties of the material at that point in the scene, whether it's absorbing light or reflecting light. And then as output, this predicts the luminance of that point, which is the amount of light reflected from that. So if you look at this program, you might notice that this program essentially divides up the input space into 3 logical regions, and then applies a different function to each of these different regions of the input space. So there is the nighttime path when the sun position is less than 0, and this ends up computing this relatively simple linear function of the input variables. There is the twilight path when the sun position is between 0 and 0.1, which computes a maybe slightly more complicated but still ultimately linear function of these input variables. And then there's the daytime path, when the sun position is greater than 0.1, which computes this much more complex, actually quadratic function of these input variables. And this leads me to the key insight of our work, which is essentially that when we're training surrogates of programs and we're trying to reason about how much data to sample from each different region of the program, we should be using the sample complexity of the function applied by the program to these different regions to guide how much data we are sampling from the program. And so for anyone not familiar with the term, sample complexity is essentially the number of samples that are required to learn a surrogate of a given function to some target error. So essentially, the higher the sample complexity, the more samples you need to learn a reasonable surrogate. And we can empirically look at the sample complexity of each of these different program paths. So I have a plot here of basically training a surrogate of each of these different paths in isolation and looking at the error as a function of the amount of data used to train that surrogate. So in this plot, error is on the y-axis, the data set size to train a surrogate is on the x-axis, and each different line is a surrogate of each of these different paths. And so you can see, essentially, the empirical sample complexity results match the intuition that I was trying to lay out earlier about the complexity of each of these different paths, right? So for a given number of data set samples, the nighttime path, which is the simplest linear function, has the lowest error, whereas the daytime path, which is a more complex quadratic function, has the highest error. And so essentially, we can use this notion of the complexity of each of these paths to help us determine how much data we want to sample overall from each of these different regions in the input space to guide, to train our surrogate of our program. And so we want to compute these sampling ratios. And this will have 2 different ingredients in the recipe. The first is the complexity, which was I was just laying out earlier, right? The nighttime path has the lowest complexity. I'll quantify this in a little bit. And the daytime path has the highest complexity. The other ingredient here, of course, is going to be the frequency of each of these different regions in a workload of interest. And so if we assume that the sun position is uniform from -1 to 1, then we get that the nighttime path is induced by about half of the inputs. The twilight path, which is relatively rare, is induced by 10%, and the daytime path by 40%. And so this can guide some really high-level reasoning about how much data we might want to sample from each of these paths, right? Because the nighttime path is by far the easiest of the simplest of these, has the lowest complexity, we should probably be sampling less than its frequency to train a surrogate. Whereas because the daytime path has the highest complexity, we should probably be oversampling it relative to its frequency. And this leads me to the second key inside of this paper, which is that when we are training surrogates of programs, we actually have access to the source code, the semantics. We know the exact function that we are trying to train a surrogate of. And so we can use tools from machine learning theory to actually exactly compute the sample complexity of the function, each of these different functions, and then use that to determine exactly how much data we actually should be sampling from each different region of the input space. And so using an approach that I will describe in just a minute, we can essentially compute that the sample complexity of the daytime path is actually 3.7 times that of the nighttime path, so it's significantly more complex to learn a surrogate of. And then using another approach I'll talk about in a minute, we can then compute these actual sampling ratios concretely. So we can get that we want to sample roughly 40% of our data from this nighttime path, so undersampling relative to the 50% frequency, and 46% from the daytime path, oversampling relative to its frequency. So how well does this approach work? I have another one of these plots with the dataset budget on the x-axis and the error on the y-axis, comparing training a surrogate of this program according to just the frequency distribution in green and the complexity-guided sampling ratios in orange. And so this is a log-log plot. It's actually a little bit hard to see exactly the gap between this, but on this range of dataset sizes evaluated here, you get about a 15% improvement in error by training according to these complexity-guided sampling ratios compared to just training according to these frequencies alone. So this is a pretty significant improvement in error in this example. So we have two core contributions in our paper. The first is this high-level approach to allocating samples to different regions of a function's input space to train the highest accuracy surrogate, based on each region's relative frequency and complexity. And this approach essentially follows the intuition I was just laying out. Regions that are more frequent, we want to sample more. Regions that are more complex, that are harder to learn, we also want to sample more. And our second contribution is Turrico, which is a programming language in which we can actually compute the complexity of the function applied by a program to each different region of its input space. And so together, these two contributions allow us to reason about the data distribution to use to train the highest accuracy surrogate of some given Turrico program. So I've laid out a lot of the intuition. Let me lay out some of the actual formal foundations behind our approach. So the core modeling assumption that we have to make is that the programs under study denote these stratified functions. These are piecewise functions. Essentially, we assume that the program applies a different function to each different region of the input space. And to learn a surrogate of such a stratified function, we learn a stratified surrogate, which is itself a piecewise surrogate. So we learn each surrogate of each different function stratum independently. And then at evaluation time for one of these stratified surrogates, we essentially determine what input or what region of the input space a given program input lies in, and then apply the corresponding surrogate. To train the best surrogate of a given function, we have to actually be able to reason about the error of a surrogate of a given function as a function of its complexity and the amount of data available. And as I mentioned earlier, to do this, we use this notion of a sample complexity measure, zeta of f. And so, as I said earlier, the error of a surrogate of f at a given number of samples is proportional to zeta of f. So the higher this complexity is, the more data you need to learn a surrogate. What are these sample complexity measures? I've used them sort of informally, but I haven't actually talked about concretely what they are. We can actually take advantage of some recent work from the theoretical machine learning community to compute these sample complexity measures for certain classes of functions. So we can actually know exactly, or an upper bound at least, on the amount of data for a certain class of functions to train a neural network to mimic that. And so the core assumption that these approaches from the theoretical machine learning community, which we actually inherit in this work, is that the functions under study are themselves analytic, which means that essentially that they have this type of power series representation. To compute this zeta of f for an analytic function, we have first, as a utility, define the tilde of a given function. And so this is essentially the power series representation of this function with all coefficients taken the absolute value of. And so essentially, you can think of this tilde as a way of measuring the influence of the sort of hard to model for a neural network, higher order terms of this power series. Then these results from the theoretical machine learning community actually tell us that zeta of f, the complexity of f, is equal to the derivative of the tilde evaluated at 1 squared. And so there's a lot of assumptions baked into this about the neural network architecture and data, but essentially this is the sample complexity for an analytic function. And so just to plug this back into the definition of sample complexity, concretely, the error of a surrogate, epsilon, is upper bounded by the square root of zeta of f over n. So the higher the complexity is, the higher the error is. The more samples you have, the lower the error is. So just to sort of formally state, or a little bit more formally state, our optimization problem here, we assume we are given a stratified analytic function. We assume we are given a data distribution that describes the frequency of each different region of the input space in a test workload of interest. And we assume we're given an overall sample budget. And our goal is to find the allocation of the sample budget to different strata to minimize the overall error of the stratified surrogate against our original function. And we do formalize this in the paper. I'm not going to have time to go into this formalization, but as I've laid out, essentially the intuition is that we want to sample proportionally to the frequency of each different region and the complexity of each different region. Okay, so how do we actually compute these complexities for programs? So to do this, we introduced a programming language and associated analysis, Turico. And so in Turico, all programs are stratified analytic functions. So it's this imp-like programming language that looks essentially something like this. And so our goal in our Turico analysis is going to be to compute zeta of f, this complexity measure for each different region of the input space, or the function applied to each different region of the input space. And our analysis has two components. The first one, which is sort of the interesting novel bit, is this non-standard interpretation to calculate the tilde of f. And so I'll quickly walk you through how this analysis, this interpretation works. So I've duplicated the definition of the tilde of f here. So it's the power series representation with all coefficients taken the absolute value of. So let's say that we have a program that computes just something simple like f of x equals sine of x. We can write out its power series representation like this. And then so if we want to compute the tilde of f, we want to write out this power series representation with all coefficients taken the absolute value of, which is equal to sinh of x. So essentially the tilde of f of x and sine of x is just sinh of x. And this is essentially how this analysis operates. We are able to replace each different operation with the language with the tilde version of the operation. And then the actual analysis of the tilde itself is compositional in these operators. So we just do this sort of non-standard analysis to compute the overall tilde. We combine this with a standard forward mode AD pass to compute the derivative of the tilde. And then by evaluating this at 1, we're able to then have this automated approach for actually computing the complexity of a given program. So we have this zeta of f for a program in Turico. Let me walk you through a little bit of the evaluation of how we evaluated how well these complexity-guided sampling ratios work. So I talked a little bit about this example of a luminance shader from earlier, in which we got about a 15% improvement in error relative to some baseline distributions. We evaluate this on a range of other programs and get an average of about a 5% improvement in accuracy of this complexity-guided sampling ratio relative to baseline approaches. And so 5% probably doesn't sound like a lot to people in this room, but I want to talk you through what this means in the machine learning context, because a 5% improvement in error can actually make a real difference in sort of upstream or downstream applications. So in some prior work, we were developing a surrogate of a program to try to have the fastest possible approximation of this program that had no more than a 10% additional error compared to the original program. And to do this, we performed this hyperparameter search on the size of the neural network. And so we ended up selecting a neural network width of 64, which had about a 57 or 1.57 times speed up compared to our original program. With a 5% reduction in error, though, we're then able to actually redo this hyperparameter search and select a significantly smaller neural network architecture with about half the width, which has an additional about 28% speed up. So a 5% reduction in error actually can lead to significant improvements in the downstream performance of the application. I also want to very briefly touch on some sort of qualitative analysis of these results. So I talked about the renderer program that we evaluated earlier. And so we ended up training a surrogate of a much larger component of this program than just this sort of simple luminance shader, and evaluated our complexity-guided, our surrogate trained according to these complexity-guided sampling distributions to several baselines. And so on the left here is going to be the original sort of ground truth render. Then the three other figures are the renders generated by a couple of different surrogates. On the left is the complexity-guided one, which is the closest to the ground truth. In the middle is a render from a surrogate trained on just the frequency of these distributions of paths. So it's also quite similar to the ground truth. A little bit hard to see it in this projector, but the nighttime is significantly more purple than the original ground truth is. You can see that sort of on the roof of the building. And then the rightmost is a surrogate trained according to just a sort of uniform sampling distribution across paths, which you can see is nowhere near the actual ground truth render. Just to very briefly recap, surrogate to programs are this emerging design pattern, an emerging programming technique that allow us to improve the speed and the accuracy of programs by replacing them with surrogate models of their behavior. And when we're training surrogate to programs, this is sort of this interesting machine learning task where we actually have access to the source code, the semantics of the program. We know exactly the function that we're trying to train a surrogate of. And we argue essentially that we should be able to use this knowledge and combine this with our both theoretical and our empirical knowledge of machine learning to be able to train the best possible accuracy surrogates of programs, or broadly the best for our downstream application, based on some analysis of facts derived from the original program. So thanks, everyone, and I'm happy to take any questions now.
Right, so we have time for one very quick question.
Hi, thanks. Wonderful talk. I think lots of interesting ideas.
Thanks.
Quick one, how do you deal with programs that have loops? So the analytical functions would be infinitely many in the representation.
Yeah, so our approach supports bounded loops, and essentially what this will look like is that you have many, 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 many different strata. And so it realistically does not scale super well to that, because we assume that currently we train essentially a different surrogate for each stratum.
Another question. This was a very quick one. Thank you for that.
Hi, thank you for the great talk. So I was wondering, you compute based on the sample complexity, how many samples or a ratio of samples that you need to take. Is there any instance where you don't even have the necessary samples in your training data set to match that, and you can't actually learn a surrogate program? Because you have a finite data set, and some of these functions could be quite complex.
Yeah, so ultimately our approach gives essentially the best allocation of samples that you can given your sample budget. And so if your sample budget is not large enough, I mean, you will learn a surrogate. It will probably be terrible. But yeah, so there's never a case where it won't learn anything. It'll try to learn the best given the sample budget. But if it's small, there may be issues. And especially you can run into issues where the approach, essentially you have to round to integer numbers of samples and things like that, right? And so you can end up with kind of these weird edge cases in the really, really small data regime.
All right, let's thank Alec again. And
thank you.
So Vivek from Georgia Tech will give the next talk, and he's going to talk about concrete type inference for code optimization using machine learning with SMT solving.
I think we're good. Yep.
Stage is yours.
Okay. Thank you. Yeah, it's a pleasure to present this work from our group. And it's unfortunate that the lead PhD student, Funker, could not be here. So let's step back and look at the broad space of application developers. And what we see in today's era, especially as we approach the end of Moore's Law, is that carrying a lot of the burden are ninja programmers who are hardware experts. And they code in C, in CUDA, in assembly, hardware intrinsics for all the new kind of accelerators coming out. And above them, we have experts in developing libraries and frameworks who might code in C++, Rust, SYCL, and so on. And then we have a vast number of domain experts who write in languages like Python, MATLAB, JavaScript. And what we've seen over the last decade is that Python has emerged as a dominant programming model for domain experts. And here are a number of frameworks that you might recognize that are all Python-based. Machine learning frameworks, NumPy, SciPy, Pandas, and so on. So let's look a bit at the needs of the domain experts from the perspective of both productivity and performance. So productivity is an absolute must for them. They're not down there at the Ninja level or even at the library framework developer level. They benefit a lot from Python's dynamic typing, interactive programming, the fact that you have many high-level aggregate operations, rich libraries, and also the fact, quite frankly, that over the last couple of decades, Python is the introductory language offered in most CS1 classes. So they've got productivity, but they want performance without compromising productivity. They can get performance from high-performance libraries, but that's only if the computation they want to perform matches an existing library. If they have some code that does not match a library, then they are reliant on optimizing compilers. There are JIT compilers for Python, and there are also some ahead-of-time compilers. So the focus of this paper is really to start with on ahead-of-time compilation, and certainly in this case, you need concrete types to deliver performance. And to give you a feeling for what the concrete types might look like in a couple of cases, suppose you have a sample Python function, f of x, y, x comma y, x and y are two parameters. It has an operation like x plus equals y. In our the research compiler that was developed in our group called Intrepid, that was presented 3 years ago in Onward 2020, you could specify types using type hints. And as shown over here, f1 is a variant of the function where x is a one-dimensional array of int32 and y is a one-dimensional array of int32. f2 is another variant where x is a two-dimensional array of int64 and y is a 1D array of int64. And that's also conformable with x plus equals y. And in the number AOT module, you can use decorators as shown over here. And I don't have time to get into it, but past work has shown that if these types are provided, you can get very significant performance improvements. At the very end, I'll give you some indication of what that looks like for some benchmarks. But keep in mind that code optimizations for these languages can do a redundancy elimination wholesale on large aggregate operations. So there's a lot more benefit from code optimization than might occur from LLVM-IR, for example. OK, so our goal is to somehow add concrete types so that we can help the domain experts obtain the performance they need. So how do we do this? Well, one is we can ask the programmers to provide it, but that's counter to our productivity goals. There has been past work in our community on using machine learning. And there are some limitations. Actually, frankly, we were looking for existing solutions to just move forward on our optimization research. And what we found is if we directly use some of the past work on machine learning, we get reasonable accuracy on a per variable prediction, but we get combinations that are inconsistent. And then there was also past work on combining ML with rules-based analysis. In our opinion, that was more focused on software engineering than code optimization, and often provided like a single type, which might be an abstract type with like any or something like that, which is not amenable to the concrete types needed for code optimization. There's been past work on solvers, particularly SMT solvers and other constraint solvers. The good thing about this work is that all the combinations they predict will be type consistent, will type check, but if you encoded the constraints correctly. But there can be a large number of these type combinations, and the SMT solver has no clue as to which combinations are more likely. So our approach is to explore how both of these can be combined. So we want to statically generate a manageable set of type assignments that are both likely and concrete type assignments that are both likely and consistent for some regions of code in a Python program. We'll focus on functions, but this could apply to any code region. And we are fine with getting multiple concrete type assignments because we know how to do this in the PL community. We can generate multiple versions and dispatch to the appropriate version at runtime. So to give you a feel for the ML models, we actually evaluated 4 in the paper just to get a sense to what extent the model had an impact on accuracy and overall results. So these are some of the results just for predicting the type of a single variable. And you can see 4 models. The first is more a statistical model, just frequency-based. The second and third are extensions from past work. And earlier this year, we had the opportunity to experiment with GPT-4, the API also as a model. And the paper has the details, and we see there's a bigger difference across models. And this is for top 1, top 5, top 10, top 20. When you have a lower K for top K. But overall, GPT-4, which we, of course, did not train, and I should mention the training set used for the other models was different from these benchmarks, did perform the best. OK, so this figure in the paper gives an idea of what you can do on the left side of the figure if you only went with ML type predictions. You do get likely types, which is great. But when you start looking at combinations of type of variables, you may get many invalid combinations for the x plus equals y example. For example, a case where y is a 2D array and x is a 1D array. You can think of it as a minor kind of hallucination, but it comes about by just combining types from different variables. So this is a major issue. All those examples shown in red are examples of types that are predicted but are inconsistent. And in fact, table 4 in the paper looks at it more quantitatively. The number of types in some of the benchmarks can be really huge, 10 to the 10, even as high as 10 to the 65. And only a small fraction of them are consistent. And on top of that, there are cases when there's still zeros, where none of the ML predictions from these large numbers end up matching the ground truth. So that's a challenge if you just use ML. So what if you explore using a type solver, an SMT solver, and in our case, we use CVC5. So the type system at the bottom, which is also in figure 1 of the paper, shows the type space that we're exploring for this work. And there can be constraints. For example, the fact that the key type for a heap data structure needs to be scalar. So you can see some constraints related to that, or conformable ranks for certain operators, and so on. And there's also, to make things tractable, we can put a bound on the rank of an array that we want to consider. Here we're showing constraints where the array rank is less than or equal to 3. Of course, it could be replaced by some other constant. And also some constraints that allow for enforcing uniform bit widths in certain operations. And the table shows that if we just let the SMT solver predict the plausible types, we will get a large number. That's a TC column. But if we add the finite type space constraints, we reduce it a bit. And if we add uniform bit width, we still reduce the space. But there's still some cases where it's very large. So this was the right-hand side of this figure, where the nice thing is all the predictions are type consistent, but there's a large number of them, and we don't know which ones are going to be more likely. So the first attempt at trying to combine the two was saying, OK, let's take the type predictions, the top K predictions from ML, and add them as constraints in the SMT solver. If you have top 5 for a variable, you have 5 types. Add to the SMT solver that the type of the variable could be the first type, second type, or the second type, or the third type, and so on. That's a good start, but what we found is that it was too much of a hard constraint. In some cases, it would still miss one type in the ground truth, and then the Cartesian product would mean that you have 0 type combinations that match. Or in some cases, there would still be too many solutions. And the issue over here is when you look at top K, you want to simultaneously consider multiple K values for different variables. So now the paper has the detail on a scoring function that we use. And the idea over here is if you have two predictions, for example, one where variable x is in the top 1, variable y is in the top 1, and variable z is in the top 10, we give it a score depending on how often it appears in top 1, 5, 10, or 20. And if in case 2, a type prediction, x is in top 1, you have a top 1 type prediction. For y, you have a top 5. For z, you have a top 5. You add it up, and then you do a lexicographic comparison that prefers more occurrences in top 1 than in top 5 and top 10. And then what you do is you essentially add to the SMT solver a constraint that the score should be greater than equal to a threshold. And this is a softer constraint. It can even accommodate some types that were ignored or not predicted by the ML system. So with the refined approach, and there are a lot of details in the paper, with the refined approach, we find that we are down to a manageable number of types. And in the GPT-4 case, we can see that the numbers vary from the variance from 2 to 186. And it turns out that 186 is totally manageable. The results will show you actually generated 186 version. For one benchmark, IPNSW, we did not happen to get a type that was in the ground truth. So we're going to fall back to the default Python version in that case. Which brings me to the performance results that are in the paper. What we see over here is that there are 10 benchmarks, one for each row. There are columns per ML model, and within that, there's a performance improvement relative to the original Python code when our types are fed into the number AOT model, or when they were fed to our Intrepid C++ code generator. The geometric mean at the bottom shows that as a geometric mean, the improvements range from 16x to 60x. But there were many individual cases where this performance improvement due to code optimization was many hundreds, and in one case, even more than 4,000. So to summarize, we introduced an approach for concrete type inference that enables code optimization for dynamically typed languages without requiring any input from the domain experts. We combine machine learning and SMT in a way that can work effectively, these soft constraints that have this notion of a progressive constraint relaxation, and get a manageable number of predicted types. And we've shown significant performance improvements by using these types. And in fact, looking ahead, we think there's an exciting opportunity to explore these combinations of machine learning and SMT. And certainly that's what we plan to do more of at Georgia Tech. My good friend, we are lucky that my good friend Vijay Ganesh, who's an expert in solvers, moved to Georgia Tech recently. And if anyone here is interested in doing a PhD or a postdoc or a faculty position in this general area, please feel free to get in touch with me. Thank you.
All right, is there any question? Please.
Thank you for the great talk. I have one question. Does the type annotations will affect the functional correctness of the produced programs?
So the question is, so the type annotations, I didn't get into the details of the multi-version code generation, but this is a classic technique in PL. So we'll generate all these versions for different types. At runtime, we will dispatch. And so the type, each code is a specialized version of the original function for those concrete types. So it should not change the correctness because it's a specialized implementation of the original code. I don't know if that was your question, though.
Okay. If you do this runtime dispatch, then that should be fine.
Yeah.
So and about the precision on overall types, did you do experiments to run the experiments on different types? Because, for example, if the integer type int 32 takes 90% of all the types, then the final results may be imbalanced or biased.
Sorry, I didn't. Are you talking about the prediction part or the code generation part?
The prediction part.
So what might be invalid? I didn't get that question.
For example, if the final code, if integer type takes int 32 type takes 90% of all the types in the code, then if I have a model, then I just predict everything as int 32, then my precision would be my accuracy would be 90% just because the imbalanced types in the code. And I think this is very common in practice.
Let's discuss further offline, because the point I was trying to make is you can get good accuracy for predicting a single variable, but it's the type combinations that become challenging. So we can discuss more offline. Yeah.
You can have another quick question.
Thank you, Vivek. Wonderful talk. Could you compare this with, say, profile-guided optimization, where you collect information from one or more runs about what the types actually are that are seen at runtime?
Yeah, thanks, Elliot. So I did not get into the details of some of the training that we did for those two models. And there, the training data set, we actually used the monkey type profiler and collected dynamic types from runs of the program and used that for training. But the results from GPT-4 were quite amazing. And offline, I'm happy to share the prompt and all with any of you that was used to get those predictions. So, yeah.
So we need to move on. I would really encourage you to get in touch with Vivek. Thanks a lot for the talk again.
Thank you.
And the next talk is an explanation method for models of code, and will be presented by you.
Hello, my name is Yuan from Nanjing University. The title of my talk today is an explanation method for models of code. Neural networks has been increasingly applied to programming language tasks and achieved good performance, such as method name prediction, program repair, and program synthesis. Oh, okay. No, yes. However, neural networks mostly operate in a black box manner, making it difficult to get insight into their internal mechanism. It means that the degree to which their prediction can be trusted is unclear. So this lack of transparency has become an impediment to the use of learning-based program analysis tools. Currently, several strands of the work has been proposed to give the explanation for models of code. The two major kinds of work are attribution methods and explainability for models of code. However, these works have several limitations. Attribution methods are well studied in recent decades. These methods assign a relevant score to each input feature with regard to a particular output of a network. Thus, they do not give a clear-cut definition of the critical features that the model uses for prediction. Before illustrating the weakness of explainability for models of code, we give our motivating example first. We use method name prediction task and use sequence GNN model. In this figure, the left subfigure is a Java method. The right is the top 4 predictions that sequence GNN make for this method. In the example, the sequence GNN model predicts the name of the example to be add item. The first work, 7, extracts the code fragment from the original program, requiring that the prediction of the original code is unchanged. It only considers the prediction preserving code. For a motivating example, 7 shows that both log add item and m items add position gene item are the explanations. The second work aims to identify minimal change to the input program so that the model makes a different prediction on the modified program. However, this work relies on external code for explaining models' prediction. To address this limitation, we present our work, which are our insight is, which classifies an entire input into 2 types of features. Which and chaff. Wait is the feature of the program that serves as the reason why the model makes the prediction. Chaff, on the other hand, is the remaining features. Based on this insight, we designed two constraints to quantify the influence of weight. The first one is the model must preserve its prediction when the original input becomes the weight alone. And second, the model must change its prediction when the original input becomes the chaff. We come back to our illustrative example. The weight of the example is the m-latence add, because it preserves the model's prediction when the original input becomes the weight alone. And as shown in the right step figure, the model changes the prediction when the original input becomes the chaff. After this example, we give the definition of weight. The weight that a model M uses for predicting the label of a program P is a set of statements P prime, such that first, P prime is a constituent of P, meaning that the weight must be a part of the input program. Second, P prime is sufficient, meaning that the weight must single-handedly make the model predict the same label as the original program P. Third, P prime is necessary, meaning that removing P prime from the original program P changes the prediction of the model M. Last, P prime is minimal, meaning that removing any token from P prime triggers the violation of sufficient, necessary, or both requirements. Based on the definition, the next question is how to efficiently find weight. A brute force search would be computationally intractable for any non-trivial programs, because with a token-based representation, a program composed of n tokens will yield a search space of 2 to the power of n candidates. Therefore, our solution should be more efficient. We designed our method based on observation, that is, few code edits, albeit preserving the property of interest for input programs, frequently cause models to alert their predictions. Therefore, we hypothesize that models heavily utilize local program features for prediction. Based on this observation, we propose the reduce and mutate method, which is a cost-to-find method for identifying the weight that code models use for prediction. The high-level step of the method are as follows. Give a program P for which a model N predicts a label L. The reduce step tries to reduce P into PR, a statement-level code fragment that satisfies the sufficient and necessary requirements. Based on PR, we mutated it to pinpoint the feature P prime that satisfies the two constraints. Finally, we declare P prime to be the weight. We show our algorithm by our motivating example and this figure. In this figure, the label that the sequence gene predicted at each step is highlighted in the shadow box. In step 1, we flat the input method into a list of statements. We then traverse the subset of all statements in the ascending order of their size, starting with those that contain only one statement. We pick the first statement to check against the sufficient and necessary requirements. As depicted in step 2, sequence gene make a different prediction for this statement. Therefore, the sufficient requirement is not met. So we move on to the other statement. As shown at step 3, statement 2 also does not satisfy the sufficient requirement. We omitted statement 3 for its non-satisfaction of the sufficient requirement either. Next, we arrived at statement 4, m-atoms add position gene atom. We found that this statement satisfies the sufficient requirement at step 4 and the necessary requirement at step 5. We declare statement 4 to be the fragment that contains weight. Concerning the future fragment to be explored are unlikely to contain smaller weight. The reduced step terminates with the output of statement 4. We then use this figure to illustrate the main step of mutate. As shown in step 1 and 2, it turns out that neither removing m-atoms or mutating m-atoms into an out-of-vocabulary token satisfies the sufficient requirement. Similarly, we found that identifying ADD is also essential to sequence gene's prediction that cannot be changed. Next, we turn to the first parameter, position. Since the m-atoms add gene atom satisfies both sufficient and requirement at step 3 and the necessary requirement at step 4, we remove position from the code fragment. Subsequently, we succeed in removing the second parameter gene atom because the m-atoms add also satisfies the sufficient and necessary requirements. Since the code cannot be reduced any further, we conclude m at z is the weight that the sequence GN used for predicting the running example. We report the result of an evaluation of Huoyan, which is the realization of which the model we used are code2vec, sequence GN, GGN, codebird. Regarding the dataset, we use the dataset on which the models are evaluated when they are first proposed. Except for code2vec. For code2vec, we use the same dataset as sequence GN. With them comparing our method with other expandability method, we use integrated gradients, shape, and the attention mechanism to represent the attribution method. We use Sievent and counterfactual explanation to represent the expandability method for code models. We did 5 experiments. We first briefly summarized the result from analyzing the performance of Huoyan, checking whether which has out of distribution issues, and checking whether other expandability method can also find which. Then we introduced the experiment about analyzing the makeup of which and demonstrating the utility of which. Regarding the performance of Huoyan, we found that first, Huoyan is efficient, and second, Huoyan and delta plugin are in the same league. And then, since Huoyan will generate intermediate programs that come from picking statement from the original program or mutating statement in a program, if these intermediate programs do not align with the distribution of the training program, weight may not be accurate because the predictions made by the models on these intermediate programs could be invalid. So in the second experiment, we confirm that which is valid without the auto distribution issues. Finally, we found that none of the baseline expansion methods are good at finding which, and which are present a distinct criteria of the expansion, which is valuable finding itself. Regarding analyzing the makeup of which, we have done 2 experiments. The first one is analyzing the number of tokens which are composed of. In this experiment, we found that Huoyan performed better than delta debugging because it found smaller weight. The second experiment is investigating the substance of weight. That is, we analyze whether the weight we found is lexical, syntactic, or semantic. Lexical means each statement in weight consists of a single identifier. Syntactic means that there is at least one statement in which composed of an expression. Semantic means that the weight has at least one data follow edge. For example, the rightmost subfigure shows that a variable sum SUM has a data follow edge. The result shows that for all evaluated models, the weight mainly consists of lexical properties. The last experiment is a user study, which is used to assess whether or not Huoyan's explanation can help end users recognize defective models with data contamination bugs. We focus on 2 kinds of data contamination bugs. The first one is mislabeled example. It means that the models are being trained on partially mislabeled data. And the second one is spurious artifacts. It means the training data display bogus correlation with labels that models may learn. Let's take a dog clarification task as an example. The spurious artifact occurs when, for any picture of a husky, the background happens to be snowy. In this scenario, models might mistakenly connect the snowy background with the husky, creating an incorrect correlation. Then we use a figure to illustrate the user task. At the first step of the study, users assess the model based on its prediction for the 10 programs. In particular, they rate how likely they think the model is buggy. For example, likely buggy, neutral, or unlikely buggy. This step is important because if the user can accurately recognize defective models with their prediction only, then no explanation method is necessary. Next, we randomly choose an explanation method out of which and the baseline to generate explanations for each prediction the model makes for the 10 programs. Based on the explanation, users give their ratings of the model again. Last, we have users repeat this evaluation procedure for the same bugging model, but this time we use the other explanation method and a different set of 10 programs. Note that this information is not conveyed to users. after the user study, we found that which is helpful for users to identify defective models caused by data contamination bugs. To conclude, in this work, we present an explanation method for models of code. Based on our evaluation, we found that our reduced and mutated step is efficient and effective in finding weight. Then, we found weight do not have OOD issues, and our reduced and mutated step is useful and valuable in finding weight. Finally, Weich's explanation is helpful in identifying defective models. Thank you for your attention. I'm ready to take questions.
All right, is there any question? Please.
Hey, thank you for your talk. Jürgen Sito, by the way. I wasn't quite clear on one part of your talk where you said you replaced one of the tokens in the, I think, reduced step with an out-of-distribution token. So I was wondering what the rationale behind that is.
I think it's this
Oh,
one.
yeah, here, exactly, yeah.
Yes, because we think it is possible that the models may take the structure of an statement into account. For example, in this statement, it's a method invocation. So if we directly remove m items, then it's a different kind of method invocation, such as function call. So we may think it is possible for models to consider the structure of an statement. So we will first try to remove this remove one token. If the token cannot be removed, we will try to mutate it into an out-of-vocabulary token. So this is the rationale.
But even in this step, you're running prediction, right? So you do the mutation, you run prediction to see whether it changed, right?
Yes, we will try to remove it and see the prediction. Then, if it doesn't work, we will try to mutate it into an OOV token, and we will check as a prediction again.
Okay, and I didn't quite get the rationale here. So if you insert an out-of-vocabulary token, the hypothesis is that the model would look at the structure more deeply?
Yes.
Okay, all right. Thank you.
Thank you.
Is there any other question? Yeah, please.
Hey, thanks for the talk. I have a basic question. You do this research. How do you know that any of the hypotheses that you're assuming are actually true? Why? Yeah, I mean, we can believe it from looking at the sort of final result, but how do we know that you're looking at the structure of the program? And I mean, how do we know that the model is looking at the structure of the program and guessing from
you
it?
mean the structure of a program? And this is because we look at the internal mechanism of some models. For example, some models may consider the data flow edges between different tokens, different variables. So we may think it is still possible they will learn the structure of the program. This is the first one, and the second one is we found several in our experiment. We found several programs that can be reduced into out-of-vocabulary tokens.
Okay, thanks. We can take it offline.
Okay, thank you.
Right. Then let's thank the speaker again. And we move on to the last talk. Thank you. To the last talk of the session. So Matteo will talk about optimization-aware compiler-level event profiling. It's from USI, Università della Svizzera Italiana. And the stage is yours.
Okay, just a second.
Okay, so thank you for the introduction. This is a joint work done in collaboration with Alexander Prokopek from Oracle Labs, Andrea Rosà, and Walter Binder from Università della Svizzera Italiana, Switzerland. This is a Toplas journal first article. It's actually 45 pages long. So in this presentation, due to a matter of time, I summarize only the main points of our work, providing a high-level overview. For in-depth explanation of the challenges, profiling accuracy, and implementation details, please refer to our article. So to analyze the effect of compiler optimizations, compiler developers usually employ either hardware performance counter or source level, bytecode level, and machine code level instrumentation. While the latter approach provides more useful information, it is well known that source and bytecode level instrumentation leads to inaccurate measurements. This is because of compiler optimization's effective event counts. Machine code instrumentation instead is too low level. It does not allow collecting bytecode level metrics. Moreover, neither of these approaches allow collecting information about compiler-generated events, such as speculative type checks and save points. Compiler AR-level instrumentation may solve these issues. However, also this kind of instrumentation needs to be carefully designed to be accurate, especially when profiling many different event types at the same time. I would like to present here the contributions of our work. In our work, we propose a novel instrumentation technique to efficiently and accurately profile the execution of compiler-generated events. We propose two path profiling strategies to count 43 different event types at the same time. And we implement our two strategies in the Graal JIT compiler for the Java virtual machine. Moreover, we propose a modification to the standard path profiling algorithm that makes it possible, that makes it practically usable in modern JIT compilers. Then we use our technique to identify the reasons behind the performance improvement and the causes of unexpected performance degradation. Finally, we evaluate our two strategies using the Renaissance and Takapo benchmark suites. Experimental results show significantly lower execution time overhead with respect to naive implementation. Before explaining our technique, I would like to present a background, starting from the terminology. In this presentation, we'll focus on just-in-time JIT compilers. Just-in-time compilers take as input a portion of code called the compilation unit. At the beginning of the compilation unit is transformed into a more suitable representation that we call intermediate representation, IR. Compilers usually perform manipulations in successive compiler phases that we call phases for short. Successive phases form the compilation pipeline. Within the compilation pipeline, the IR abstraction does not remain the same, but progressively gets closer to the machine code. We call this process of transforming the IR by removing abstraction lowering, and the phases that perform lowering phases. For example, at the beginning of the compilation pipeline, we may find load field instructions that specify a load of an object field. Closer to the end of the compilation pipeline, load fields may be lowered to read instructions that specify a read of a memory address instead. We implement our technique in the Graal compiler. Graal is a state-of-the-art compiler for the JVM. In Graal, a compilation unit is a Java method. And Graal uses a graph-based IR in static single assignment form. In Graal, nodes represent either expressions or statements, and directed edges define either the controller or data flow. I would like to describe now our technique. Our technique for accurate profiling consists of 4 steps, namely the event occurrence identification, the instrumentation phase insertion into the compilation pipeline, the marker insertion to the third insertion of the instrumentation code, and finally, the instrumentation code generation that takes place at the end of the compilation pipeline. I will now explain each of these steps in detail. To identify the event occurrences of interest, we define a predicate for each event type. The predicate checks whether a certain AR node represents an occurrence of that event type. We would like to note that certain event types can be directly mapped to basic AR nodes, such as object allocations, while others must be identified with static analysis. Let's consider, for example, this expression, optional of character value of x. The IR corresponding to this expression is reported on the right-hand side of this slide. White nodes connected with solid arrows define the control flow, while purple nodes connected with dashed arrows define the data flow. We are interested in profiling two different event types, that are the if event type and the allocation event type. Hence, we iterate over the AR nodes and we test the predicates of these two event types, identifying one occurrence of the if event type and two occurrences of the allocation event type at nodes 2, 4, and 6. Each event type predicate is tested by a new compiler phase that we call instrumentation phase. If we have multiple event types, we have multiple instrumentation phases. The problem is determining the place in the compilation pipeline where each instrumentation phase should be added. Indeed, inserting the instrumentation phase at an arbitrary place in the compilation pipeline may lead to two issues. First, if the instrumentation is performed too early, the profiler could wrongly instrument, or miss, event occurrences that are removed or added by subsequent optimization phases. Second, if the instrumentation is performed too late instead, occurrences may not be identified because the compiler has lowered the corresponding AR nodes. Hence, event occurrences must be detected and then instrumented after that they've been fully optimized, but before they are transformed into low-level representations, and hence are not available anymore. For this reason, we insert our instrumentation phases, so the instrumentation phase of each event type, after the last phase where that event type can be identified. Each instrumentation phase identifies the event occurrences of a certain event type. However, does not insert any instrumentation code in the AR. Doing so will reduce the accuracy of the collected metrics. This is because instrumentation perturbs compiler optimizations. For example, instrumentation code may contain side effects that alter subsequent optimizations, control flow, and instruction scheduling. Moreover, instrumentation code may, for example, increase the size of the AR, reducing the code size budget of subsequent optimization phases. There may be, for example, method inlining. So instead of inserting the actual instrumentation code in the AR, we insert placeholder nodes that we call markers. Markers are no OP nodes that denote the execution of a certain event type. Markers have no side effects and no data dependencies. Considering, for example, the previously shown IR, we simply insert markers either before the occurrence of the if event or after the occurrence of the allocation events. Finally, after the execution of all the compiler and instrumentation phases, we replace all the markers with instrumentation code. We define, for this reason, a single instrumentation code generation phase, ICG, which is injected at the end of the compilation pipeline. This phase may implement different code generation strategies. In our article, we present three implementations, namely direct event counting, which is a naive implementation that increments an event counter at every marker location, path decoding that exploits path profiling to perform bulk event counter updates at the end of program paths, and finally, path counting, that counts the number of times that a path is executed and computes the actual event counts offline using a path decoding table. In this presentation, due to a matter of time, we focus on path counting. We report here the previously shown IR. This IR contains two program paths. Both start at node 1, the start node at the top, and end with the return node 7 at the bottom. The first path goes through the true branch of the if on the left side, while the other path goes through the false branch of the if on the right side here. But this path end at the same point. Hence, we add instrumentation code only in a single point of this IR. Our instrumentation code for path counting is composed of two different parts, namely the path tracking and the path count update. Path tracking determines the path that is executed, while path count update actually updates the counter associated to that path. I would like to present here the use cases of our technique. When developing new optimizations, compiler developers need to carefully analyze the effects of their changes on the compiled code to assess the benefits. The problem is that changing one phase may have unpredictable effects on all the other compiler phases. Manually analyzing the IRs is time-consuming. Even though it may be a solution, this process is time-consuming. since an IR typically contains thousands of nodes. For this reason, we employ our technique to analyze compiler optimization phases. In our article, we show an example where we understand the reason behind the performance improvement. Second, we can employ our technique to simplify debugging. In our article, we show a use case where we identify the root cause of an expected slowdown introduced by a compiler phase. In this presentation, I'll focus on the first use case, hence explaining the reasons behind the performance improvement. In particular, we analyze the optimistic aliasing analysis OWA phase. This phase speculatively inserts information into the IR about which object pointers are actually the same, meaning they are aliased. The OWA phase allows other optimizations to perform, to optimize the code. These optimizations may be, for example, read elimination, write elimination, GC write barrier elimination, or vectorization. However, it's a priori unclear which of these optimizations are improved and to which extent. We noticed that OWA leads to a 15% speed up of the Renaissance benchmark ALS. Hence, we run ALS with and without OWA, and we look at event counts that significantly differ between the two executions. In this table, you can find in the first column the all and only metrics that significantly differ between the two executions. In particular, you can find some bulk metrics that are related to vectorization, and some other metrics that are, for example, loop end, if, and arithmetics. In the second column, you can find event counts collected for benchmark ALS for the metrics reported in the first column. These event counts are collected while using all the compilation phases. In the third column, instead, you can find the event counts for the ALS benchmarks for a certain metrics when using all the compiler phases except OWA. By looking at the metrics, we see that vectorization metrics, that is, the bulk metrics, are much higher when OWA is enabled. This suggests that OWA enables vectorization of more loops. This is confirmed by the loop end and if metrics. The loop end and if metrics both decrease when using OWA. We would also like to notice that arithmetic operations decrease instead, due to fewer loop index updates, memory address computations, and scalar computations. We would also like to notice that there is no significant difference in Java object array accesses that are indeed not reported in the table. This suggests that OWA does not significantly affect read-write elimination in this case. Before concluding, I would like to briefly present the evaluation of the overheads of our approach on the Renaissance and the Capo benchmark suites. In particular, due to a matter of time, we report only the geometric means across all the benchmarks of all the suites for the path counting strategy when profiling 43 event types simultaneously. In particular, we have an average execution time overhead of 1.18x, an average compilation time overhead factor of 1.48x, and an average code size overhead factor of 1.49x. We would like to notice how the compilation time overhead and the code size overhead are strictly correlated. In our article, you can find a more extensive evaluation. In particular, you can find a comparison of the 3 different implementations we have previously described, namely direct event counting, path decoding, and path counting. Moreover, you can find a detailed evaluation that uses several event types categories. That is, we evaluate several subgroups of event types profiled at the same time. To conclude, we propose a novel technique for AR event profiling. Our technique efficiently and accurately profiles bytecode level and compiler-generated event types, reducing perturbation on compiler optimizations. We propose 2 path profiling strategies to reduce instrumentation overhead. Moreover, we propose a modification to the standard path profiling algorithm that makes it applicable to modern JIT compilers. We implement our methodology in accounting profiler for the Graal compiler, and we use our approach to identify the reasons behind the performance improvement and the causes of an expected performance slowdown introduced by compiler phase. We evaluate our approach using the Renaissance and the Capo benchmark suites. Our experimental results show significantly lower execution time overhead with respect to NAV implementation. Finally, as future work, we plan to extend our implementations to support the collection of program execution traces. I would like to thank you for your attention, and I would be glad to answer your questions.
Right. Any question?
Thank you, Matteo. Just curious, the marker operations, is it possible for later compiler pass to move or remove the markers?
So the markers are like placed attached to the node they refer to. So if a later compiler phase moves the code they kind of attached to, the marker is moved as well. So in this way, we count for example, if the marker is attached to an if, and the if is moved, for example, outside of a loop, the marker is moved as well. So we actually count the right execution count in this sense.
Thank you. And I assume if the code is duplicated, loop is unrolled, the marker will be copied as well.
Yeah.
Right. Thank you.
Any other question? Quick one from my side. So I remember Da Capo has different types of applications, right? So is there any domain where this techniques works better, or are the improvements, let's say, cross-domain? I think Da Capo contains a ray tracer, for example, or the core of Eclipse, and these are very different applications. So does it perform? Can you correlate the performance of this technique to the type of the application, or is it really a cross-domain thing?
I would like to double-check the article, but as far as I remember, it's like cross-domain. I would like to check each of them individually, but yeah, it's kind of cross-domain. There is no particular like behavior, unless in like particular benchmark where we have like dynamic code generation. So we have code generation at runtime, and there we have like a different behavior for that reason. But for all the others, like the overhead is like in line. It's the same, kind of the same. It's like depending on the type of the application. Yeah.
Thanks. If there is no other question, then we are really in between you and lunch. Thanks for joining this session, and thanks, Matteo, again.
Thank you.
All right, everyone, welcome to the afternoon session. Welcome back from lunch. This is the session on SE for AI. And our first speaker is Chen. Chen, take it away. Oh, just give us a second.
Oh, yeah.
Wonderful. Go ahead.
Hi, everyone. I'm Chen. Thanks for listening to my presentation. Today, I will present my work, Runtime Prevention of Software Integration Failures of Machine Learning APIs. We have released our benchmark and code through this link. So let's first go to the introduction. Machine learning cloud APIs offer effective solutions for a spectrum of cognitive tasks. They enable developers to easily incorporate learning solutions into software systems. It requires less domain knowledge and completely removes developers' burden of designing and training neural networks. Due to this convenience, many software applications in a variety of domains are incorporating machine learning APIs. Unfortunately, these applications often experience integration failures in their use of these APIs. It's a type of failure that occurs when the output of an API invocation is incompatible with the software component that uses this output. Integration failures are widespread in applications that use these ML APIs due to underspecified interfaces of the latter. This phenomenon is particularly visible in two ways. First, every cognitive task performed by an ML API typically has more than one correct answer. Second, the model used by an ML API is inherently probabilistic, whose outputs are only statistically reliable over many input samples. To better understand these integration challenges and their consequences, just consider these applications, which is called flood depths. It's an open source application that uses vehicles as a reference to estimate the flood depths. As shown in the code, it first identifies objects in a street view image uses the ML API. It then iterates through all the identified objects and finds the one whose name matches one of the vehicle-related keywords in the target list. Finally, it invokes and predicts flood depths upon these objects. This code snippet seems straightforward on its own, but the software and the ML does not work well when integrated together. Here shows the API outputs onto adjacent frames in the video. As we can see, the left car is successfully identified by the API in both frames and is labeled as vehicle. However, without a clear API specification, the software developers do not anticipate the vehicle output and do not include it in the target list. As a result, this correct but unexpected output, this car will be mistakenly skipped in the flood depth prediction. Furthermore, the van in the middle is correctly identified in frame 1, but gets missed in the almost identical frame 2. Again, lacking API specification, the software do not anticipate this incorrect output and would omit this van in the flood depth prediction. With these vehicles mistakenly skipped, the software underestimates or even completely fails to predict the depths. Similar problems occur widely in software applications that use ML APIs. The straightforward way of integrating machine learning APIs, like that in example, cannot tolerate the API results that are out of context or occasionally incorrect, which leads to software misbehavior. It is desirable to have an adapter that converts ML API output at runtime to better fit the software component that uses the output, compensating for the underspecified interfaces of the ML APIs and reducing integration failures. To design such an adapter, there are several challenges. First, how to judge whether an ML API output matches the expectation of the software. Lacking the API specification, software developers do not know what output they may get from an API invocation and do not have a standard way to specify what output they expect. How to automatically extract that expectation and hence judge whether an API output matches the expectation of software is an open question. Second, how to judge whether an ML API output is correct. Like an ML API specification, it is difficult to know which specific output of an ML API invocation would be wrong. In fact, judging the correctness of an ML API that emulates human cognition tasks typically requires human effort, which is difficult to carry out during the runtime detection. And third, how to conduct compatibility checking and conversion with low overhead. High overhead is not acceptable for software users. Consequently, we cannot use expensive techniques, such as retraining and updating the neural network models at runtime, which will typically take hours of time. Next, I will talk about how we solve these challenges. We first conduct an empirical study to understand the challenges of integrating machine learning cloud APIs into software and the consequences of the integration problems. We studied 55 Python applications where ML APIs are used to make control flow decisions. As shown in the table, they cover a wide range of machine learning tasks. For each application, we created 100 test cases to offer roughly even coverage for all the passes in the function that invoke the ML API. Test inputs are from various sources: search engine, YouTube, public datasets, and audios recorded by the participants. Among all the unit tests, around 16 of them failed. Almost all of them are non-fail stop failure. At the first glance, one might blame the ML service providers for high failure rate. However, for both vision and language applications, the majority of testing failures are actually not caused by the incorrect output. In total, 2/3 of the test failures are caused by the ML API outputs that are correct but do not match with the software's need. Our further study reveals 3 main types of mismatch. Here we'll use a property management application and example. So the first type is hierarchy mismatch. This is the most common type of mismatch, contributing to 1/3 of all the unit testing failures. We know that real-world entities hierarchical relationships. For example, one is subclass or a component of the other. One object can often be correctly described by multiple labels at different levels of hierarchy. However, a software application may only be coded to recognize one of these labels and causing this hierarchy mismatch. Here we show the example is about roof, landing, and light. Besides this, there's also perspective mismatch. Given an object, we can output multiple correct labels that describe the object from different perspectives, like shape, texture, and colors. Perspective mismatches contribute to around 3% of all unit testing in our study. In this example, the software expects the API to describe equipment, while the API actually outputs its material. And the last type is focus mismatch. Sometimes the software applications cares about a particular object in the input image or video, and yet the ML API outputs are about the other objects in the input. This contributes to around 1/4 of all unit testing failures in our study. In this example, the software expects the API to describe promptly, while the API thinks the hands are the main element of this image. ML APIs adopt statistical models without strict correctness guarantees. Therefore, from time to time, ML APIs produce incorrect outputs, which lead to about 1/3 of all the test failures. In the study applications, incorrect ML API outputs mainly come from 2 sources. First, the neural network volatility. A small perturbation of the input may trigger inner flows of the neural network models and lead to an incorrect answer. As another example, a real-time game tracker uses the text detection API to extract all the status logs from the screenshots. And here shows the logging area of 3 adjacent frames of a game video, which share the same text string at the same position. However, due to the minor background changes, the API recognizes different text from them, and leading the software to make different decisions. And second, the low input quality. Sometimes the software input does not contain enough information for ML APIs to perform its cognitive task, like a blurry photo or a noisy audio clip. Here we illustrate a voice assistant application. It records the user's voice command and uses the recognized API to transcribe speech into text strings. It is supposed to play music when the user says, "play this sound." However, the ML API often wrongly recognizes as play sound, missing a character from the audio clips with a high speaking rate. This small mistake caused the software to misbehave, not playing the music when it should. So guided by our study, we proposed SmartGear. SmartGear serves as a middle layer between ML APIs and software that uses them. It transparently and automatically checks and converts output of ML API calls, preventing ML API integration failures. To use it, application developers only need to apply a static code instrument routine to the applications, which insert the SmartGL method after every ML API invocation. At the runtime for every ML API output, which is typically an array of values, SmartGL applies a series of incompatibility checking, starting from mismatch checking and followed by the incorrectness checking. Whenever SmartGL figures out a way to convert an output value, the new value is inserted to the original output array. So we conduct all the checking through the bytecode level instrument. Therefore, the developer's source code remains unchanged. At a high level, SmartGL tackles the mismatch between ML API output and software by examining the cognitive relationship between them. It includes several steps. First, for each invocation of an API, SmartGL conducts static analysis to obtain focal values to represent ML API outputs that software is interested in and knows how to handle. Next, at the runtime, right after the invocation of ML API, SmartGL compares the API outputs produced there, which is typically an array of values with focal values associated with ML API. The SmartGL's incompatibility detection checks if there exists any hierarchy, perspective, or focal mismatch one by one. Guided by the empirical study, our checking is centered on using a knowledge graph to understand the cognitive relationship between the API outputs and focal values. So is the one the superclass or the alias of the other? Is the one from the different perspective of the other? Or is the one related to the other, even though there's no superclass relationship? And when some mismatch is detected, a conversion attempt follows. We first try to clustering the ML API outputs to software focal values, like clustering the roof lantern to the lights in the property management application. If it fails, we will try segment and ensemble strategy. So here's another example. When the ML API outputs furniture initially, the SmartGL would not immediately know how to convert this output, as the furniture is a superclass of both light and sink, which belong to two different focal value sets. So in this case, SmartGL will segment the photo into 4 pieces and try again. And this time, it correctly recognizes there's sink in the image. As discussed earlier, it's difficult to automatically judge whether the output of an ML API is correct or not. SmartGL tackles this challenge by leveraging information beyond a single API invocation. First, validate across the APIs. SmartGL utilizes earlier invocation of other APIs on the same input. For example, a smart album uses Google's face detection API to find human faces in the image. It then invokes Google's label detection API to categorize the same image with the focal value face. While the former is a more specialized API for finding humans, the later API is also able to classify human images. Therefore, when one of them recognizes the face but the other does not, the SmartGL will regard the later as incorrect and adds face to the output array. Second, validation across inputs. SmartGL utilizes earlier invocation of the same API on the similar inputs. Let's go back to the flood depth application. The SmartGL detects the object localization API provides different vehicle detection results across the adjacent video frames. SmartGL then invokes the corresponding video API, which finds all the vehicles in the image, and forwards the last frame result to the software as a correction of the most recent invocation of the original vision API. And finally, validating across software and ML APIs. It will cluster ML API output to software focal values, particularly for those have text string outputs. And next, I will introduce the evaluation. So we evaluate SmartGL using 65 applications, including the ones in our empirical study and also the additional ones. And we also design a new set of tasks for each applications using the similar methodology. And we compare SmartGL with 4 baselines: crash only, which only captures the software crashes; ML API only examines the ML API confidence scores; software only examines the control flow of the software; and the last one, the software segment, it will apply the segment and ensemble strategy. In summary, our SmartGL detects 70% failures with neglectable false alarms. For the 300 incompatible ML API output missed by SmartGL, there are mainly 2 reasons. First, 60% of the false negatives are focus mismatches, which are not only common but also inherently difficult to detect. Second, over a third of these false negatives are incorrect API outputs. SmartGL fails to detect them as it assumes that ML API is reliable for most of the cases. In comparison, the 4 baselines either miss many failures or raise many false alarms. The ultimate goal of SmartGL is to improve applications execution correctness. So SmartGL achieves this goal by improving the average execution correctness rate across all applications from 84% to 95%. It results 1/3 incompatible outputs using all 4 types of fixing strategies. In comparison, the software segment, the other scheme that has failure prevention capability, is only able to eliminate 126 failures, improving the execution correctness by only 2%. And here is our ablation study. It shows that all of our components all contribute to our results. And finally, I will go to the summary. So the integration failure is widespread in machine learning software. To solve this problem, we propose SmartGL, a tool that automatically detects and converts mismatching or incorrect ML API output at runtime, serving as a middle layer between ML API and the software. Our evaluation proves its effectiveness. We welcome people to try our tool and join us in improving machine learning software. Thank you.
So thank you for that talk. So I'd like to invite people to come forward to the microphones to ask questions if they have any, and do introduce yourself for the remote audience. I can start us off with a question. So it seems like the APIs that you've been talking about in your talk are are either taking like image or video as input. Can you talk about what other techniques might be needed for, say, APIs that take a natural language input or like audio input?
Yeah, great questions. So I use the image ones just because it's easier for me to present in the slides. Actually, we study all the 3 types of applications. So let me just find the one we showed. Yeah, so we cover all these types of APIs. So they include the vision ones, the language ones, and also the speech ones. And these are the popular categories from the commercial cloud API services.
Any other questions from the audience? Okay, let's thank the speaker again. Good. All right, and so Mahdi is our next speaker, and take it away.
Okay, hello everyone. I'm Mahdi Ghorbani, a PhD candidate of University of Edinburgh, and today I want to present our paper, Compiling Structure Tensor Algebra, to you. So let's start with the motivation of this work. Tensor algebra basically lies in the heart of many, many applications like machine learning, deep learning, quantum computing, and signal processing. And these tensors are usually structured in some way or another. So they can be dense or they can be sparse, as in they have like several 0 elements in their structure. And there are tons of frameworks working on providing efficient code for both sides of the spectrum. Like for dense computation, we have TensorFlow, PyTorch, NumPy, a lot of frameworks providing efficient code generation. And we have Taco, SciPy on the other side of the spectrum, providing good infrastructure for sparse representation. And when we move towards the dense side of the spectrum, we get more specialization opportunities. Like we have better vectorization, parallelization, cache locality. And when we move towards the sparse end of the spectrum, we have more flexibility. And we get a lot of benefits, like better storage, better and smarter algorithms that have lower computational complexity, and we can scale them to larger size of data and larger size of tensors. And we observe that in so many cases, we have other form of structure that is some form of like crossover between dense and sparse. So it's basically sparse, but it has like some nice form of structure that we can capture it symbolically, and they appear in like machine learning and signal processing as I go to them through this talk. And our main focus is on this type of structure. So let's start by what we mean as structure and how we can capture it. So here, for example, we have a diagonal matrix, and it's a 4x4 matrix, and it's very sparse. So if we want to capture it, capture this diagonal, these unique elements in a set, we can represent it in this format. So if we put x between 0 and 4, y between 0 and 4, and x equals y, it basically captures all the non-zero elements. And we call this a unique set. So basically, unique set is all the non-zero elements, and we just ignore the zero elements. And it would be very nice if we can do some structure reasoning, meaning that if we can propagate that structure throughout the whole tensor algebra computation. And let's see what we need to do that. So first, we need to represent the tensor algebra computation over this matrices. And it's basically matrix-matrix multiplication. So we have T of x and z equals to m of x and y multiplied by v of y and z. And we represent the structure of the inputs. So as we had in the previous slide, the structure of both of them are diagonal. So they're represented as x and y between 0 and 4 and x equals y. And structure of v is basically the same, y and z between 0 and 4 and y equals to z. And what we want to know is what is the output structure. But for this, we need a better representation. This set representation is not ideal to define some form of automatic structure inference on top of them. And we cannot easily propagate the whole structure throughout the tensor computation. So for that, we defined a better representation based on using the same notation as tensor algebra to cover it. So here we have the set representation of this diagonal matrix. If we just do a mapping from false and true to 0 and 1 and transform the conjunctions to multiplication and disjunctions to addition, we can reach to this other representation, which is very similar to the tensor algebra input. And it's going to be x between 0 and 4 multiplied by y between 0 and 4 multiplied by x equals y. And these two are corresponding to each other. So if we have this representation, now let's go and do the structure reasoning and find out what is the output structure. So for that, we have a full set of structure reasoning rules, structure inference rules in our paper. And this is just one example of a generalized version of one of them. And it says if we have a multiplication of two tensors and the set of variables in the input tensors, the union of them is equal to the output variable, the set of variables of the output tensor, then the unique set of the output is going to be basically multiplication or conjunction between the unique sets of the inputs. So here we just put the structures, put the unique sets in the formula. So the two matrices are diagonal, so these are the structures, and we multiply them. And as expected, we get the diagonal as the output structure. But is this the only interesting structure out there? The answer is no. So if we have something like redundancy structure, what do I mean by redundancy? Here, for example, we have symmetric. And in symmetric, if we take a look at the upper triangular part of the matrix, we can basically capture the whole elements. Like basically, the lower triangular part is the same as the upper triangular part if we have a proper mapping from the lower triangular part to the upper triangular part. And here, we change the definition of unique set and take it a bit more literally. And we only keep the unique elements in the unique set. So it's non-zero and it's unique. So here we chose to select the upper triangular part as the unique part. I mean, we could pick the lower triangular part, but here we just picked that. And we have a redundancy map. And this redundancy map basically provides the proper mapping that we needed. So it has double the number of variables of the original tensor. And the conditions over the first two tensors are representing the area that has the redundant elements, here the lower triangular part, and the conditions over the last two dimensions are basically representing the mapping that we need. So here, if we swap x and y, we can basically find the unique elements that we want. We can retrieve all the elements. But the question is, are all the structures this simple and easy to capture? The answer is no. Imagine we want to create a covariance matrix for polynomial regression degree 2 over a vector of size 4, very tiny vector. And this is the output. It's going to be a 20 by 20 matrix, 400 elements. Only 65 of them are unique. As you can see in the right-hand side figure, only the black elements are the unique elements, and rest of them are just repetition, and we can just capture them through our redundancy map. So let's see how we can do that, how we can capture this nice structure there. So for that, we need to have an intuition on how we create the covariance matrix first. So basically, for creating covariance matrix, we have a vector x, and we do XX transpose, or self-outer product of x to itself. And x for polynomial regression degree 2 is going to be a concatenation of a vector called f and the linearized version of self-outer product of f to itself. And we just replace this value to the formula, and we can see that we can only compute M1, M2, and M3 to capture all the elements. And M1 is corresponding to the top left part, M2 is the rectangle on top right, and M3 is the square on bottom right. And the rectangle in left right is, in bottom left is basically equivalent to M2, because covariance matrices are technically symmetric. So as long as we have a redundancy map, we're good to go. So to know how we can do that throughout our architecture, our framework, we need to know a bit about the architecture of our framework. So our system takes tensor algebra and the input structure of the inputs as an input. So we have basically tensor algebra computation. We have the structure of all inputs there. And then we have a structured tensor unified representation. And why it's called unified representation, I go through that later. We pass it through star, and it does structure inference. And what is structure inference is basically what you've seen in previous slides. We propagate the structure of the inputs throughout the whole tensor computation. And we infer the output of the structure of the output. And the next step is optimizations. We do some level of optimization over the inferred structure. And the very last step is code generation. And we generate C++ code, structure of our C++ code for the tensor algebra computation. So let's go back to the example that we had. So because of lack of time, we just focus on M2, M1, and M3 can be computed in the exact same way. So as long as we know how everything happens for M2, we're good to go for M1 and M3. So let's see how we can generate code for M2 and for M2. So M2 was this mathematical computation. First, we need to translate it to tensor algebra and put it as an input to star. So the translation is going to be M2 of ion call equals to self-outer product of f 3 times to itself multiplied by column equals j times n plus k, which is a linearization condition because we want to fit everything in a matrix. It's the vec in the mathematical notation. And some of you might wonder how we are doing like a multiplication between real domain and Boolean domain. So here, basically, the self-outer product, which is the actual arithmetic computation of this tensor algebra computation, is going to be separated inside star and from the Boolean domain, and it's going to be used in the code generation. So basically, we write it in this way. We multiply all real domain and Boolean domain to do the structure inference properly, do optimizations properly. And in the end, most of the Boolean domain, which is the computation over indices in our computation, is going to end up in unique set and redundancy map. And the real part is going to represent the actual arithmetic, and it's going to end up in our generated code. So we separated later, but star treats them properly, and basically in Boolean domain, we translate them to conjunction and disjunctions. In real domain, they're just what you see there. And the second input that we have is the structure. So the structure of vector f here is x between 0 and n. And we take that as input. And now we want to do structure inference. What our structure inference says, structure inference rule says, is that if we have a self-outer product of a vector by itself 3 times, we just restrict the area. Instead of like iterating over a cube, we can iterate over this pyramid. Like we restrict the computation domain, and we write it as this part. And the Boolean part of the tensor computation is going to be appearing in the unique set as it is. And the next step is we apply some optimizations. The first one is inlining. We put the structure of f in this computation, and this is the output. The next step is logical simplification. And the I less than equal, j less than equal, k, and both, like all of them between 0 and n, basically subsumes the I between 0 and n, j between 0 and n, and k between 0 and n. So we just get rid of them, and we keep the last line. And we need to generate some code for that now. So we have the output structure, and we have the tensor algebra input. So we can basically use the unique set, the structure, for generating loopness and the computation over indices. So here it's for I between 0 and n, j from I to n, and k from j to n. And the index call is equals j times n plus k, which all of them are computed based on the unique set. And the arithmetic part, fi times fj times fk, is going to appear in the computational part of the code. And we've done some extensive evaluation. As an example, we have some of them here. Polynomial regression degree 2 is the example that we had throughout the slides. And as you can see, if we change the size of the vector, the input vector, from 125 to 250, we can get 1 to 2 orders of magnitude performance boost compared to PyTorch, NumPy, TensorFlow, Taco, and all of them have like very optimized kernels down there, but we can outperform them because we are structure aware. And MTTKRP is another kernel which is used for tensor factorization. It's very important. And in this case, we get between 1 to 4 orders of magnitude performance boost. And there is another important kernel, convolution, 1D convolution, which is used in signal processing a lot. And there is no proper tensor algebraic representation of it. And all of these frameworks out there, they use like some sort of manual implementation, which is very hand-tuned and very optimized to do the convolution, but we transform it to a matrix into like pure tensor algebraic form using a matrix vector multiplication, and the matrix is like using this variation of two-uplist matrix, which has both redundancy and sparsity. And on the right-hand side, we see that if we use the convolution kernel using the same libraries, but using the two-uplist matrix multiplied by a vector, then we outperform them significantly. And even if we use them, even if we use the built-in kernels that they have, we can see on the left-hand side that we are competitive or outperforming all other competitors. So if you want to know more about STAR and the full set of inference rules that we have, if you want to know the optimization techniques that we use, if you want to see the actual compilation and code generation algorithm, if you want to know the proof of soundness for inference rules and extensive experimental results, you can take a look at our paper. And in conclusion, basically we have a framework working on structured tensor algebra, and by structure we mean sparsity and redundancy. And in this framework, we do automatic structure inference using STAR, which is our unified intermediate representation. And we introduce struct tensor, our framework, and it does all of the automatic structure inference, optimization, and code generation. Thank you for your time. If you have any question, I would be glad to answer.
Thank you for your talk. I have a question. What kind of inputs does your system take? Do user feed tensor of numbers and your system will automatically dig out the relation between elements? Or do you require the user to program the tensors and tell your system what are the relations?
So currently what we have is we expect the user to provide this information, meaning that like the sparsity pattern of the inputs should be provided by the user. But as a future work, we're working on like capturing all the relation, like capturing the unique set and redundancy map automatically.
I have a further question or comment. I think if you want the user to program the tensor, the user might prefer program the computation directly. I mean, maybe programming the computation requires the same efforts as programming the tensors.
I mean, I do not agree with that fact, because like the examples that I had here, they were quite simple and they were just for representation. But imagine we have like, I don't know, a function of 100 lines of code, and it's full of like, I don't know, different structure types of tensors, and the user knows the input structures, but throughout that whole computation of, I don't know, like 100 tensor algebraic computation, if they want to keep track of like each of the structures, it's going to be much, much harder, and they can't automatically, have all of that. It's going to take a lot of effort and time.
Thank you.
Yeah, no worries.
Let's take a question from you.
Thanks. Wonderful talk. My name is Pratik. I'm from NUS. I was wondering, I mean, you're computing these covariance matrices as you go along, right? And this computation for a very long time is, like, it performs really poorly with increasing dimensions, right? Say order of d cube, where d is the dimensions, right? So did you run into this issue, like when you were trying to scale up these, your benchmarking on larger and larger, today we use very high dimensional models, and so, what's your experience with using these large models?
So basically, I mean, let me bring that slide. So it actually takes, some time. Like, it's true that it's O of n3, so we, can't do anything about that. But like, basically, our framework can roughly give like 24 times performance boost. I mean, it does like the computation over like 24 times less elements, roughly. So, I mean, we are not changing it by orders of magnitude or like the complexity, but we are changing the actual runtime with a large constant factor.
Okay,
so
and the analysis time should increase, right? Like, obviously,
the analysis time is, I mean, it's not that long, because like basically we have a set of inference rules and we just use them, and that one doesn't take that much time. Plus, that's in compilation time, so we just do it once and then that's it.
Okay, thanks, wonderful.
Maybe a quick question there while the next speaker is setting up.
Hopefully quick. So if I understand correctly, the storage you use is compact, right? You just store a vector and it represents the whole covariance matrix, right? But it seems that there's a certain maybe subclass of sparsity patterns where that is possible or that you recognize. So my question is there some kind of theory for your optimization techniques so that you stay within that class of sort of things you know how to store?
Oh, okay, good question. So here, we actually do not store everything in one vector. Like basically, we keep the structure as dense, like a multidimensional array, and we perform the computation over only the parts that they have the elements. It's going to be our future work that we're going to, have an optimized and efficient
just store
storage.
the diagonal and don't worry
Exactly,
about it.
exactly.
Okay, got it, thanks.
Let's thank the speaker again. And Angelo is our next speaker. Your ball from the next paper, right? Great, okay.
Our work
is focused on the safety of ML-based cyber-physical systems, such as autonomous vehicles that use vision-based perception. In these systems, ML modules enable perception tasks to estimate ground truth real values of the environment. For example, how far is the pedestrian away? We're interested in showing safety of such systems. An example of a safety property is for the car should not leave the current lane. So we pose a fundamental question here is, what exactly is a contract for ML vision components? And how can such contracts help us reason about system safety? Contracts for ML component, much like those in traditional software, consist of pre and post conditions. For example, the specification for robustness says for some input x and all inputs x prime within a ball of radius centered at x, for some radius centered at x, the output label of the original input x and the label of x prime should agree, right? That says something about the input and says something about the output. However, these kind of contracts cannot capture relevant objects for perception on images. This is a problem when we're trying to assure the safety of these systems. As you can see, the particular example is how would we be able to express from images that if the pedestrian is 5 meters away? So to address this, we propose perception contracts. But before I formally define it, I sort of want to discuss the insights that we make for the formal definition. So perception contracts are not usual module contracts. They do not relate inputs and outputs of an ML perception module. Rather, they relate the implicit ground truths associated with the image to the output ground truth estimates given by the perception module. So you can see in the top left corner, we have two kinds of perceptions. One that deals with a real environment interacting with the perception module via images, and another one where there's a model of the environment. There's a model of the environment that takes in feedback from the controller system, and gives you the ground truth values for a perception object. So as you can see here in the third diagram at the bottom, a perception contract, what it's really doing is relating this perception indicated in the blue line that deals with a real environment and ML-based perception, and this other sort of perception that involves working with a model of the environment. And in fact, if you notice, given that it is not clear how to formalize a relation among images and pixels in images to a perception contract, we can't really use any sort of verification approach here, right? I wouldn't know how to do that yet. So I think the only course that we have for now is to sample some states of the system and to gain as much confidence as we can of these perception contracts. So formally speaking, we propose perception contracts. So consider that we have a ML perception and a safety property fee for it. And now also consider that we have an ideal system with ideal perception, meaning that the estimate, GTE that we know here, equals the ground truth. That's what we mean by perfect perception. And then assume that we have an inductive invariant that proves the safety property, phi, for the system working with ideal perception. A perception contract for a system is defined with respect to such an invariant. The perception contract relates ground truth and ground truth estimates, intuitively capturing the error ML-based perception is allowed to make. It is a symbolic formula in logic that relates ground truth and ground truth estimates and ensures the crucial property that if we start with the state satisfying the invariant, and the environment on this state transitions to a new ground truth GT, and perception contract allows an error in ground truth estimate GTE, then the controller, reacting using this estimate as a result in a new state that continues to satisfy the invariant. And I point your attention to the predicate that is control of S on GTE produces this S prime, which is the next state. And that's sort of the key property here. And below, you can see an example of what a perception contract looks like. We have these perception variables, y theta, and those will be the ground truth variables. And we have ye and theta e, which are the estimates. And as you can see, this formula is more or less bounding how much discrepancy can be between these values. So now we're ready to define the perception contract synthesis problem. Given an invariant of the system, given an invariant that the system maintains and shows the safety of the system, and a set of pair of ground truth and their estimates, which we can assume also preserve the invariant, and a logic for expressing contracts. The goal of the synthesis problem is to find a perception contract such that the following two things hold. The given input set of pairs of ground truth and their estimates are included in the perception contract. And more importantly, the perception contract maintains the invariant for all the states S under the ground truth perception GT and estimates GTE from the given input images. Okay, so this is the problem. This is what we want to accomplish. Now, how are we going to build a learning algorithm to find these contracts for us? So to do this, we propose a learning approach called Perceptor. Each round we begin with a set X of ground truth and estimate pairs, labeled positive or negative based on if they preserve the invariant. The learner synthesizes a classifier that separates the samples in X and proposes it to the teacher, which then checks whether the pairs of ground truth and ground truth estimates defined by the contract maintain the invariant. And that's sort of like the key point that I want to make in this slide is that the teacher, in this case a constraint solver, will check for each candidate perception contract whether that following constraint holds. If it does not, the teacher will give us back a counterexample, which is a GT-GTE pair that it's included in the candidate perception contract, but not in the invariant. Now, in terms of implementation details, for the learner, we use a decision tree learner that we modified to be an exact learner. So it's a consistent classifier, doesn't make mistakes. As for logic, we use quantifier-free formulae and Boolean combinations of octagonal constraints and real value functions with upper and lower bounds. For our teacher, as I mentioned, we use Gurobi, which is a constraint solver based on mathematical optimizations. And this sort of takes us to, okay, so now we've proposed perception contracts. It's there, but okay. So now we've defined perception contracts. I've told you define the synthesis problem. I've defined a way to synthesize these. So now, I guess, we have to put it to action, right? So to evaluate our approach and the utility of perception contracts, we use two case studies. One is a lane tracking system on a Polaris Gen E2 electric vehicle, and a crop follow system, an agricultural robot that follows crop. Although these two systems might be similar at first, they are significantly different. For example, the neural perception for the lane tracking system is LaneNet, which is a very large model. It's 18 layers and over 3 million neurons. The controller is the Stanley controller. And we collect over 24,000 GT-GTE pairs for synthesizing a perception contract. The crop follow is just a different Neural network is ResNet 18, and for that one, we collect over 7,000 GT and GTE pairs. Something I do want to point out is that these systems are proven to be formally safe under perfect perception. And as you will later see, with neural network perception, these systems are not safe. So we make some design decisions to address this. So continuing on this, as part of our evaluation, we set up an environmental model, as discussed earlier, and we define sort of the perceptions that these systems are estimating. The perceptions in this case is d, which is the relative distance, and psi, which is the heading angle, and these two precisely describe the location of the vehicle. The invariant for these two case studies has a similar shape, but different sort of V functions here. And the invariant is saying that they require that the system, when the system is evolving, the error they make is always not increasing. This V function takes a ground truth values of ground truth estimate values of D and psi, and now puts a non-negative real value representing the distance to a desired state. So for example, in the lane tracking system, a desired state would be when D is 0 and psi is 0, because that means that the vehicle is perfectly aligned with the center lane. So in our case, the B function for this case study is simply a distance function from that particular state to the origin. The other thing I wanted to mention is that, as I mentioned, these systems are not proven to be safe with neural perception, correct? So we take the space of all of the state space of ground truth perceptions, right? So all the possible locations where the vehicle can be, and then we partition them based on if they're safe or not safe. So as you can see here, this vehicle is facing away from the center lane. So that in that sense, it'll be unsafe. Sorry about that. Okay, so here we discussed our approach, or the results of our approach. So as you can see here, we have various configurations for a feature space. This feature space defines sort of the kind of constraints that that the decision tree learner has access to. But the main takeaway here is that you can see that on regions that are safe, meaning that there are no GT-GTE pairs that violate the invariant, and the region is unsafe when there exists at least one GT-GTE pair that violates the invariant. So on safe regions, you can see that our approach is very good at finding perception contracts. So I think the main takeaway is also that we can learn these perception contracts effectively, and we can do so in a reasonable amount of time. Excuse me. Now, I want to sort of illustrate these pictures in context, so it makes a little bit more sense. On the left, you can see is the region of ground truth values. So blue indicates that region is perfectly safe, and then the black arrow indicates sort of how the vehicle would be positioned. On the y-axis, you will find the relative heading angles in degrees, and then the relative distance on the x-axis. So as you can see, that when the vehicle is positioned sort of further away from the center of the lane, the system is unsafe, and so that sort of makes sense, right? Violate the invariant. And also on the top right. And as you can see for one of the results where we cover all the cases, we have a check mark. And that's sort of how you can see how we find perception contracts. So the last thing I want to discuss is runtime monitoring. I think we can use runtime monitoring. We can use perception contracts for doing runtime monitoring, and this is something that we wanted to sort of evaluate. Right? To do this, we validate perception contracts within the context of closed-loop systems, and then so we run these systems with simulation. We collect the traces, as you can see there in the results in the table, and then we compute sort of the precision. So now, as you can see here, the main takeaway here that you can see is that our results indicate that PCs can be effective during runtime monitoring and can alert users of problematic regions in safe problematic regions. So because in safe regions, it agrees with the invariant very well, but we notice this pattern that in unsafe regions, although the precision doesn't drop significantly, it kind of is indicative that, okay, so it's not agreeing with invariant so much, so maybe there should be some sort of debugging that needs to happen. So just to culminate, another reason why we can use the invariant for runtime monitoring is because, in this case, the invariant says that this perception, which says that we have two-lane road, it's okay. There's no error here. But our perception contract, because it checks against all states for a given perception, says that at faster speeds, but reasonable, at fastest but reasonable speeds, the perception causes the system to break the invariant. That is all that I have, and now I'm ready to take some questions.
We have time for like one quick question if anyone has one. Why don't you go set up? Let me ask a quick question. So any thoughts on like sensor fusion? So you're in these systems, you're often dealing with like multiple sensors that are sort of, monitoring the road or something. Any thoughts on how this might fit into that? Any thoughts on sensor fusion, where you have, say, multiple sensors, say LiDAR plus, a normal vision camera, for example, sensing the same thing, and when they disagree? Like, how would perception contracts fit into that kind of system?
So the notion of So in a setting where there's multiple sensors, are you saying that would that be a problem for perception contracts?
Yeah, just your thoughts on that.
No, I don't think so. So because generally speaking, yeah. So we want some inputs, could be images, and whether it's come from sensors. We're working at the level where we just care about the output of your perception module, whatever that is, right? And yes. Can we take this one offline?
Sure.
Thank you.
I'm not getting the, not sure what's going on.
Great. So Paul is our next speaker.
Okay, how's this for volume? Good? Yeah?
Yes.
Okay. Yeah, so my name is Paul Krogmeyer. I'll tell you about this work on languages with decidable learning. This is work with my advisor Madhu at the University of Illinois. Right, so this work is about symbolic learning and synthesis from examples, and in particular, a generic algorithmic technique for getting decision procedures for these problems. So many applications of symbolic learning, well-studied problems like program synthesis, where you're trying to construct a program from examples to fill out your spreadsheets, or in verification, trying to find invariants for proving distributed protocols correct. These are naturally expressed in quantified logics, trying to synthesize tedious to write SQL queries from examples, and also in things like mathematics. There's been some interesting work trying to conjecture interesting theorems in graph theory in sort of example-driven synthesis loops. some of my own work on trying to synthesize axiomatizations for classes of structures. And then also this morning there was a nice talk on synthesizing program specifications from examples. All right, so there's lots of applications, and this talk is going to try to tell you something about something that they all have in common when it comes to learning in these languages. So this is an algorithmic meta theorem for symbolic learning problems that at a very high level says, if you can write a specific kind of interpreter for your symbolic language, then you can kind of compile that interpreter into an algorithm for the learning problem, the synthesis problem, that's actually a decision procedure. Okay, so in the remainder of the talk, when I talk about learning, I mean this generic concept learning problem. So you have some symbolic language L, and you're given two things: a grammar G over the expressions of L, and a finite set of examples. Okay? And then the goal is just to find an expression in the grammar that's consistent with the examples. So consistent depends on the problem. All right? So here's an example. So you've got these 4 graphs. The 2 on the left are labeled positive, the 2 on the right are labeled negative. And the goal is to find some logical formula phi that holds on the positive graphs and not on the negative graphs. So now if I told you that the grammar here, it's first order logic, but you only get to use conjunction and existential quantification. So no universal quantification, no disjunction, no negation. In that case, it turns out that there's no concept which can classify these, right? So in general, how do you decide that? How do you search an infinite space of expressions or programs and conclude that there's no solution? Okay. So this doesn't just have to be about programming languages or classical logics. This is also about things like learning regular expressions. So you might have a set of positively and negatively labeled strings, like valid email addresses and invalid ones, and I say, give me a regular expression which matches the valid ones and not the invalid ones, right? So the question is, when can we find terminating algorithms? So these are expressive languages with infinitely many programs or formulas, so you can't naively enumerate them and still conclude that there's no solution when there isn't, right? Another point I want to emphasize is, if you're expressive enough, you can define examples up to isomorphism. And so we don't like that. I mean, learning regular expressions from these words, like A, B, A, B, A, B, A, B, A, B. We like A, B star, right? We don't like the one that says, oh, it's either positive example number 1, or number 2, or number 3. So that's A, B plus A, B, A, B plus A, B, A, B, A, B. So the grammar is crucial, and it also makes the problem computationally complex. Okay, so back to this meta theorem. You come to me with a symbolic language L, and you say, I want to do learning or synthesis from examples in L. So this meta theorem says, okay, write a suitable interpreter, and we can compile it to a learning algorithm that's actually a decision procedure. Okay. This interpreter has a particular form. It's a little recursive program, and it takes 2 inputs: a structure, an example, and an expression. And it's going to compute either true or false, depending on the problem. So if we're learning in first order logic, we'll write this little interpreter called FOL, that takes a graph, perhaps, and a first-order formula phi, and it computes true exactly when the graph satisfies phi. Or if we're learning regular expressions, we'll write an interpreter called reg that takes a word and a regular expression and computes true exactly when the word is matched by the regular expression in its language. So we have this programming language called Facet. It's sort of a notational tool for writing these interpreters, right? I'm not going to talk about the syntax and semantics. If you're interested, ask me after or see the paper for the formalization. The only thing I want to point out is that these programs in Facet take the expression. Remember, there's 2 inputs, structure and expression. They take the expression as a syntax tree, and the only way they access it is by referring to a pointer n that points into the syntax tree, and they can walk up and down on the tree by going to the parent or going to the child or the left child or the right child. And so they're kind of computing on the tree, updating a little bit of state as they go. So we'll see an example. Okay, now the meta theorem, specialized in light of this language Facet, says, given the language L, write a Facet interpreter for L, and then you'll get a learning algorithm. Okay. The crucial requirement here, so the interpreter has a requirement on the memory that it uses, right? It takes a structure and an expression, and it needs to compute the semantics of the language, basically. So it needs to store the structure and the expression somewhere, but how much memory does it use over and above those things? So that extra memory, which I'm putting in the middle there, should not depend much on the expression. It gets to point into the syntax tree using pointers, but that's it, okay? it can depend wildly on the structure, however much it wants, right? So it gets to use memory that as the structure grows, the memory can go up, but as the expression grows, it can't use any more memory for a fixed structure. Okay. The proof of the meta theorem kind of relies on translating these interpreters to tree automata. So in a learning problem, you get some examples, right? And you can say, I'm going to specialize the interpreter for each of these examples. And then that object you can translate to what's called a two-way alternating tree automaton. And then algorithms we can get by using tree automata emptiness checking. So you get these tree automata, you take a large product of them, and what you end up with is this final tree automaton whose language is exactly the solution set for the learning problem. Okay. So now I'm going to walk you through an example of learning regular expressions, right? So we want to learn them, we want an algorithm, so we're going to write this interpreter called reg, which takes a word W, a regular expression E, computes true if the word is matched by E, okay? The question you have to ask when using this meta theorem is, what kind of memory do I need to do the job? In the case of regular expressions, it turns out that you need to keep track of the subwords of the input word W, okay? So I'm going to represent a subword with just 2 indices into the word L and R, so L's on the left, R's on the right, okay? So now I've made that extra memory explicit as that middle parameter there, and the program on a word W with this LR and a regular expression that's pointed to by N, this program will compute true exactly when the subword from L to R in W is matched by the expression that I'm pointing at with N, okay? Here's the interpreter, right? It's fairly simple. So I'm just showing a few cases for like a subset of regular expressions. Let's suppose that we're working over the regular expression AB star, right? So initially the pointer is looking at the root, so it's seeing the Kleene star symbol. And initially L and R would be the first position of W and the last position, but that'll change as the program computes. So it's reading the star symbol and it says, this is really just intuitively what regular expression semantics is. You've got a word, you want to break it up into a prefix and a suffix, and check that the prefix matches the internal part of the expression that has the star around it, and then check that the suffix matches the starred regular expression again, right? So that's what's happening in this case. If L is equal to R, so if I'm checking the empty word, then I'll return true because the empty word is matched by any starred regular expression. Otherwise, I need to find if there's any way to productively decompose W by splitting it into a prefix and suffix and recursively calling the program either at the child node, the A concat B in this case, and also at the current expression to check the suffix that the word is matched. Okay. And then concatenation is just a simpler version of that, really, finding any split of the word and checking that the subregular expressions match the prefix and suffix. And then in the base case, if you're reading an alphabet symbol X, you just check the word I'm checking, the subword should be of length 1, and the letter that I'm actually looking at should be X. Okay. So if you believe that this is a correct interpreter of regular expressions, then our meta theorem gives you a decision procedure for learning regular expressions. Okay, so stepping back, what we have is these interpreters and a programming language for writing them, and a meta theorem which takes the interpreters and compiles them to tree automata and gives you decision procedures for these learning problems, with the decision procedures being based on tree automata emptiness. So now, which languages have we used this for to prove decidable learning and get algorithms? I'm going to talk about 2 of them, but in the paper there are 7 decidability results, and each of the interpreters is kind of interesting, so I'm happy to talk about them if you're curious. So here's one example. This is learning context-free grammars given words as examples. So the problem is you have some labeled words, positive and negative, like regular expressions, but now you want to find a context-free grammar that generates the positive words and doesn't generate the negative words. Right? So what you need to do is you have to represent this grammar somehow as a tree, so like this on the right here. Many ways to do it, I've just sort of picked one. And then you're going to write this interpreter that walks up and down on this tree, parses the word, and checks that it's generated. So it turns out you can do that with an amount of memory that's bounded by the size of the word, but not the length, the number of productions, or the size of the terms in the productions, right? And the memory that you need to do that roughly is subwords, a counter to handle recursion correctly, and then some extra bits of information to parse the word. Okay, this one is pretty cool. This is learning functional programs in the DSL from Sumit Gulwani's work on Flash Fill. So this is a DSL for writing programs that manipulate strings in spreadsheets, right? So you're wanting to move a string like international business machines to IBM, and you've got some looping programs. So this is actually decidable learning for a significant extension of his DSL. He had a restriction on the regular expressions, and there were no nested loops, and we can easily interpret those this way. And the memory roughly boils down to subwords, some bounded arithmetic, and finite maps. Okay, so here's the full list of results. We also looked at learning linear temporal logic formulas over infinite periodic words, learning modal, propositional modal logic on Kripke structures, computation tree logic on Kripke structures, and learning in an infinite domain of first-order queries over rational numbers with order. And then the last three, I've talked about regular expressions, context-free grammars, and functional programs in the Flash Fill DSL. I also want to point out this work generalizes, and you can get these recent results that we had in Popple 2 years ago on learning in finite variable logics. Okay, future work. This is a kind of a theoretical thing that I think is potentially interesting. So there are these classic constructions from model checking where you take properties, like a linear temporal logic formula phi, and you can construct automata that read execution traces of systems or programs, and these automata check that the trace has a certain property. What we're doing is kind of going in the other direction. So these are constructions for learning that take arbitrary structures, like arbitrary graphs, and they build automata that read syntax trees of programs or formulas and say yes or no if the programs or formulas work on a structure, right? So I'm wondering if there's some more formal connection that could be established here. Okay, the second one is, can we compile these interpreters to efficient learning algorithms, right? So under the hood, these tree automata constructions are fairly complex. There's two directions that the scaling happens in. There's structures getting larger, right? And that's a problem. And there's also more and more examples, right? So how can we tame both of these to get efficient algorithms in some cases? I think there's a lot of hope and promise for this. I think the Flash Fill work, it's written in terms of version space algebra. It turns out VSAs are an instance of tree automata. So I think there are good proofs of concept that these kinds of algorithms can be made practical by carefully designing the language to not be too complex to search. All right, to conclude, I've talked about learning symbolic concepts from structured data. We have many decidable learning results. You can obtain many, many more by writing these interpreters. And this is also an algorithmic framework for learning, right? Algorithms based on tree automata and emptiness. Many applications, like I mentioned at the beginning, so now it's time to tame the complexity. That's all I had to say. So thanks to my advisor, Madhu, and to friends and colleagues for good discussions on this work. And here's my website. Happy to answer questions over email also. I'm also on the job market, so if you like this work, please get in touch. I'd be happy to talk more about it. Thanks.
I'd like to invite the audience to come up to the microphones to ask questions, if anyone has any. And please just introduce yourself for the online audience.
Sofia Drosopoulou, thank you. Very interesting talk. I was a bit surprised that at some point you said you can go down and up the tree, but I thought that the interpreters that you wrote were doing pattern matching and therefore were only going down the tree. How is that?
Good question. Yeah, I talked about the regular expression interpreter, and that one, it stayed at the same node and it went down, but you're right, it didn't go up. They can also go up. In the context-free grammar case, you have to go up and down arbitrarily.
I thought that your interpreter language would forbid you from going up the tree, the way that you have defined the interpreter language.
No, you can go up, yeah. Thank you.
Hi, Paul. Great talk. I'm Gautam from CU Boulder. And great work as well. So I have a quick question about expressivity of the language that you have, right? So if I were to express a fully recursive functional language in your language, what is the blocker? Like, why can't I express? Because if I can express it, then the learning is decidable for a fully recursive functional language, right? But I'm assuming that's not the case. So what prevents me from writing a functional language in your?
Right, so these programs can be arbitrarily large, but the memory you need to evaluate them is bounded by these structures, examples. And all you need is that given fixed structures, inputs to a learning or synthesis problem, you can compute this amount of memory that you need, right? So if you imagined trying to interpret lambda calculus terms, you can't do that with bounded memory in any obvious way. I mean, you could fix the depth of the terms, you could do many things, but it would fail because you can't get a bound on how large the terms will get, and sort of they're kind of mixed together. The memory and the data and the program are kind of mixed there, and I don't know how to separate them. But
I see. Okay, thank you.
All right, let's thank the speaker again. Right, so both Yuval and Eran will be presenting the last talk of our session.
Hey, my name is Yuval Shapira, and together with me is Eran Avneri, and today we will present our paper, Deep Learning Robustness Verification for Few Pixel Attacks, done under the supervision of Dana Drexler-Cohen at the Technion. We start with an example of a few pixel attack. Consider this image. It was clearly 4, but by changing only 3 pixels, we fooled the neural network to classify it as 9. In contrast, consider this image of the digit 2. In this talk, we will show you how we formally proved that by changing at most 3 pixels, it is impossible to fool the same neural network from before to change its classification from 2. Okay, as most of you probably know, deep learning has become a very useful tool, specifically in image classification tasks. Unfortunately, previous studies have shown it is vulnerable to adversarial example attacks. An adversarial example is a slight perturbation of an image that causes a network to misclassify. For example, consider the panda image on the left, which is correctly classified by some neural network. Adding to it this little noise, which is undetectable by the human eye, makes the same network classify it as a gibbon, with great confidence. This weakness raises a great concern regarding safety and reliability of deep learning and neural networks. To address these concerns, various studies have shown methods to formally prove robustness of neural networks, focusing on a property called local robustness. This property means that no adversarial example could be found in a given neighborhood of an image. They typically work with box neighborhoods. Therefore, we call them box robustness verifiers. Their input is a neural network, an image, and a box neighborhood contains it, expressed by a sequence of intervals, 1 for each pixels. And the output is whether the network is robust to adversarial example in this neighborhood or not. We know that these kind of verifiers are suitable for proving robustness against attack models that change each pixel independently. In our work, we focus on a different kind of attacks, L0 attacks. Given a positive integer t, an adversary goal is to find an adversarial example by changing at most t pixels of the image. For example, on the left, there is a pole, and by changing a few dozens of pixels, it is misclassified as traffic light. In the right, there is a backpack, which is also misclassified by changing a few dozens of pixels.
An important property of the L0 neighborhoods is that they can be represented as sequences of intervals. For example, if t equals 1, the corresponding L0 neighborhood of an image with v pixels is all different perturbations that change only 1 pixel. So for each such perturbation, the corresponding sequence, there is a corresponding sequence of v intervals, each bounding the respective pixel value. If we change just one pixel, then all pixel values should be fixed, but one. And we should let this pixel value range over all possible values, say between 0 and 1. Since each sequence is uniquely determined by the pixels we can change, we can think of each sequence as the set of these pixels, as you can see in the slide. This representation naturally extends to all values of t, not just t equals 1, and we will use it from now on. We can also learn from this representation that in order to verify L0 robustness of an image with v pixels, we have to verify robustness of all of its t-sized subsets. This representation as sequences of intervals is important because we can use it in existing box robustness verifiers that Yuval talked about earlier. We can use this box robustness verifier in order to suggest a naive approach for solving the L0 robustness verification problem. We can simply iterate over all subsets of size t in the image. For each such subset, we can use an existing box robustness verifier and on the respective interval neighborhood, as we explained in the previous slide. If all subsets are robust, then the image is robust for L0 attack with parameter t. For example, if I have an image with 5 pixels, 1, 2, 3, 4, 5, and I want to verify L0, its robustness with respect to L0 attack with parameter t equals 3, so I will have to iterate over all of its 3-sized subsets and submit the corresponding neighborhood to the existing box robustness verifier, as you can see in the example in the slide. However, this approach fails to scale even for t equals 3. The reason for that is that the number of iterations of our naive approach is v choose t, which can be exponentially large in the general case. For example, if you consider an MNIST image of 784 pixels and the box robustness verifier that always completes in 1 millisecond, then for t equals 3, our naive approach will terminate after 22 hours. For t equals 4, 180 days. For t equals 5, 77 years. So clearly, we must find a better solution. Our main insight is that if a subset sized k, which is a number larger than t, is robust, then all of its subsets are robust, specifically all of its subsets of size t. So with a single query of an existing box robustness verifier, we can verify multiple t-sized subsets. For example, if we verify that the subset 1, 2, 3, 4 is robust, then all of its subsets are robust, specifically all of its subsets size 3. So we proved robustness of 4 subsets using just one query to the existing box robustness verifier. So that means that we can significantly reduce the number of queries to the existing box robustness verifier by submitting to it to a larger neighborhood. However, this approach faces many challenges and questions that arise. For example, we must understand how we choose the value of k. How do we do that? And how to choose the sets. And if we verify sets of size k, how do we know we've covered all sets of size t, since this is our purpose? And what happens if a set is not robust? Now Yuval will answer these questions.
Okay, to overcome these challenges, we will use a combinatorial object called covering designs. Given 3 parameters, v, which is greater than or equal to k, which is greater than or equal to t, covering designs deals with finding a group of subsets of size k of our universe, which is the numbers 1 to v, minimal as possible, such that every subset of size t of our universe is contained in at least one of these subsets of size k. For example, if v is equal to 5, our universe is the numbers 1, 2, 3, 4, 5. And here we have subset of size k equals 4, 3 of them, such that every subset of size 2 is contained in at least one of these subsets of size 4. Therefore, these 3 subsets of size 4s forms a 5, 4, 2 covering design. Finding minimal covering designs for arbitrary parameters is a hard combinatorial problem, but luckily this subject has been well studied. Okay, now we'll see how covering design can help us. Assume that we have an image with v equals 5 pixels, and we want to prove it is L0 robust for t equals 2. Also assume that we decided to use covering with size k1 equals 4. We will explain later how this decision is made. So here we have 3 subsets of size 4 in the slide. If all of the subsets of size 4 were robust, we could conclude that all of the subsets of size t equals 2 is also robust, because these 3 subsets covered them all. So we run the box verifier on them. First one is robust. The second one is not. But it does not mean it as a subset of size 2, which is not robust. So we make a refinement step and cover its subset of size 2 using subset of size K2, which is less than K1, let's say 3. And now we run the box robustness verifier on them. The first one is robust, and again, the second one is not robust. So we make another refinement step and cover its subset of size 2 using, in this case, subset of size 2. Now, we run the box verifier on them. The first one is robust, the second one is robust, and the third one is also robust. We go back up, this subset is robust, and the last one is also robust. In this procedure, we managed to find a group of subsets, robust subsets, such that every subset of size 2 is contained in at least one of them. Therefore, we proved that the image is L0 robust for t equals 2. Let's go back to our challenges. The procedure from the previous slide solves the second challenge. We choose the sets using covering designs. And by the way we choose them, we know that we cover all of the subset of size 2. What happens if a set is not robust? In this case, we make a refinement step, if possible, if its size is greater than t. And if its size is t, we found a subset of size t which is not robust, and we can terminate because we know that the image is not L0 robust for this t. Regarding the first challenge, which case should we choose? Now we can rephrase it more accurately at which refinement strategy to choose, meaning which sizes K1, K2, and so on to choose in our refinement strategy. So we want to choose refinement strategy efficient as possible. For that, we use programming, dynamic programming, and sampling. The technical details are in our paper for those of you who are interested. This method basically considers the trade-off consider the trade-off. When k is small, it is more likely that the subset of size k is robust. But when k is large, it has more subset of size t that it covers, and we can prove them all at once.
The two main parts that you've all just described, the covering designs procedure and the method of sampling and dynamic programming, are the two components of our contribution in the paper, an algorithm called Calzone, a certification analyzer for L0 neighborhoods. We implemented Calzone and evaluated it for T from 1 to 5 on several known image datasets, such as MNIST and C410, and on several neural networks, convolutional and fully connected. And now we discuss these results. So in the table, you can see our results for the MNIST datasets on few selected networks. First, we consider the different values of T and the number of subsets of size T that had to be verified. We can see here the exponential growth of this number. For T equals 1, 784 subsets had to be verified. For T equals 3, it already becomes 80 million subsets. For T equals 5, 2.4 trillion subsets. So we see again the importance of just iterating through them all. Let's take a look on an experiment we did with a convolutional network and T equals 3. Here again, we had to verify 80 million subsets. We gave Calzone a timeout for each image. We set a timeout of 30 minutes per image. And we gave it 100 images to go through. Out of them, 98 images were correctly classified by the network. And out of them, Calzone determined that 87 were robust for a text with L0 text with parameter T equals 3. 11 images were non-robust, and none of the images timed out. In the last two columns, you can see the average execution time for robust images and the average execution time for non-robust images. As you can see, on average, it took Calzone to determine, in either case, less than a minute. And as we saw in our results, no more than a few minutes generally. You can also see that it terminates faster in non-robust images than it is for robust images, and it is something that was repeatedly true mostly throughout our experiments. And now let's take a look on another experiment, which is more challenging, the case where T equals 5 and another convolutional network. Here, again, we had to verify 2.4 trillion subsets. We set, therefore, a higher value of timeout, 300 minutes, and gave Calzone 10 images to go through. 9 of them were correctly classified by the network. Calzone determined that 5 were robust, 3 were not robust, and 1 did time out. As for the average execution time, you can see that for robust images, it took Calzone much longer than the previous case, where t equals 3, over an hour on average, and few hours generally per image. And for the non-robust images, it is slower than before the case where t equals 3, but much faster than for the robust images, only a few minutes on average. To conclude, we present here Calzone, the first sound and complete L0 robustness analyzer for neural networks as far as we know. Typically, as we saw in the previous slide, Calzone completes within few minutes. On our most challenging instances, t equals 5, as we saw, Calzone completes within few hours. We put here a link to GitHub. We will upload our code there soon, so stay tuned. Thank you.
So we're just at time, so I think there's time for one or two quick questions. Please just introduce yourself.
Hi, thank you for the talk. I'm Theodora, I'm from NUS. So I was wondering, for L0, you have this few pixels attacks. Do you have any idea of what that means for an image? Like, for example, how many pixels does this make sense in the sense of like visually imperceptible changes? And this is the first question. The second question, have you considered other types of distances?
Do you mean for the first questions, like how much,
yeah,
like what happens in reality, like how many pixels you have to change to really fool a network?
Yeah. So for example, for L infinity, there are some studies that tell you that like 0.3 for MNIST is close to what would be considered human imperceptible, right? Visually imperceptible. So I'm just wondering, for this case, for L0, do you have such a metric that says, hey, 5 pixels for MNIST is enough for a human to also distinguish that this is a 4-digit and not a 9?
We don't really like have this number, like how many do you need? But as you see in our really in our first example, you can see the 3 pixels we've changed, and they cause the network to change it to a 9. So it really, you can see that it really closes the upper bridge between this. So we can see why it would become a 9, but we don't have like a benchmark that says I need 6 pixels, and then I guess it depends on the image as well.
Okay. And for the second question, have you considered other distances, and how would would this approach work for other types of distances?
I think like for the existing box robustness verifier usually work for like L infinity distances, and this approach is really used. It's the combinatorial structure of the L0 distance. Then you have number of pixels that change. Other distances usually say, well, you can. The distance is not something that has this combinatorial structure. So I don't think it will apply to other kind of distances.
Thank you.
Right, one last question from here.
Hi, I'm Pradeep. Sorry, again for NUS. Look, I mean, the question is interesting. You're phrasing it as a combinatorial question, right? Have you looked at the geometry of this question, which is, if I remove 1 pixel from the set, how much is the distance going to change? How much is the distance going to change, right? If you ask geometric questions as to the size of changes, you might make this procedure a lot more efficient, right? Because you're not doing it combinatorially, searching for the option, like the number of combinations. You're searching sort of geometrically. So have you thought about this approach at all, the geometric approach?
This is interesting, I agree. We basically don't treat all the pixels the same. We don't care which pixel we change, which is not the best. We can improve that. And I guess we can choose a covering in a way that pixels which are important in the image, not in the background or something, will appear less. And I guess it can improve the result.
Got it. Thanks. Wonderful.
All right. Thank you, sir. Idea for another paper. All right. Thank you, everyone, for coming. And I think there's a coffee break at this point.
So the first talk is a deductive verification infrastructure for probabilistic programming. And we have Philip Schroer from RWTH Aachen presenting the work. Thanks.
Yeah, thank you. So I'm Philip, and I'm going to talk about our new verification infrastructure to verify probabilistic programs. This is joint work with Kevin Butts, Benjamin Kaminski, Jos-Peter Cartoon, and Christoph Matea. So let's start with a simple probabilistic program. This is what we call the geometric loop program. We have two variables, C and run, and we initialize those to 0 and true respectively. Then we have a loop, and it runs while run is set to true. And now the loop body has this probabilistic choice, right? And with probability 50%, we enter the left branch, and we basically terminate the loop by setting run to false. And otherwise, with the other 50%, we increase the counter C by 1. So this is a simple probabilistic program, and we can look at various interesting properties about this one. So, for example, we can look at what is the probability of terminating in a state that satisfies C equal to 2. This is 25%. Then there's another property, the expected value of, so for example, the counter C after termination. So there are infinitely many possibilities, but the expected value is 1. And then this program is also almost surely terminating. So this is something about the probability of termination. There is a run that runs forever, right? There is this run where you always increase the counter, but the probability of it is 0. And then further, this program is what we call positively almost surely terminating. So this program has a finite runtime, which means in this case, the loop guard is evaluated twice, so the expected runtime is 2. And so we want to look at programs like these and obviously more complex ones and properties like these and verify them. So in general, we are interested in lower and upper bounds on expected values of probabilistic programs, expected runtimes, almost sure termination, positive almost sure termination, amortized expected runtimes, and then even more, probabilistic sensitivity, conditional expected values. And then in this other box here, I put in some of our proof rules that we use. So Park induction, K induction, martingale-based reasoning is required to reason about loops in probabilistic programs, so we also want to use them. And the motivation for our work really is the following. How do we automate the verification of probabilistic programs using these different properties, these different proof rules? And crucially, how do we make this extensible? How can we design it so that we can add more properties, more proof rules without lots of engineering? And the idea is inspired or taken from classical deductive verifiers, where this was very successful. You might know Boogie or Viper. These are intermediate languages to encode verification problems. And what we are doing is build an intermediate language to encode verification problems for probabilistic programs. Okay, so we want to build the probabilistic version of Boogie or Viper. So what does this look like? Well, we present our new intermediate language that we call HeyVL to verify probabilistic programs. And then in addition to this, we have a new logic, an assertion language to reason about quantities such as expected values, and we call this one Halo. And the semantics of HeyVL are given by so-called verification conditions, so that's this VC generator there, and tell us whether a program verifies or not. Then we have encodings of all of these different properties and proof rules into HeyVL that we also describe in our paper. And then finally, we have an implementation that takes a HeyVL program, generates these verification conditions in this logic, Halo, and then uses an SMT solver to try to determine whether the program verifies or not. And finally, we also implemented a front end, which makes this easier to, which automates the encoding of those proof rules and those properties into HeyVL itself. So this is our paper and our contribution in one slide, our verification infrastructure. So let's see how this works. And let's first talk about classical specifications for probabilistic programs, for classical programs, sorry. So in the classical setting, we look at predicates. Predicate is an assignment that maps each program state to a Boolean, yes or no. And this whole triple here for total correctness says, okay, if we start in a state that satisfies P, then we terminate, and also we terminate in a state that satisfies Q. We can phrase this somewhat differently and say P represents a subset of the states terminating in Q. And in deductive semantics, using what's known as weakest preconditions, we can say, okay, P is a subset of the so-called weakest preconditions of Q, which represents exactly the above here. Now, what's cool about intermediate verification languages is, at least that's one thing, you can use assumptions and assertions, so verification-specific statements to encode this specification here. You can assume the precondition before the program, and you can assert it at the end. So this creates this proof obligation. And then we encode the program as in the language again, for example, with proof rules for loops. And this is something that we want to do for probabilistic programs as well. So what's the setting in probabilistic programs? We look at now random variables or expectations, not just predicates. And these expectations, f and g, are mappings from states to non-negative real values or infinity. And now this triple here that I put down says for every initial state, f is a lower bound to the expected value of g. Okay, so now we shift to lower bounds on expected values from subsets. In deductive terms, this is there's a thing called weakest pre-expectations, which generalizes weakest preconditions. So now we say f is a lower bound to the weakest pre-expectation of g. And in Javier, our intermediate language, you can write this specification in the same way. You can assume the pre-expectation now f, and then you assert the post-expectation g, and you encode the program again. Now notice that f and g evaluate two numbers, right? So f might be 42 in some state or 3, and not just true or false. So now the crucial question is, how does this work? What does assume and assert mean in this quantitative setting? What is the semantics of Javier? And to understand this, we look at a logic on expectations, logical reasoning about these values. For the assertion, we assert an expectation f with a post-expectation g. We define the semantics as a minimum. So we take the least numeric value in each state. This corresponds to the classical setting where you would say both f and g must be true. And here, this is the minimum. But a bit more interesting or a bit more complex is how do we understand a quantitative assumption? What does assume f mean when f can evaluate to a number, right? And for this, we want to find some kind of implication on expectations. F and g are expectations, and this must evaluate to numbers again. And to understand what such an implication should look like, what it should be, we look at some properties that we want to have for it, right? And one property is that an implication, when we introduce it, g implies h down here, must make a proof easier. What I mean by this, g implies h, and with the lower bound f should be the same as looking at the minimum of f and g as a lower bound to h. Okay, so this means introducing an implication on the right-hand side of this inequality is the same as shifting this implication or this assumption g to the left-hand side, which really makes this inequality easier. Okay, so here the meaning is implications make verification easier. And this gives us what's known as a hating algebra, which is where the names Halo and Javier come from. The second property that we want to have is this deduction theorem that gives us exact comparisons, so to say. We compare two expectations f and g, and f is a lower bound to g if and only if our new implication that we're looking for evaluates to infinity between these two expectations. Okay, so we have on the left-hand side the property that tells us implications make stuff easier, and on the right-hand side it says we can exactly, using implications, encode comparisons. And these are very important to encode proof rules, for example, for loops. So what does the implication now look like? This is an example. 42 implies g. So g here is on the x-axis, and the interpretation of 42 implies g of this quantitative implication is assume g at least 42 to be true. What do I mean by this? Formally, this means in every state, you check, is 42 a lower bound to g? And that's the top right line over there. And then we give the quantitative equivalent of true, so that's infinity. If 42 is not a lower bound to g, then we return g unchanged. Okay, so this really means if g is at least 42, then we pull it up to infinity, otherwise we don't do anything. And so this is our basis for the logic of on expectations. We have an assertion and an assumption on expectations. So let's look at a very simple example. This is a very simple behavioral program with a quantitative assumption, C plus 0.5, and then a very simple probabilistic choice, and then the assert C at the end. And we want to check whether this program verifies in behavior. What does it mean in this intermediate verification language to verify? It means that we need to evaluate the semantics of this program, and we start at the bottom with infinity. We evaluate the semantics, and we must obtain infinity again. Then we say this program verifies. This is how we encode all of our proof rules. So we start at the bottom with infinity. We apply the semantics of the assert that we've seen before. That's the minimum between infinity and C, but this is the same as C. So we can simplify. And then we do the probabilistic choice, and the semantics is the expected value of C, which turns out to be 0.5 times C plus 0.5 times C plus 1. Okay, so with probability 50%, C is not changed, and with probability 50%, it decreases by 1. We can simplify this, we get C plus 0.5. And this gives us the implication C plus 0.5 implies C plus 0.5, which means this program verifies. And this encoding tells us, okay, C plus 0.5 is indeed a lower bound to the expected value of C. So this is how we encode simple specification for lower bounds in behavior. And so we've seen this third statement as a minimum, we've seen the assumption as an implication, and the havoc statement is a new one. This is a non-deterministic choice that corresponds to an infimum over all possible values of the variable x. And this kind of design satisfies one of our main goals, namely that behavioral generalizes classical IVLs. So in the classical IVL, we have a Boolean AND. We have a minimum. In the classical IVL, we have an implication. We have the Gödel implication. In the classical IVL, we have a for all, for the havoc semantics, and we have an infimum. So really, in a formal sense, we generalize classical IVLs to expectation-based reasoning. Another goal of ours was to reason about upper bounds on expected values. This is very natural when reasoning about expectations of probabilistic programs. For example, you want to say the probability of crashing is at most 10%, or the expected value is at most 42, right? So this is not that common in classical reasoning, but here it is. So this is why behavioral supports these co-assert, co-assume, and co-havoc statements, which correspond to the duals. Maximum Gödel co-implication, omitting this one here, and for the co-havoc, it's a supremum. Okay, so you can see these are exactly dual and allow us to do upper bound reasoning in our verification language as well. So to show you that this works, we have more than 40 examples verified with 12 proof rules for loops, doing lower and upper bounds reasoning, for example, with partial and total correctness, so that's probabilities, expected values, conditional expected values, expected runtimes, almost sure and positive almost sure termination. We also have encoded procedures with recursion, and user-defined data structures are also supported. And the point of this slide is to say, if you find a new proof rule, you can also encode it into HAVL and basically get automation for free. That's the hope. So just briefly to show you how this works for a very simple proof rule, let's say in the, you have a loop, while b do s, and we use a rule that requires invariance. In the classical setting, in the classical encoding, what you can do is use this encoding of a specific proof rule. This is the whole logic proof rule. In the beginning of the loop, when we encode it, we need to ensure that the invariant holds before the loop. Then we enter the loop, we assume that the invariant holds, and at the end we assert it again. So that's kind of the intuition. In the probabilistic setting, we now have an invariant that's quantitative. It's an expectation. So it looks very much the same. We still assert the invariant, assume it, and assert it at the end. But we have differences, right? We have an assume 0 instead of false. That's the quantitative version of it. And we also have this additional validate statement that it's necessary for the correctness in the probabilistic setting, and we have details on this in the paper. How do you get started with behavior? In the paper, we provide the details on syntax and semantics of behavior, or intermediate language. We detail our assertion language to reason about quantities, and we have case studies described for these different encodings of these proof rules. Online on caesarverify.org, you can find our tool. Caesar, it's written in Rust, it's open source, and we're actively maintaining it. So you can also find the language documentation and an extended version with more details of the paper. That's it. I'm happy to take any questions.
Any questions? So I have a couple of questions. So one is, I see that you are working with expectations, right? So
Yes.
it's only the first moment, or like, can you generalize this to higher moments, like variance, or the third or fourth moment, for example?
So when I say expectations, I just mean mappings from states to values, right? And this includes higher moments, but also, let's say, an exponential or something. So this includes, yeah, reasoning, like in theory, reasoning about all moments.
I see. And what kind of solver are you using for solving these verification conditions?
Right now we're using Z3, so we are encoding this halo, this verification question about halo as a Boolean query into Z3.
Got it.
But we are also looking into, trying more.
Thanks.
So in propositional reasoning, you have weakest precondition, which corresponds to the box in dynamic logic. I'm curious if your co-assume and co-assert, does that somehow correspond to like the diamond of dynamic logic?
Okay, so I'm not sure. I'm not too familiar with dynamic logic. I would be happy to talk to you about
Well,
this.
basically the idea is the box is you're sort of universally quantifying over all the non-deterministic possibilities, and the diamond is like you're existentially quantifying.
I mean, the universal and existential kind of corresponds to the Havoc main cohort equations. But I wouldn't, I would be cautious to claim any similarity. But we can talk about this.
Sure.
This sounds interesting.
All right. Thank you so much.
Thank you.
Are you Wenjia? Yeah. Okay, great. Thanks. Okay, so now we have Wenjia Ye, and she will talk about a gradual probabilistic lambda calculus.
Hello, everyone. I'm Wenjia Ye. I'm a PhD student from the University of Hong Kong under the supervision of Bruno Oliveira. Today, I will talk about the work with Matthias and Federico from University of Chile. The paper named Gradual Probabilistic Lambda Calculus. Suppose you have a simple application with authentication, and you have a user that Suppose you have a simple application with authentication. You have a user that connects to a login web application for a company. And then to authenticate, you prefer to ask if the user exists in the database of the company or not. So you consume a web service. And the web service is going to respond either this user exists or not exist. But this is not the only answer, because you could say, okay, if the API does not have connection to the database, then it's going to give you an error. We can zoom over the login module, and then you have two different modes, like development mode and or production mode. If you try to log in like Bob with some password, then the password, then the code related to that part of is this one. Before returning the login is correct or not, you first ask if the user is active or not. And the user is active is going to consume an external web service if you are in production mode. But if you are in development mode, then you don't want to consume the external web service. Maybe you just want to return true or false with a local code. empirically, you can check that the web service has a 90% uptime. And your boss tells you that you have to have 95% uptime. If he asks that and you don't do anything, you just run with this program and you just put this in production mode, you are going to fail to detect the impossibility to comply with the requirement because you don't do anything. So to model this specification, you can use probabilistic choice, n o plus n. This means that this expression behaves like m with probability p and with like n with probability 1 minus p. And you also have this probabilistic type, meaning that the type t subscribe I occurs with probability p subscribe I. If you use the combination of these two things, probabilistic choice and probabilistic type, you can type the external code with this type that is going to return a Boolean with 90% probability and an error with 10% probability, because this is the empirical information that you have. Maybe your local code can be type checked with as such, like it's going to succeed with 95% probability, and an error with 5% probability. You can type check the whole program like this. The external code has a 90% probability of success. Local code has a 95% probability of success. And if you mark its user active as a function that has a 95% probability of success, the external code is going to be yield type, because the external code has 90% probability of success, and you are expecting a 95% of success. So it's very conservative. To address this, you have greater typing, where you can use unknown to represent any type, because any type which causes error. So instead of fixing its user active with a 90% probability, you can set it as unknown, as while you are in developing mode. You can develop freely without worrying about failing. And if you are in production mode, you are going to fail at runtime. Yeah, so this is what happens. If production mode is true, then it's going to fail at runtime, because 90% is not equal to 95%. And if production mode is false, then it runs successfully. This is done by consistency relation. We can detect errors because consistency is not transitive. So here you have an example says that a 90% Boolean is consistent with unknown, and unknown is consistent with 95% Boolean, but transitive does not hold. So what we do is that we check at runtime if those type annotation is respected at runtime. If we add more annotations, if we increase the precision of the program, we are going to make the term yield type, because now we are going to statically detect that we are not satisfying the 95% requirement that we have in a login function. So besides that, we are able to encode imprecision probabilities. For instance, what if we want to specify that external code has an uptime of at least 95%? We do this by defining Boolean as 95% probability. And then also, you can have a Boolean with unknown probability and an error with unknown probability. There you have imprecision in the probabilities. And this unknown probability are subject to, of course, the probability has to sum up to 1. Another thing that you can do with this system is that you can synthesize probabilities. For instance, suppose you have a load balancer. You have many login attempts. So you want to balance the load of this access. This load balancer is going to sometimes drive you to a cheap server, and sometimes it's going to drive you to an expensive server. Besides, you know that the cheap server has a 90% uptime, and of course, it's very cheap. On the other hand, the expensive server is a very good server, and it has a 98% of uptime, but it's very expensive. If you want to ensure or guarantee at least 95% uptime, how should we distribute the request? So to know this answer, you could model this problem using gradual choice probabilistic. In this case, you can model the cheap server as a function that returns something with 90% probability, and the expensive server returns something with 98% probability. The external code is going to use a probabilistic choice, and the probability of the choice is going to be unknown. This is going to be type check, and at runtime, you can use symbolic variable to represent unknown probability. So you can run the program to know what are the restrictions for this symbolic variable in order to satisfy the requirement. At runtime, the main contribution is that we detect that the coupling as a key center pieces, and plausibility is composed of the use of coupling, the use of constraint, and the satisfiability of this constraint. For instance, if you have this consistency relation between unknown with probability unknown, and real with half probability, and Boolean with half, then this unknown with probability is going to represent like this, and the other hand is going to represent like this. So this will induce this lemma, this formula. So the coupling is going to induce the lemma to know if this consistency relation holds. We ask a SMT server, for instance, if this is satisfiable. So this could be more complex, and the answer will not always be 1. So we just list this example. And these are the constraints, and you can see the answer is is a range, not just one solution. Going back to the example, if you analyze the possible answer for the constraints, it's going to give you that the probability has to be less or equal than 37.5%. If you choose any probability less than that, then you can guarantee that the probability is going to be at least 95% to satisfy the requirement. And what's more, in the paper, we have a formalization about this language. We define a source and a target language. We show how to leave relation on gradual type to relation on distribution types using couplings. We also show operational semantics, define over distribution of values. And we show some properties, such as type safety and the gradual guarantee. And the gradual guarantee is the most complicated property to establish. If you have a function foo, which reduces to true with half probability, if you take a less precise version of the program, it should always also return a value according to the gradual guarantee. But in this case, this could reduce to the same probability, but to an error. So this seems that the dynamic gradual guarantee doesn't hold. But actually, what you have to do is to compare the value distribution of these two executions. So the first value execution is going to give you true and error with half probability each. And we say that is more precise than the distribution of true, unknown. and error with half probability each. So the dynamic gradual guarantee holds if we analyze the whole value distribution, not just for like the single execution. And we can, and to know more about the coupling, which we also use for the dynamic gradual guarantee, we can have a look for this more complex example, which I have mentioned, but I haven't gone into the detail. So you can have many answers. For instance, here you have, for consistency, you have 2 types. So a real with 1/2 and an unknown with 1/2. On the right, you have unknown with 1/3, a real with 2/3. You have many possibilities. You can connect the first with the second one, the first with the first one, and so on. If you write the set of constraints, it's going to something like this. The interesting thing is that you don't have, you can calculate this for, you can calculate for this symbolic variable, and then you can like in like in synthesized probability, you can have a range where you can choose for like to satisfy some requirement. Okay, and thank you.
Questions?
Hi, thank you for the talk. I have just one quick question. Do you support recursive definitions in your language? Sorry, do you support recursive definitions in your language? Like
Recursive definitions.
Recursive definitions?
Yeah.
What kind of recursive?
Like, for example, a factorial function with a non-deterministic choice? Or just a loop, an infinite loop where you choose that?
No, we don't have
okay.
Infinite loop.
Okay, thanks.
Yes, thanks for the talk. I'm just trying to have an idea of the type system. So you can have those distribution types. It seems like if you erase the probability, is it like union types to some extent? Because you can have a set of different values. Is that how we should think about those distribution types?
So you mean for the distribution type, it's like a union?
Yeah, is it a good intuition or?
Yeah, I think you can because it's because it's some like you have a set, and this set you have many types, and this type has their probability. So I maybe, but for union you don't have a constraint that the probability has to sum up to 1. So I think you cannot.
Yeah, right, like quantitative unions,
yes.
so to speak. And then I guess you can only use ground types, but not higher order types, for example.
Like, ground type?
Function types. I guess you don't have function types.
Oh, we have function type.
Within the unions, like you can have a distribution types of function types?
You mean in union you can have function?
I mean, in your distribution types, can you have higher order types, function types inside?
Oh, yes, we have function type
okay.
inside the distribution type.
Okay, thanks.
Thank you.
Sorry, I had a question about your dynamic gradual guarantee. Okay. The example you showed had the distribution, the value itself in the distribution was becoming more precise. It was going from dynamic to precise value. But can you also increase the probability of an error when you add type precision to a term?
At the precision in error?
Yeah, so when I change the precision of the term, couldn't I increase the probability that there's an error as well?
I think because they are the symbolic variable. So so for a probability for the exact number is calculated during at runtime. for the probabilistic, for the probability.
Okay, so I couldn't go from, is a because it could be if expression, then flip a coin, and then I could make that expression more precise and cause there to be a type error, and so the precise one would have a distribution heads and tails is 50-50, and then the precise version would have 100% chance of type error at runtime, right?
No,
I mean, maybe it's too
maybe
technical.
you can take it offline.
Yeah.
I think maybe not because because it's just check the dynamic gradual guarantee is checked by like in the coupling, and you when you check the coupling, if you have 100% of error, then you cannot satisfy the coupling.
Okay.
Yeah.
I want to talk more about that.
Thank you.
All right, let's thank the speaker one more time. Next up, we have Ming Shui, and he will talk about lower bounds for possibly divergent probabilistic programs.
Thanks for the introduction. Hello, everyone. My name is Ming Shui Chen. I'm an assistant professor from Zhejiang University in China. I'm going to talk about lower bounds for probabilistic programs. In fact, a new proof rule, so I'm kind of like to challenge Philip for his tool to encode the new rule. This is a joint work with Shenghua Feng, Han Su, and Naijun Zhang from Chinese Academy of Sciences, as well as Benjamin Kaminsky from Saarland University and Jus-Peter Katun from RWTH Aachen. Before I go into the very technical part, let me start with some fun fact, saying that a drunk man will find his way home, however, a drunk bird may get lost forever. I think this is a very nice interpretation of the mathematical principle, saying that a two-dimensional symmetric random walk on a lattice returns to the origin almost surely, which is, however, not the case for a 3D dimensional random walk. In fact, the precise probability that a drunk bird can return home is rather involved to compute. And hence, it is natural to ask the question, can we give some sound approximations of quantities like the like the probability of returning home? And in our paper, we provide such a mechanism to answer questions about such quantities from the perspective of computer science. And there, we model random walks as or stochastic processes as probabilistic programs, and the behavior of returning the origin as termination by violating some loop guards. So what is a probabilistic program? You have already seen many in previous talks. So this is a biased random walk where at each step you simply flip a biased coin, and then with probability 1/3 you go to the left, with probability 2/3 you go to the right. This process continues until you hit some termination flag at the origin 0. This is a simple-looking program, but it already induces some complex behaviors. For example, because of the biased nature of this coin, this program does not terminate almost surely. All right? And this brings extra difficulties in analyzing such probabilistic programs. And all the difficulties actually come from the fact that a probabilistic program is no longer a state transformer. Rather, it transforms a state distribution into another state distribution. In order to reason about such programs, we use the tool called weakest pre-expectations, which is a quantitative extension of Dijkstra's weakest precondition. Suppose we start from some initial state sigma here, we run the program C, and we may diverge here with some probability, and we may terminate at some final states. Suppose we are interested in some quantity, let's say f. Here is a mapping from state to some non-negative real number. And then we can simply take the expected value of all those quantities, and this gives us the weakest pre-expectation of the program. We use this WP to characterize the semantics of the loop, of the program C. And in this case, if we take 1 as the post expectation, then this gives us the termination probability of the program C. Let's look at a few examples. Now, the WP of this single assignment with respect to variable n is 5. This basically tells you the value of n after termination of the program will be 5, regardless of the initial state. This is a constant function that maps any possible initial state to the number 5. Here's another example where we have a probabilistic choice. And if you calculate the WP, this gives you the n plus 1/3. This expression tells you that the initial value of n after termination of this program will be increased by 1/3 in expectation. In fact, the WP of all the loop-free fragments from an imperative programming language can be calculated purely syntactically. But there's one exception. So for the loop construct, for example, let's say we are interested in post-expectation 1. Basically, we want to ask, what is the termination probability of this while loop? And this is not so intuitive anymore. For this particular example, I can show you that this is the precise WP, but calculating the precise WP for while loop is in general intractable. This is because the semantics of the loop, or the WP, corresponds to some least fixed point of some monotonic operator phi. This phi is often called the characteristic function of a while loop. I wouldn't go into detail there, but I hope most of you agree with me that computing the exact least fixed point is in general intractable. And that's why we want approximations of the least fixed point or the semantics of the loop by either putting an lower bound or an upper bound. Now for upper bound, this is easy because we have this very elegant theorem called Puck's lemma, saying that if we push a candidate upper bound u through the characteristic function, and this takes us down in the partial order, then this already suffices to show that u upper bounds the least fixed point. In terms of a picture, we start with a candidate upper bound u. We apply phi, this takes us down in the partial order. We keep doing so until we reach some fixed point. And then by the Knaus-Tarski theorem, this is necessarily an upper bound of the least fixed point. Now, can we have something similar for lower bounds? Namely, by simply flipping the direction of the inequality sign, and we obtain something for lower bounds. However, this turns out to be unsound. In terms of a picture, again, we start from some candidate lower bound L. We apply phi. This takes us upper in the partial order and until we reach some fixed point of phi. But this fixed point of phi is necessarily a lower bound of the greatest fixed point, not necessarily for the lower bound, for the least fixed point. And that's why we don't have a relation claiming that L lower bounds the least fixed point. And in order to fix this problem, there's a very nice paper by Marcel Hack et al. They propose to use some side condition to fix the problem. And here the side condition basically says the candidate lower bound is uniformly integrable in some sense. And this concept of uniform integrability comes from stochastic processes, which I wouldn't want to go into detail here. But just to give you a bit of flavor, this often requires some extra requirements on the programs. For example, this is only applicable to programs which terminate almost surely, and with some boundedness condition on the expectations. And what we want to do is to avoid such extra restrictions on our problem. To do so, we propose a new proof rule for lower bounds called the God strengthening rule, and this rule works in a quite straightforward way. For example, given a while loop with loop guard phi and loop body c, we simply rewrite this loop into a new one, which differs from the old one only in loop guard. So we have a new loop guard phi prime. Now our rule says, if the new loop guard strengthens the original one or implies, then a lower bound for the modified program with respect to some modified post-expectation suffices as a lower bound for the original loop semantics. What is the intuition behind that? Let's recall our biased random walk example. Suppose now we are interested in verifying some lower bound on the termination probability of this random walk. We can simply rewrite this loop into a new one by putting an upper bound m onto the variable n here. And m can be an arbitrary fixed natural number. This amounts to putting a barrier on the way of the random walk. And now it's obvious that the new loop terminates either by hitting the left bound 0 or by hitting the right bound m. Now, our rule claims that the probability that our new loop terminates by hitting the left bound 0 is a lower bound of the termination probability of the original loop. Why this is the case? Suppose we start from some location n. We can go either all the way to the left until we terminate. This is a valid terminating run for both of the two loops. We can do similarly by taking this, first go right and then all the way to the left. This is also a valid terminating run for the original loop. However, if we somehow want to cross the barrier and eventually terminate, this is a valid run for the original loop. However, because of the barrier we put there, this is no longer possible for the new loop. And in that sense, we lose some probability of termination. And that makes this quantity a lower bound of the original loop semantics. Okay, and now, even though in this form the rule looks quite simple, but sorry, I forgot something. That, the whole purpose that we do this guard strengthening is in the hope that the modified loop will feature a stronger termination probability. For example, in this case, the loop becomes asked. Okay, and in the hope that it's easier to verify uniform integrability and boundedness conditions on expectations. The rule is simple, but the proof is quite involved, I would say. So we basically investigate the difference between weakest pre-expectations of two arbitrary given loops, where we have to explore different categories of infinite traces. But for the sake of time, I wouldn't go into detail here. Yeah, now let me show you a few nice properties of our proof rule. The first, it is complete in the sense that whenever there exists a lower bound for the original loop, we can always find a strengthening such that this lower bound also lower bounds the modified loop semantics. This is true because you can simply take phi prime equals to phi. Right? But this does not necessarily give you a helpful strengthening because it doesn't do anything basically to the loop. And the second property is that the rule is general, as we have already seen, that is applicable to some possibly divergent probabilistic loop and unbounded expectations. To be more specific, recall our example of the biased random walk. In case now we want to verify something, some ugly-looking expression as a lower bound of the termination probability. And then we can simply apply our rule, and then we reduce the problem to finding some, or to verifying some lower bounds for the almost surely terminating program. And in this case, we can apply existing rules, for example, Hark's rule, to establish such a lower bound. The next property is that our rule is tight, in the sense that you can always pull this barrier up to the infinity, and this gives you the tightest most lower bounds, or under approximations. In our case, this corresponds to taking the limit over m, and this gives you a nice expression independent of m. And in this special case, you can even apply Park lemma to show that this expression suffices also as an upper bound, and hence we can claim that this is the precise semantics for the while loop. The very last property I'd like to show is that our rule can be partially automated, because whenever we can find a strengthened loop which has a finite state space, we can always use probabilistic model checking to find some non-trivial lower bounds for the modified loop. This applies already to our three-dimensional random walk example, where we know that the precise probability of returning to the origin from any neighboring location is something around 0.34. But we don't want to calculate this horribly looking expression. Instead, we apply our rule, and we restrict the state space of the random walk, and then we use Prism, for example, as the underlying probabilistic model checker. Then it gives us a picture like this. So this line indicates the precise probability. And as you can see, when our strengthening goes weaker and weaker to the right, we have tighter and tighter under approximations. This also confirms with our intuition that the further you deviate from the origin, so the further you go down, the lower probability you will return back. The very last example is called zero-conf protocol. This is just used to give you a bit of flavor how our rule can be applied in a somewhat real application. So this is a local network where whenever there's a new device coming in, the network itself tries to assign an unused IP address to the new device. And this algorithm is a randomized protocol because it uses communicating packets in between, and the packets can get lost with some probability. At the end, we are interested to verify some property saying that the probability of the protocol successfully terminating with an established IP address is at least of this quantity. However, using existing techniques, we were not able to do so. For example, the maximum number of packets allowed to send in this protocol is not bounded from above, and hence we cannot use probabilistic model checking. However, by applying our rule, let's say we simply put an upper bound 10 here, and then we were able to use some invariant synthesizers to find a good enough invariant to certify such a lower bound. In summary, we have presented a new lower bound rule based on WP difference and Gauss strengthening. This rule, to the best of our knowledge, is the first one that admits divergent loops with unbounded expectations. And our rule often produces tight lower bounds, for example, for the three-dimensional random walk and the zero-conf protocol. There are much more in the paper, for example, how to find a good strengthening, how to generate a non-trivial lower bound for the modified loop, and some corner cases where the Gauss strengthening is insufficient. If you are interested in that, check out our paper. With that, I'd like to conclude my talk, and thank you very much.
I think we have time for maybe one question. Okay, I'll ask a question. It was nice to see one practical application of this. I was also kind of curious, are there examples where this guard strengthening doesn't work? And could you maybe say a little bit about what kinds of programs those would be?
Yes, short answer is there is. I have two examples of this. So I wouldn't go into detail of that, but basically the first example says there is a program where just applying a very trivial strengthening does not work. Let's say simply putting a bound on some variable. This does not work. But we carefully tune such an example such that the variable takes values in a spiral pattern such that you can only use a circle as a strengthening, right? And the second example says there just does not exist any meaningful strengthening. We also have an example of that. Yeah.
Got it. Thanks. Let's thank the speaker one more time. Next, we have Colin McDonald, and he will talk about exact recursive probabilistic programming.
Good on the TV there. Cool. All right. It's good? Okay. So as motivation for this work, we find that probabilistic inference is common across a variety of fields, such as natural language processing, computational biology, artificial intelligence, and others. And also that manual coding of these inference algorithms is pretty tedious and error-prone. And this is where probabilistic programming languages, or PPLs, come in. They make inference really nice. You can program your model at a very high level with probabilistic code, and then have the compiler determine an inference algorithm for you and run that inference. And in general, we think that PPLs should have three attributes. First, we think that they should be expressive. You should be able to write or express your probabilistic model or distribution in a natural way, and we think that this frequently is with recursion. And you can see from this table that some PPLs, such as WebPeople, support recursion, while others, like DICE, do not. And it is the case that Purple, our language, also supports recursion. Further, we believe that they should be exact. Many PPLs only support sampling-based inference, where you only approximate from the true distribution. However, such sampling suffers from high variance and also lacks gradients, making it less useful within contexts like machine learning. And this is another area that Purple also supports exact inference in a differentiable way. And thirdly, we believe that they should be efficient. And this is, as you can see from this plot, this is an area where Purple really excels asymptotically, just being very efficient compared to many other PPLs. And really the key attribute in how we do this with Purple is through our use of a linear type system in which no bound variable is used twice. We'll see this come up over and over again throughout this talk and just how crucial it is for proving correctness of various transformations in addition to helping with our performance. And so the way Purple works is it takes your probabilistic program and via our denotational semantics translates it to a system of equations for which we can solve for the least fixed point and get out our exact distribution over values that we want. So with that, let's hop into an example Purple program. So say you have this context-free grammar where your start symbol S can go to SS and it can also go to A. And this is a probabilistic context-free grammar, or PCFG, in that it applies the first rule, S arrow SS, with probability P, and the second with probability 1 minus P. And we're asking, what is the probability that starting from S, we generate a finite string? That is, like, what is the probability that this PCFG terminates? And you can imagine that if P is equal to 1, then this is going to infinitely branch. We always apply the first rule and never get to a finite result. On the other hand, if P is equal to 0, then we always immediately apply this S arrow A rule and immediately terminate. But in between those two probabilities, there's a wide range of other possible strings with different probabilities ranging between 0 and 1. So the way we'd express this in Purple is with a program like this, and we'll walk through its operational semantics to see how it works. So we start out with a start symbol S, and then we just substitute it in for its definition, which is this if expression. And then again, we substitute in the definition of flip, and we get this expression here. And what amb does, or ambiguous, is it's a non-deterministic operator that selects the first argument, true, with probability P, and the second with probability, or the second argument, false, with probability 1 minus P. So you can see that reflected in these two edges here, labeled P and 1 minus P. And then we have if true, so we select the then case. And on the other side, we have if false, so select the else case. And then we multiply all the probabilities to each of these nodes to get the probability that we reach there. So S goes to SS with probability P, and to unit representing this terminal A with probability 1 minus P. However, operationally, the next step here is to start evaluating these S's down here, because this is not actually a leaf node. We can apply further reductions. So this is actually going to cause us to infinitely branch, and we'll never get the exact result that we want. But Purple doesn't actually use its operational semantics to run. It uses its denotational semantics. So let's see how that works. So each of these expressions here, or equations, really just denotes the probability that an expression results in a value. So you can see we have true subscript true, meaning that true always results in true, so we give that probability 1. And true never results in false, so we give that probability 0. And similarly, unit always results in unit. These are essentially our base cases. And then we can start building out from there. So we have amb, which selects true with probability P, its first argument, and in the second argument, false with probability 1 minus P. We also have this S semicolon S, which terminates essentially if both sub-expressions, both S, do as well. So we just multiply their probabilities together. And we have if, which multiplies the probability that flip is true with the then case, and also the probability that flip is false with the else case. And then finally, after doing some substitutions, we can find that S, the denotation of S is equal to P times S plus 1 minus P, which if you kind of squint at it and imagine that each thing within brackets is really just a symbol in an equation, and this is actually just a polynomial equation defined by this expression, and we can solve for the least fixed point of this and get our exact result out. So this is how the Purple compiler works, and it works fantastic in this particular case, and will give us the result we're looking for. However, there's a lot of other questions we could ask about this PCFG, not just what is the probability it terminates. For example, we could ask, what's the probability it generates a particular string, for example, AAA? So we believe that the most natural way to express this is by using recursive data types, not just recursive functions. So here we have a recursive string and a recursive nat type defined, and then we generate a string following this distribution. Then we have a function that tests is the length of a string equal to a nat, and at the end we just can say, did the string that S generated, does it have length 3? And in this way we test is the string equal to AAA. But there's a problem here for exact probabilistic programming languages. And generally, it's that they can't handle recursive data types because there are an infinite number of terms or values that could have that type. So in particular, for example, for NAT, we generate these denotational equations, and we need to generate infinitely many of them because we need a subscript for every possible value that has type NAT, which is 0 or 1 or 2 and so on. So it seems like we're stuck. But we have a combination of two algorithms that we apply that are whole code transformations that we apply to each of our programs that translate it into an operationally equivalent program, but with no recursive data types. And this is a major contribution of our paper. So we'll examine this exact program and see how we do that. So the first algorithm we'll talk about is defunctionalization. And what that does is it sees that we construct a NAT in 4 places, down here labeled at the bottom. And we label these with the locations. So we have location 0, location 1, 2, and 3. And what we do is we replace the recursive instances of NAT with a location, which is essentially a pointer to a NAT, instead of being in memory, but a location in the original code. And then we write an unfold function that basically dereferences the location. So you can see that it maps from L3 to 0, as it is in the original code, from L2 to successor of L3, from L1 to successor of L2, L0 to successor of L1. And the only other changes we have to make is instead of pattern matching on where we pattern matched on a NAT before, we now dereference or unfold the location. And then instead of constructing a NAT down here, we just give the location of that in the original code, which is L0. And in this way, we've changed NAT from a recursive data type to a non-recursive one without changing the operational semantics of this program. And if you're worried about probabilistic effects, our linear type system guarantees the correctness of this program even with those, such as AMP or factor. Because basically, we never duplicate effects. So if you apply the effect before or after you did in the original code, it's still fine because it still happens exactly once. Our second algorithm is refunctionalization. And what this does is it observes that we only ever pattern match on a string in one place. So instead of constructing it so we basically move the elimination site to where we introduce a string in the first place. So what we do is we redefine string to no longer be this recursive data type, but instead be a function type from location to bool that roughly corresponds to has length. And then we define nil to be the nil case of has length, which you can see the code is essentially the exact same, and similarly for cons. And in this way, we again translate string from being a recursive infinite data type to this finite function without changing the operational semantics of our program because of our linear type system. And while a sequence of these transformations doesn't always exist, if one does exist that eliminates all recursive data types in your program, then the Purple compiler will find it for you automatically. So to back up, what we just did is we had an infinite recursive string, and we refunctionalized it, which gave us this function type. So we went from infinite domain, or infinite set of possible values, to a finite one, and the size of that being the size of bool to the power of the size of location, which is finite, so that's awesome. However, it's still somewhat unsatisfactory because this is actually still exponential. And we can actually do better because of our linear type system. By realizing this is a linear arrow, we can actually more compactly represent functions as non-deterministic pairs, which gives us a polynomial representation rather than exponential. This has a huge impact on our performance. And speaking of performance, we've benchmarked this program against 2 other common probabilistic programming languages, WebPeople and DICE. You can see our results here. On the y-axis, note that it's already logarithmic. So both WebPeople and DICE quickly grow very large, whereas Purple has a much more gradual growth, matching up to string lengths even up to 400. And the way that it does this here is essentially by, via our denotational semantics, it translates this program into a system of equations that's essentially equivalent to the CYK algorithm, which is cubic. And in addition to recovering algorithms like that, our Purple compiler also recovers other algorithms, each described in this paper, each of which takes a naively exponential algorithm and turns it into a polynomial algorithm. And with Purple, you get all of these for free. So I think this is also just another really cool result of our compiler. And so in conclusion, I'd just like to say that we've seen how with Purple, we can have an expressive probabilistic programming language in which you get unbounded recursion and many recursive data types. And you also get exact and efficient inference on that. And we think this is a really unique position within the probabilistic programming languages field. So with that, I'd just like to conclude, and thank you.
Go ahead.
Thanks for the nice talk. If you have a probabilistic program, you always produce a nice output distribution, right? So could a Purple program not terminate with probability 1? And what would happen in this case? I still get the result, right? I don't just not terminate.
Right. So with Purple, it's actually weighted. So the probabilities don't need to sum to 1. They can be less than or even greater than 1. So perhaps you get a total probability 0.5 if 50% of the time you terminate and 50% it never does.
Okay, and that would still be meaningful in any way if I, as a user, just get a weirdly weighted output distribution?
I believe so, yes.
Thanks.
Yeah.
Hello. So in order to compare with DICE, you have actually unrolled the programs.
Yes, that's correct.
Right? So did you make a comparison with Psi, the system by ETH folks? Because that one is also about like exact inference with recursion. So I was wondering, they are also using a symbolic approach. So how the system behaves in comparison with them?
I do not believe we benchmarked against them. Is
Okay.
that correct, David and Ken?
Okay. Okay, thanks.
Yeah.
Hi, Colin. Thanks for the nice talk. I'm curious about how this sampling procedure interacts with ambiguity in the grammar. So if you want to sample strings of a certain length and you have a lot of ambiguity, maybe it biases certain ones, and you want to sample unique strings. Is that possible, or just any general thoughts about ambiguity in the grammar?
So the output of our program has to be a finite type or non-recursive type. So if you're like your program, like you're essentially not able to output a string as a result of your program, because via D-unity functionalization we need to produce a finite type. So if you wanted to find the probabilities of exactly specific strings, you could do that, but I don't think we can do arbitrary sampling of recursive data types.
Oh, okay.
Yeah.
Thank you.
Okay, well, let's thank the speaker one more time. So now the final presentation for this session is by David, and he's going to talk about solving string constraints with lengths by stabilization. And this is also a distinguished paper, so congratulations for that.
Just double space, it works on the test and not here. Yeah, that's what I'm trying to do. Thank you for the introduction. My name is David Chocholati, and I would like to tell you today how we solve string constraints with lengths using stabilization. This is a joint work with Yufang Chen from Academia Sinica in Taiwan. And I cannot move the presentation. Okay. For our motivation, we focus on a high demand of SMTs and string solvers, especially in the industry. In the industry, there is important to be able to reason about strings, for they are used for analysis of programs and manipulations of strings in programs, or for prevention attacks such as cross-site scripting or SQL injection. And one example to speak for them all could be how Amazon, in Amazon Web Services, uses a whole portfolio of several SMT solvers where they run this portfolio of SMT solvers simultaneously on a whole, as they say, 1 billion SMT queries each day. And for each query, then run this portfolio simultaneously. And whichever SMT solver finishes first, its result they take as a satisfiable and unsatisfiable for some string constraint. As you can see, there is a wide range of string solvers, Z3, CVC5, or derivatives of these string solvers, such as Z3 Trau or Z3 string 3RE, or separate ones such as Ostrich. So take a look at this example string formula. What we can see here is that there are equations and disequations. There are regular constraints, which talk about variables in the equations and disequations. There are length constraints, again, talking about lengths of some variables in the equations and disequations. Or there can be also some other more complex string operations and constraints, such as substring or contains. So how can we solve this string formula with these constraints? Our approach is to use a combination of two automata-based algorithms. The first algorithm is called stabilization. It's a novel approach where we tightly integrate equations with regular constraints. It is a fast approach, and it can easily solve equations with regular constraints, but due to how the algorithm works, it cannot solve length constraints. But we can and we want to solve length constraints. Therefore, we combine this algorithm with another older approach called align and split, which is a slower approach, but can solve length constraints. Furthermore, we expand this combined approach to be able to solve these equations and other string constraints, which expand the formula or a part which can be solved to the whole formula which we saw earlier. So for the first algorithm, align and split can solve length formulas with equations and regular constraints, where we have an equation and each variable in the equation has assigned some regular language. And somewhere in the constraint formula, there is a length constraint, such as the length constraint at the end for variable x. First, we do a full equation alignment, where we align the left-hand side of the equation and the right-hand side above each other. And we try to see where are the borders, relative borders of each of the variables. So for example, the variable x can either be inside u, or inside v, or inside w. And we get these case splits. So for the first case split, the variable x has a border inside w. Each of the case splits need to be handled separately. Note that we generated here 6 case splits. It's too much to use this algorithm alone, therefore the combination. But for the first case split that is generated here, we note this equation alignment with substitutions which we append to the formula. And okay. And then with operation on automata. Remember, each of these variables is represented in our approach as a automaton, finite automaton. Therefore, we can do some automata splitting and compute this formula into a pure regular constraint formula, which contains only regular constraints. The equations are eliminated thanks to the automata splitting. And thanks to the monadic decomposition, this gives us possibility to extract lengths from these regular constraints. There are regular constraints represented by automata, and from each automaton for each variable, we can extract some regular length constraints, which we then append with the length constraints in the input formula. And what we get is a new length formula, which we can pass to SMT Lia solver. Lia stands for linear integer arithmetic, which will give us an answer for satisfiable or unsatisfiable. The second approach is stabilization. Stabilization is our novel approach, which is really fast for equations and regular constraints, but it cannot solve length constraints because there is no monadic decomposition, so no length extraction. But there are no splits, as in the equation alignment splits, and no new variables are introduced, such as the subparts of the variables which were introduced in the equation alignment. We concatenate the languages for each of the sites in the equation. One with a special delimiter, that's the pound symbol, and the other normal concatenation, again in types of automata. And then do automata product construction, which we modified in a smart way to be able to refine languages for each of the variables. Once we refine these languages, we can simply check whether some of the languages is empty. If it is empty, the formula is unsatisfiable. If all of them are refined and non-empty, then the formula is satisfiable. If we combine this algorithm, we want to use stabilization, which is fast, for all of the parts in the formula which only talk about regular constraints and equations, but not about lengths. If we have lengths, we have to use the align and split method. Therefore, we do only a partial equation alignment. We again align left-hand side, right-hand side of the equation above each other, reason about where the possible borders of the variables can be. But now we reason only about the possible borders of the length variables. That's x in this case. Y and z can be considered as a single variable for the purpose of this partial equation alignment. Notice that the k-splits here are only 3 instead of 6. That's the improvement that we've made. Then each of the k-splits needs to be again solved separately, but we can split the problem for each split into sub-problems. One for the length part, which can be solved easily by align and split, thanks to monadic decomposition, and the non-length part, let's say, which can be solved even more easily thanks to stabilization, because there are no lengths now. The lengths have been extracted only to this left part in this k-split. And the same goes for the other splits. Then we took this approach combined and we extended it even further. We extended it with string constraints, which can be solved easily by rewriting them into more simple constraints, and by saturation of basic constraints, the performance increases. Also, we added support for unrestricted these equations, again by eliminating them and rewriting them into another form of length formula, which can be solved by SMT Lia solver. And we get an algorithm which is complete on the chain-free fragment, and even extend it further with unrestricted these equations, which gives us a new largest known fragment, decidable fragment, which contains equations and Aristoteles equations, regular constraints, and length constraints. We implemented this approach in Z3 Noodler, which is based on top of Z3, and it replaces this theory of strings. Our solver is a string solver, so it replaces this theory of strings and some other parts of Z3. Then for our approaches, we need automata, finite automata and quick operations on them. For that, we implemented our own automata library Mata, which handles the representation of automata and operations on them. What we get is a very fast and string solver, which is complementary to state-of-the-art string solvers used in the industry. As you can see in the examples, in the first table, we have taken benchmarks from praxis, from real problems, which are part of SMT-lib, and we've split them into 3 groups. One is for regex-heavy benchmarks, one is for equations-heavy benchmarks, and one is for benchmarks which are heavy with predicates or predicate uses. As you can see, Z3 Noodler performs well on mostly all of these. It has the least number of unsolved instances for a large number of benchmarks, or at least it's close to the best string solvers for the given benchmark. In the second table, we can also see that the average runtimes of the Noodler are the lowest for the first 2 groups of benchmarks. If we take a look at a comparison in these scatter graphs with Z3 and CVC5, we can easily see the 90-degree axis here in the graph and here, which shows us that the Z3 Noodler is complementary to both CVC5 and Z3. If CVC5 and Z3 cannot solve it, we can solve it really fast, as opposed to what CVC5 and Z3 has to compute. If you take a look at what the first example I gave for Amazon Web Services, we take a portfolio of several SMT solvers, run them together, and compare them with the performance of Z-Noodler in this cattle prod. We can again see that Z3 Noodler is complementary to the whole portfolio. And even in the cactus plots, we can see that Z3 does really well on its own. That's the green line. But if we combine Z3 here and here, but if we combine Z3 Noodler only with, for example, CVC5, we get basically the same performance as we would get if we run all of these 7 SMT solvers together simultaneously. So instead of 7 SMT solvers, we have to run only 2. Z3 Noodler and CVC5, and we get basically the same performance and solve the same number of instances. This can be easily seen in the table, where if we take the virtual best solver and remove Z3 Noodler here and here, the performance increases drastically, and also the number of unsolved instances increases. So to conclude the presentation, I've talked about our approach, which combines 2 algorithms. One of stabilization to easily and quickly solve string constraints with equations which are tightly integrated together, and a line and split approach, which solves equations with lengths. Also, we implemented this approach in new string solver, which uses as an underlying library for handling of automata, our library Mata. And right now, as Z3 Noodle and both with Mata are ongoing projects, we work on supporting string constraints, other string constraints, adding support for transducers, and also to generate witnesses or certificates. This would be all for my talk, and now there is a place for questions, I believe, and thank you for your attention.
questions?
Thanks for the talk. So I have like some functionality question about, so is this decision procedure can apply to some string operations like reverse, lower, upper case?
We can also reason about these constraints, but currently we support only constraints which appear in the SMT string theory specification. So for example, substring, index of, contains, and this kind. For example, to upper, I believe it's not in the SMT.
So the point is that you haven't tried these.
We haven't tried these. We don't have benchmark for these. And frankly, the approach would be to take, or create some benchmark with these constraints and rewrite these difficult string constraints to some form of easily solvable constraints which contain length constraints, equations or these equations, and regular constraints again.
Yeah, but I think a follow-up question is I think in real world we have so many like unbounded strings. For example, I think one problem I could think of is, let's imagine you have a string S which matches A+, and we know that S reverse is equal to S itself, and we want to prove this theorem using SMT solver, which means you want to check the negation is unsatisfiable. So do you think this kind of problem can be solved in this framework?
I believe that yes, it can be solved. Again, as I said, we can rewrite this constraint into some kind that, for example, the reverse of a string has the same length as the original string, and the index of the first symbol in the string is at the index of the last symbol of the reverse string.
Yeah, but since this S is unbounded, so how can you specify the last index of a string? Because it can be infinitely long. So do you think that will also apply in this case?
I believe that, yeah, it would apply, because you would just create a harder constraint which would tell that the index is length of the string -1, for example. That's that's the specification of the problem in formula.
Yeah, thank you.
Hi, I'm Prateek. I'm from NUS. Excellent work. I just have a very short question. So do you support word equations as part of the theory or not?
Word equations?
Yeah.
Yeah, we support word equations.
They're all part of, and the whole subset that you have right now is still completely decidable.
Yeah, it is decidable.
Okay, thanks.
All right, let's thank the speaker one more time. So that was the last talk. Thank you so much, everyone.